Figure of a bull and a graph of market prices. Standard and Poor's Index with dividends reinvested, credit bull. Modification of work by Prayitno Hadinata, credit graph. Modification of work by Measuringworth. Chapter outline 3.1 functions and function notation, 3.2 domain, and range 3.3 rates of change, and behavior of graphs 3. 4 composition of functions 3. 5 transformation of functions 3. 6 absolute value functions 3. 7 inverse functions toward the end of the 20th century. The values of stocks of internet and technology companies rose dramatically. As a result, the Standard and Poor's stock market average rose as well. The graph above tracks the value of that initial investment of just under $100 over the 40 years. It shows that an investment that was worth less than $500 until about 1995 skyrocketed up to about $1,100 by the beginning of 2000. That 5-year period became known as the dot-com bubble because so many internet startups were formed. As bubbles tend to do, though, the dot-com bubble eventually burst. Many companies grew too fast and then suddenly went out of business. The result caused the sharp decline represented on the graph beginning at the end of 2000. Notice, as we consider this example, that there is a definite relationship between the year and stock market average. For any year we choose, we can determine the corresponding value of the stock market average. In this chapter, we will explore these kinds of relationships and their properties. Learning objectives in this section, you will determine whether a relation represents a function, find the value of a function, determine whether a function is one-to-one, use the vertical line test to identify functions, graph the functions listed in the library of functions. A jetliner changes altitude as its distance from the starting point of a flight increases. The weight of a growing child increases with time. In each case, one quantity depends on another. There is a relationship between the two quantities that we can describe, analyze, and use to make predictions. In this section, we will analyze such relationships. Determining whether a relation represents a function, a relation is a set of ordered pairs. The set of the first components of each ordered pair is called the domain, and the set of the second components of each ordered pair is called the range. Consider the following set of ordered pairs. The first numbers in each pair are the first 5 natural numbers. The second number in each pair is twice that of the first. 1, 2, 2, 4, 3, 6, 4, 8, 5, 10. The domain is 12,345. The range is 246,810. Note that each value in the domain is also known as an input value or independent variable, and is often labeled with the lowercase letter x. Each value in the range is also known as an output value or dependent variable, and is often labeled lowercase letter. Why a function f is a relation that assigns a single value in the range to each value in the domain. In other words, no x values are repeated. For our example that relates the first 5 natural numbers to numbers double their values, this relation is a function because each element in the domain, 12,345, is paired with exactly one element in the range, 246,810. Now let's consider the set of ordered pairs that relates the terms even and odd to the first 5 natural numbers. It would appear as odd 1, even 2, odd 3, even 4, odd 5. Notice that each element in the domain, even odd, is not paired with exactly one element in the range, 12,345. For example, the term odd corresponds to 3 values from the range, 135, and the term even corresponds to 2 values from the range, 24. This violates the definition of a function, so this relation is not a function. Figure 1 compares relations that are functions and not functions. 3 relations that demonstrate what constitute a function. Figure 1a, this relationship is a function because each input is associated with a single output. Note that input q and r both give output n. B, this relationship is also a function. In this case, each input is associated with a single output. C, this relationship is not a function because input q is associated with 2 different outputs. Function of function is a relation in which each possible input value leads to exactly one output value. We say the output is a function of the input. The input values make up the domain, and the output values make up the range. How to given a relationship between two quantities, determine whether the relationship is a function. Identify the input values. Identify the output values. If each input value leads to only one output value, classify the relationship as a function. If any input value leads to two or more outputs, do not classify the relationship as a function. Example 1, determining if menu price lists are functions. The coffee shop menu, shown below, consists of items and their prices. Is price a function of the item? B, is the item a function of the price? A menu of donut prices from a coffee shop where a plain donut is $1.49 and a jelly donut and chocolate donut are $1.99. Solution: let's begin by considering the input as the items on the menu. The output values are then the prices. A menu of donut prices from a coffee shop where a plain donut is $1.49 and a jelly donut and chocolate donut are $1.99. Each item on the menu has only one price, so the price is a function of the item. B, two items on the menu have the same price. If we consider the prices to be the input values and the items to be the output, then the same input value could have more than one output associated with it. See the image below. Association of the prices to the donuts. Therefore, the item is not a function of price. Example 2, determining if class grade rules are functions in a particular math class, the overall percent grade corresponds to a grade point average. Is grade point average a function of the percent grade? Is the percent grade a function of the grade point average? Table 1 shows a possible rule for assigning grade points. Percent grade 0, 56, 57, 61, 62, 66, 67, 71, 72, 77, 78, 86, 87, 91, 92, 100 grade point average 0. 0, 1, 0, 1, 5, 2, 0, 2, 5, 3, 0, 3, 5, 4, 0. Table 1 solution for any percent grade earned. There is an associated grade point average. So the grade point average is a function of the percent grade. In other words, if we input the percent grade, the output is a specific grade point average. In the grading system given, there is a range of percent grades that correspond to the same grade point average. For example, students who receive a grade point average of 30 could have a variety of percent grades ranging from 78 all the way to 86. Thus, percent grade is not a function of grade point average. Try it 1. Table 21 lists the 5 greatest baseball players of all time in order of rank. Player rank: Babe Ruth 1, Willie Mays 2, Ty Cobb 3, Walter Johnson 4, Hank Aaron 5. Table 2. A, is the rank a function of the player name? B, is the player name a function of the rank? Using function notation, once we determine that a relationship is a function, we need to display and define the functional relationships so that we can understand and use them, and sometimes also so that we can program them into computers. There are various ways of representing functions. A standard function notation is one representation that facilitates working with functions. To represent, height is a function of age. We start by identifying the descriptive variables h for height and a for age. The letters fg and h are often used to represent functions just as we use xy, and z to represent numbers and ab, and c to represent sets. His letter 1 d453, o f letter 1 d44 letter 2 and 0e equals letter 1 d453. Letter 1 d44e letter 1 d453. Letter 1 d44e we name the function f. Height is a function of age. We use parentheses to indicate the function input. We name the function f. The expression is read as letter 1 d453 OFA. Remember, we can use any letter to name the function. The notation letter 210e, letter 1 d44e, shows us that h depends on a. The value a must be put into the function h to get a result. The parentheses indicate that age is input into the function. They do not indicate multiplication. We can also give an algebraic expression as the input to a function. For example, letter 1 d453, letter 1 d44e plus letter 1 d44f means first add a and b, and the result is the input for the function f. The operations must be performed in this order to obtain the correct result. Function notation: the notation letter 1 d466 equals letter 1 d453, letter 1d465, defines a function named f. This is read as y is a function of x. The letter x represents the input value, or independent variable. The letter y, or letter 1d453, letter 1d465, represents the output value, or dependent variable. Example 3, using function notation for days in a month. Use function notation to represent a function whose input is the name of a month and output is the number of days in that month. Assume that the domain does not include leap years. Solution: the number of days in a month is a function of the name of the month, so if we name the function f, we write days equals letter 1d453, month, or letter 1d451 equals letter 1d453, letter 1d45a. The name of the month is the input to a rule that associates a specific number, the output, with each input. The function 31 equals f, January, where 31 is the output, f is the rule, and January is the input. Figure 2, for example, letter 1d453, March equals 31, because March has 31 days. The notation letter 1d451 equals letter 1d453. Letter 1d45a reminds us that the number of days, d, the output, is dependent on the name of the month, m, the input. Analysis: note that the inputs to a function do not have to be numbers. Function inputs can be names of people, labels of geometric objects, or any other element that determines some kind of output. However, most of the functions we will work with in this book will have numbers as inputs and outputs. Example 4, interpreting function notation. A function A gives the number of police officers, n, in a town in year y. What does letter 1d453, 2005 equals 300 represent? Solution: when we read letter 1d453, 2005 equals 300, we see that the input year is 2005. The value for the output, the number of police officers, n, is 300. Remember, the statement letter 1d453, 2005 equals 300 tells us that in the year 2005 there were 300 police officers in the town. Try it too. Use function notation to express the weight of a pig in pounds as a function of its age in days d. Q and A, instead of a notation such as letter 1d466 equals letter 1d453, letter 1d465, could we use the same symbol for the output as for the function, such as letter 1d466 equals letter 1d466, letter 1d465, meaning y is a function of x? Yes, this is often done, especially in applied subjects that use higher math, such as physics and engineering. However, in exploring math itself, we like to maintain a distinction between a function such as f, which is a rule or procedure, and the output y we get by applying f to a particular input x. This is why we usually use notation such as letter 1d466 equals letter 1d453, letter 1d465. Letter 1d443 equals letter 1d44a, letter 1d451, and so on. Representing functions using tables. A common method of representing functions is in the form of a table. The table rows or columns display the corresponding input and output values. In some cases, these values represent all we know about the relationship. Other times, the table provides a few select examples from a more complete relationship. Table 3 lists the input number of each month. January equals 1, February equals 2, and so on, and the output value of the number of days in that month. This information represents all we know about the months and days for a given year. That is not a leap year. Note that, in this table, we define a days in a month function f, where identifies months by an integer rather than by name. Month number, m, input, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 days in month. D, output, 31, 28, 31, 30, 30, 130, 30, 130, 130, 30, 130, 30, 1. Table 3. Table 4 defines a function. Remember, this notation tells us that g is the name of the function that takes the input n and gives the output q. n1, 2, 3, 4, 5, q8, 6, 7, 6, 8. Table 4. Table 5 displays the age of children in years and their corresponding heights. This table displays just some of the data available for the heights and ages of children. We can see right away that this table does not represent a function because the same input value, 5 years, has two different output values, 40 in and 42 in. Age in years, A input, 5, 5, 6, 7, 8, 9, 10 height in inches, H output, 40, 42, 44, 47, 50, 52, 54 table, 5 how to given a table of input and output values. Determine whether the table represents a function. Identify the input and output values. Check to see if each input value is paired with only one output value. If so, the table represents a function. Example 5 identifying tables that represent functions which table, table 6, table 7, or table 8 represents a function, if any. Input output 2, 15386, table 6, input output. 350145, table 7, input output 105254, table 8 solution, table 6, and table 7 define functions. In both, each input value corresponds to exactly one output value. Table 8 does not define a function because the input value of 5 corresponds to two different output values. When a table represents a function, corresponding input and output values can also be specified using function notation. The function represented by table 6 can be represented by writing letter 1d4532 equals 1, letter 1d453, 5 equals 3, and letter 1d453. 8 equals 6 similarly. The statements letter 1d454, minus 3 equals 5, letter 1d454, 0 equals 1, and letter 1d454. 4 equals 5 represent the function in table 7. Table 8 cannot be expressed in a similar way because it does not represent a function. Try it 3. Does table 9 represent a function? Input output 110, 2, 103, 1000, table 9, finding input and output values of a function when we know an input value and want to determine the corresponding output value for a function, we evaluate the function. Evaluating will always produce one result because each input value of a function corresponds to exactly one output value. When we know an output value and want to determine the input values that would produce that output value, we set the output equal to the function's formula and solve for the input. Solving can produce more than one solution because different input values can produce the same output value. Evaluation of functions in algebraic forms. When we have a function in formula form, it is usually a simple matter to evaluate the function. For example, the function letter 1d453, letter 1d465, equals 5 minus 3 letter 1d4652 can be evaluated by squaring the input value, multiplying by 3, and then subtracting the product from 5. How to given the formula for a function, evaluate. Substitute the input variable in the formula with the value provided. Calculate the result. Example 6 evaluating functions at specific values. Evaluate letter 1d453, letter 1d465, equals letter 1d4652 plus 3 letter 1d465 minus 4 at A2 B A C D. Now evaluate letter 1d453, letter 1d44e plus letter 210e minus letter 1d453, letter 1d44e. Letter 210e solution, replace the x in the function with each specified value. A, because the input value is a number. 2, we can use simple algebra to simplify. Letter 1d453, 2 equals 22 plus 3, 2 minus 4 equals 4 plus 6 minus 4 equals 6b. In this case, the input value is a letter, so we cannot simplify the answer any further. Letter 1d453, letter 1d44e, equals letter 1d44e 2 plus 3 letter 1d44e minus 4c with an input value of a plus h. We must use the distributive property. Letter 1d453, letter 1d44e plus letter 210e equals letter 1d44e plus letter 210e 2 plus 3. Letter 1d44e plus letter 210e minus 4 equals letter 1d44e 2 plus 2 letter 1d44e letter 210e plus letter 210e 2 plus 3 letter 1d44e plus 3 letter 210e minus 4d. In this case, we apply the input values to the function more than once, and then perform algebraic operations on the result. We already found that letter 1d453, letter 1d44e plus letter 210e equals letter 1d44e 2 plus 2 letter 1d44e letter 210e plus letter 210e 2 plus 3 letter 1d44e plus 3 letter 210e minus 4. And we know that letter 1d453. Letter 1d44e equals letter 1d44e2 plus 3 letter 1d44e minus 4. Now, we combine the results and simplify. Letter 1d453. Letter 1d44e plus letter 210e minus letter 1d453. Letter 1d44e letter 210e equals letter 1d44e2 plus 2 letter 1d44e letter 210e plus letter 210e2 plus 3 letter 1d44e plus 3 letter 210e minus 4 minus letter 1d44e2 plus 3 letter 1d44e minus 4 letter 210e equals 2 letter 1d44e letter 210e plus letter 210e2 plus 3 letter 210e letter 210e equals letter 210e. 2 letter 1d44e plus letter 210e plus 3 letter 210e equals 2 letter 1d44e plus letter 210e plus 3 factor out h. Simplify. Example 7, evaluating functions given the function letter 210e. Letter 1d45d equals letter 1d45d2 plus 2 letter 1d45d. Evaluate letter 210e4. Solution to evaluate letter 210e. 4. We substitute the value 4 for the input variable p in the given function. Letter 210e. Letter 1d45d equals letter 1d45d2 plus 2 letter 1d45d letter 210e. 4 equals 4. 2 plus 2, 4, equals 16 plus 8 equals 24. Therefore, for an input of 4, we have an output of 24. Try it for given the function letter 1d454. Letter 1d45a equals letter 1d45a minus 4 square. Evaluate letter 1d454, 5. Example 8, solving functions given the function letter 210e. Letter 1d45d equals letter 1d45d 2 plus 2 letter 1d45d. Solve for letter 210e. Letter 1d45d equals 3. Solution letter 210e. Letter 1d45d equals 3 letter 1d45d2 plus 2 letter 1d45d equals 3 letter 1d45d2 plus 2 letter 1d45d minus 3 equals 0. Letter 1d45d plus 3. Letter 1d45d minus 1 equals 0. Substitute the original function letter 210e. Letter 1d45d equals letter 1d45d2 plus 2 letter 1d45d. Subtract 3 from each side. Factor. If letter 1d45d plus 3, letter 1d45d minus 1 equals 0, either letter 1d45d plus 3 equals 0 or letter 1d45d minus 1 equals 0, or both of them equal 0. We will set each factor equal to 0 and solve for p in each case. Letter 1d45d plus 3 equals 0. Letter 1d45d minus 1 equals 0. Letter 1d45d equals minus 3 letter 1d45d equals 1. This gives us two solutions. The output letter 210e. Letter 1d45d equals 3 when the input is either letter 1d45d equals 1 or letter 1d45d equals minus 3. We can also verify by graphing as in figure 3. The graph verifies that letter 210e, 1 equals letter 210e, minus 3 equals 3 and letter 210e, 4 equals 24. Graph of a parabola with labeled points, minus 3, 3, 1, 3, and 4, 24. Figure 3, try it 5 given the function letter 1d454. Letter 1d45a equals letter 1d45a minus 4 square, solve letter 1d454. Letter 1d45a equals 2. Evaluating functions expressed in formulas. Some functions are defined by mathematical rules or procedures expressed in equation form. If it is possible to express the function output with a formula involving the input quantity, then we can define a function in algebraic form. For example, the equation 2 letter 1d45b plus 6 letter 1d45d equals 12 expresses a functional relationship between n and p. We can rewrite it to decide, if p is a function of n, how to given a function in equation form, write its algebraic formula. Solve the equation to isolate the output variable on one side of the equal sign, with the other side as an expression that involves only the input variable. Use all the usual algebraic methods for solving equations, such as adding or subtracting the same quantity to or from both sides, or multiplying or dividing both sides of the equation by the same quantity. Example 9, finding the algebraic form of a function. Express the relationship 2 letter 1d45b plus 6 letter 1d45d equals 12 as a function letter 1d45d equals letter 1d453, letter 1d45b, if possible. Solution: to express the relationship in this form, we need to be able to write the relationship where p is a function of n, which means writing it as letter 1d45d equals z, xp, ressionvinvolving letter 1d45b. 2 letter 1d45b plus 6 letter 1d45d equals 126 letter 1d45d equals 12 minus 2 letter 1d45b letter 1d45d equals 12 minus 2 letter 1d45b 6 letter 1d45d equals 126 minus 2 letter 1d45b 6 letter 1d45d equals 2 minus 13 letter 1d45b. Subtract 2 letter 1d45b from both sides. Divide both sides by 6 and simplify. Therefore, p as a function of n is written as analysis. It is important to note that not every relationship expressed by an equation can also be expressed as a function with a formula. Example 10. Expressing the equation of a circle as a function. Does the equation letter 1d4652 plus letter 1d4662 equals 1 represent a function with letter 1d465 as input and letter 1d466 as output? If so, express the relationship as a function letter 1d466 equals letter 1d453, letter 1d465. Solution: first we subtract letter 1d465 from both sides. Letter 1d466 equals 1 minus letter 1d465. We now try to solve for letter 1d466. In this equation, letter 1d466 equals plus 1 minus letter 1d465 square equals plus 1 minus letter 1d465 square, and we get two outputs corresponding to the same input. So this relationship cannot be represented as a single function letter 1d466 equals letter 1d453, letter 1d465. Try it 6. If letter 1d465 minus 8 letter 1d466, 3 equals 0. Express letter 1d466 as a function of letter 1d465. Q&A. Are there relationships expressed by an equation that do represent a function, but which still cannot be represented by an algebraic formula? Yes, this can happen. For example, given the equation letter 1d465 equals letter 1d466 plus 2 letter 1d466, if we want to express letter 1d466 as a function of letter 1d465, there is no simple algebraic formula involving only letter 1d465. That equals letter 1d466. However, each letter 1d465 does determine a unique value for letter 1d466, and there are mathematical procedures by which letter 1d466 can be found to any desired accuracy. In this case, we say that the equation gives an implied rule for letter 1d466 as a function of letter 1d465, even though the formula cannot be written explicitly. Evaluating a function given in tabular form. As we saw above, we can represent functions in tables. Conversely, we can use information in tables to write functions, and we can evaluate functions using the tables. For example, how well do our pets recall the fond memories we share with them? There is an urban legend that a goldfish has a memory of 3 seconds, but this is just a myth. Goldfish can remember up to 3 months, while the betta fish has a memory of up to 5 months. And while a puppy's memory span is no longer than 30 seconds, the adult dog can remember for 5 minutes. This is meager compared to a cat, whose memory span lasts for 16 hours. The function that relates the type of pet to the duration of its memory span is more easily visualized with the use of a table. See Table 10. 2. Pet memory span in hours. Puppy 0, 8. Adult dog 0, 83. Cat 16. Goldfish 2,160. Betta fish 3,600. Table 10. At times, evaluating a function in table form may be more useful than using equations. Here let us call the function letter 1d443. The domain of the function is the type of pet, and the range is a real number representing the number of hours the pet's memory span lasts. We can evaluate the function letter 1d443 at the input value of goldfish. we would write letter 1D443, goldfish, equals 2,160. Notice that, to evaluate the function in table form, we identify the input value and the corresponding output value from the pertinent row of the table. The tabular form for function, letter 1D443, seems ideally suited to this function, more so than writing it in paragraph or function form. How to, given a function represented by a table, identify specific output and input values. Find the given input in the row or column of input values. Identify the corresponding output value paired with that input value. Find the given output values in the row or column of output values, noting every time that output value appears. Identify the input value, S, corresponding to the given output value. Example 11. Evaluating and solving a tabular function. Using Table 11, evaluate letter 1D454, 3. Solve letter 1D454, letter 1D45B equals 6. N, 1, 2, 3, 4, 5, letter 1D454, letter 1D45B, 8, 6, 7, 6, 8. Table 11. Solution. A. Evaluating letter 1D454, 3 means determining the output value of the function letter 1D454 for the input value of letter 1D45B equals 3. The table output value corresponding to letter 1D45B equals 3 is 7, so letter 1D454, 3 equals 7. B. Solving letter 1D454, letter 1D45B equals 6 means identifying the input values, letter 1D45B, that produce an output value of 6. The table below shows two solutions, 2 and 4, N, 1, 2, 3, 4, 5, letter 1D454, letter 1D45B, 8, 6, 7, 6, 8. When we input 2 into the function letter 1D454, our output is 6. When we input 4 into the function letter 1D454, our output is also 6. Try it 7. Using the table from evaluating and solving a tabular function above, evaluate letter 1D454. 1. Finding function values from a graph. Evaluating a function using a graph also requires finding the corresponding output value for a given input value. Only in this case, we find the output value by looking at the graph. Solving a function equation using a graph requires finding all instances of the given output value on the graph and observing the corresponding input value, S. Example 12. Reading function values from a graph. Given the graph in Figure 4, evaluate letter 1D453, 2. B. Solve letter 1D453, letter 1D465 equals 4. Graph of a positive parabola centered at 1, 0, Figure 4. Solution. A. To evaluate letter 1D453, 2. Locate the point on the curve where letter 1D465 equals 2. Then read the y-coordinate of that point. The point has coordinates 21, so letter 1D453, 2 equals 1. See Figure 5. Graph of a positive parabola centered at 1, 0 with the labeled point 2, 1 where f2 equals 1. Figure 5. B. To solve letter 1D453, letter 1D465 equals 4. We find the output value 4. On the vertical axis, moving horizontally, along the line letter 1D466 equals 4. We locate 2 points of the curve with output value 4, -1, 4, and 34. These points represent the two solutions to letter 1D453, letter 1D465 equals 4, -1, or 3. This means letter 1D453, -1 equals 4, and letter 1D453, 3 equals 4, or when the input is -1, or 3, the output is 4. See Figure 6. Graph of an upward-facing parabola with a vertex at 1 and labeled points at -1, 4, and 34. A line at y equals 4 intersects the parabola at the labeled points. Figure 6. Try at 8. Using Figure 4, solve letter 1D453, letter 1D465 equals 1. Determining whether a function is one-to-one. Some functions have a given output value that corresponds to 2 or more input values. For example, in the stock chart shown in the figure at the beginning of this chapter, the stock price was $1,000 on 5 different dates, meaning that there were 5 different input values that all resulted in the same output value of $1,000. However, some functions have only one input value for each output value, as well as having only one output for each input. We call these functions one-to-one functions. As an example, consider a school that uses only letter grades and decimal equivalents, as listed in Table 12. Letter grade point average. A4, 0. B3, 0. C2, 0. D1, 0. Table 12. This grading system represents a one-to-one function, because each letter input yields one particular grade point average output, and each grade point average corresponds to one input letter. To visualize this concept, let's look again at the two simple functions sketched in Figure 1a and Figure 1b. The function in part A shows a relationship that is not a one-to-one function because inputs letter 1d45e and letter 1d45f both give output letter 1d45b. The function in part B shows a relationship that is a one-to-one function because each input is associated with a single output. One-to-one function. A one-to-one function is a function in which each output value corresponds to exactly one input value. Example 13. Determining whether a relationship is a one-to-one function. Is the area of a circle a function of its radius? If yes, is the function one-to-one? Solution. A circle of radius letter 1d45f has a unique area measure, given by letter 1d434 equals letter 1d70b letter 1d45f2. So for any input, letter 1d45f, there is only one output, letter 1d434. The area is a function of radius letter 1d45f. If the function is one-to-one, the output value, the area, must correspond to a unique input value, the radius. Any area measure, letter 1d434, is given by the formula letter 1d434 equals letter 1d70b letter 1d45f2. Because areas and radii are positive numbers, there is exactly one solution. Letter 1d434 letter 1d70b square. So the area of a circle is a one-to-one function of the circle's radius. Try it 9. A is a balance, a function of the bank account number. B is a bank account number, a function of the balance. C is a balance, a one-to-one function of the bank account number. Try it 10. Evaluate the following. A, if each percent grade earned in a course translates to one letter grade, is the letter grade a function of the percent grade? B, if so, is the function one-to-one? Using the vertical line test, as we have seen in some examples above, we can represent a function using a graph. Graphs display a great many input-output pairs in a small space. The visual information they provide often makes relationships easier to understand. By convention, graphs are typically constructed with the input values along the horizontal axis and the output values along the vertical axis. The most common graphs name the input value letter 1d465 and the output value letter 1d466, and we say letter 1d466 is a function of letter 1d465, or letter 1d466 equals letter 1d453, letter 1d465, when the function is named letter 1d453. The graph of the function is the set of all points, xy, in the plane that satisfies the equation letter 1d466 equals letter 1d453, letter 1d465. If the function is defined for only a few input values, then the graph of the function is only a few points, where the x-coordinate of each point is an input value and the y-coordinate of each point is the corresponding output value. For example, the black dots on the graph in Figure 7 tell us that letter 1d453, 0, equals 2, and letter 1d453, 6 equals 1. However, the set of all points, xy, satisfying letter 1d466 equals letter 1d453, letter 1d465, is a curve. The curve shown includes 2 and 61, because the curve passes through those points. Graph of a polynomial, Figure 7. The vertical line test can be used to determine whether a graph represents a function. If we can draw any vertical line that intersects a graph more than once, then the graph does not define a function because a function has only one output value for each input value. See Figure 8. 3 graphs visually showing what is and is not a function. Figure 8. How to, given a graph, use the vertical line test to determine if the graph represents a function. Inspect the graph to see if any vertical line drawn would intersect the curve more than once. If there is any such line, determine that the graph does not represent a function. Example 14. Applying the vertical line test. Which of the graphs in Figure 9 represent S, A function letter 1d466 equals letter 1d453, letter 1d465. Graph of a polynomial. Figure 9. Solution. If any vertical line intersects a graph more than once, the relation represented by the graph is not a function. Notice that any vertical line would pass through only one point of the two graphs shown in parts A and B of Figure 9. From this, we can conclude that these two graphs represent functions. The third graph does not represent a function because, at most x values, a vertical line would intersect the graph at more than one point, as shown in Figure 10. Graph of a circle, Figure 10. Try at 11. Does the graph in Figure 11 represent a function? Graph of absolute value function. Figure 11. Using the horizontal line test. Once we have determined that a graph defines a function, an easy way to determine if it is a one-to-one function is to use the horizontal line test. Draw horizontal lines through the graph. If any horizontal line intersects the graph more than once, then the graph does not represent a one-to-one function. How to? Given a graph of a function, use the horizontal line test to determine if the graph represents a one-to-one function. Inspect the graph to see if any horizontal line drawn would intersect the curve more than once. If there is any such line, determine that the function is not one-to-one. Example 15. Applying the horizontal line test, consider the functions shown in Figure 9, a and Figure 9b. Are either of the functions one-to-one? Solution. The function in Figure 9, a, is not one-to-one. The horizontal line shown in Figure 12 intersects the graph of the function at 2 points, and we can even find horizontal lines that intersect it at 3 points. Figure 12. The function in Figure 9, b, is one-to-one. Any horizontal line will intersect a diagonal line at most once. Try at 12. Is the graph shown in Figure 9c one-to-one? Identifying basic toolkit functions. In this text, we will be exploring functions, the shapes of their graphs, their unique characteristics, their algebraic formulas, and how to solve problems with them. When learning to read, we start with the alphabet. When learning to do arithmetic, we start with numbers. When working with functions, it is similarly helpful to have a base set of building block elements. We call these our toolkit functions, which form a set of basic named functions for which we know the graph, formula, and special properties. Some of these functions are programmed to individual buttons on many calculators. For these definitions, we will use letter 1d465 as the input variable and letter 1d466 equals letter 1d453, letter 1d465. As the output variable, we will see these toolkit functions, combinations of toolkit functions, their graphs, and their transformations frequently throughout this book. It will be very helpful if we can recognize these toolkit functions and their features quickly by name, formula, graph, and basic table properties. The graphs and sample table values are included with each function shown in Table 13. Toolkit functions. Name function graph, constant letter 1d453. Letter 1d465 equals letter 1d450, where letter 1d450 is a constant graph of a constant function. Identity letter 1d453. Letter 1d465 equals letter 1d465. Graph of a straight line. Absolute value letter 1d453, letter 1d465 equals letter 1d465. Graph of absolute function. Quadratic letter 1d453, letter 1d465 equals letter 1d465 Graph of a parabola. Cubic letter 1d453, letter 1d465 equals letter 1d465 Graph of f, x equals x3. Reciprocal letter 1d453, letter 1d465 equals 1 letter 1d465. Graph of f, x equals 1/x. Reciprocal squared letter 1d453, letter 1d465 equals 1 letter 1d465 Graph of f, x equals 1/x2. Square root. Graph of f, x equals sqrt, x. Cube root letter 1d453, letter 1d465 equals letter 1d465 square 3. Graph of f, x equals x 1/3. Table 13. Media. Access the following online resources for additional instruction and practice with functions. Determine if a relation is a function. Vertical line test. Introduction to functions. Vertical line test on graph. One-to-one functions. Graphs as one-to-one functions. 3. 1 section exercises. Verbal. 1. What is the difference between a relation and a function? 2. What is the difference between the input and the output of a function? 3. Why does the vertical line test tell us whether the graph of a relation represents a function? 4. How can you determine if a relation is a one-to-one function? 5. Why does the horizontal line test tell us whether the graph of a function is one-to-one? Algebraic. For the following exercises, determine whether the relation represents a function. 6. Letter 1D44E, letter 1D44F, letter 1D450, letter 1D451, letter 1D44E, letter 1D450. 7. Letter 1D44E, letter 1D44F, letter 1D44F, letter 1D450, letter 1D450, letter 1D450. For the following exercises, determine whether the relation represents letter 1D466 as a function of letter 1D465. 8. 5 letter 1D465 plus 2 letter 1D466 equals 10. 9. Letter 1D466 equals letter 1D465 2. 10. Letter 1D465 equals letter 1D466 2. 11. 3 letter 1D465 2 plus letter 1D466 equals 14. 12. 2 letter 1D465 plus letter 1D466 2 equals 6. 13. Letter 1D466 equals minus 2 letter 1D465 2 plus 40 letter 1D465. 14. Letter 1D466 equals 1 letter 1D465. 15. Letter 1D465 equals 3 letter 1D466 plus 57 letter 1D466 minus 1. 16. Letter 1D465 equals 1 minus letter 1D466 2 square. 17. Letter 1D466 equals 3 letter 1D465 plus 57 letter 1D465 minus 1. 18. Letter 1D465 2 plus letter 1D466 2 equals 9. 19. 2 letter 1D465 letter 1D466 equals 1. 20. Letter 1D465 equals letter 1D466 3. 21. Letter 1D466 equals letter 1D465 3. 22. Letter 1D466 equals 1 minus letter 1D465 2 square. 23. Letter 1D465 equals plus 1 minus letter 1D466 square. 24. Letter 1D466 equals plus 1 minus letter 1D465 square. 25. Letter 1D466 2 equals letter 1D465 2. 26. Letter 1D466 3 equals letter 1D465 2. For the following exercises, evaluate letter 1D453, minus 3, letter 1D4532, letter 1D453, minus letter 1D44E, minus letter 1D453, letter 1D44E, letter 1D453, letter 1D44E, plus letter 210E. 27. Letter 1D453, letter 1D465 equals 2 letter 1D465 minus 5. 28. Letter 1D453, letter 1D465 equals minus 5 letter 1D465 2 plus 2 letter 1D465 minus 1. 29. Letter 1D453, letter 1D465 equals 2 minus letter 1D465 square plus 5. 30. Letter 1D453, letter 1D465 equals 6 letter 1D465 minus 15 letter 1D465 plus 2. 31. Letter 1D453, letter 1D465 equals letter 1D465 minus 1 minus letter 1D465 plus 1. 32. Given the function letter 1D454, letter 1D465 equals 5 minus letter 1D465 2. Evaluate letter 1D454, letter 1D465 plus letter 210E minus letter 1D454, letter 1D465, letter 210E, letter 210E not equal to 0. 33. Given the function letter 1D454, letter 1D465 equals letter 1D465 2 plus 2 letter 1D465. Evaluate letter 1D454, letter 1D465, minus letter 1D454, letter 1D44E, letter 1D465 minus letter 1D44E, letter 1D465 not equal to letter 1D44E. 34. Given the function letter 1D458, letter 1D461 equals 2 letter 1D461 minus 1, A. Evaluate letter 1D458, 2. B. Solve letter 1D458, letter 1D461 equals 7, 35. Given the function letter 1D453, letter 1D465 equals 8 minus 3 letter 1D465. Evaluate letter 1D453 minus 2. B. Solve letter 1D453, letter 1D465 equals minus 1, 36. Given the function letter 1D45D, letter 1D450 equals letter 1D450, 2 plus letter 1D450. Evaluate letter 1D45D minus 3. B. Solve 37. Given the function letter 1D453, letter 1D465 equals letter 1D465, 2 minus 3 letter 1D465. Evaluate letter 1D453, 5. B. Solve letter 1D453, letter 1D465 equals 4, 38. Given the function letter 1D453, letter 1D465 equals letter 1D465 plus 2 square. Evaluate letter 1D453, 7. B. Solve letter 1D453, letter 1D465 equals 4, 39. Consider the relationship 3 letter 1D45F plus 2 letter 1D461 equals 18. Write the relationship as a function letter 1D45F equals letter 1D453, letter 1D461. B. Evaluate letter 1D453 minus 3. C. Solve letter 1D453, letter 1D461 equals 2. Graphical. For the following exercises, use the vertical line test to determine which graphs show relations that are functions. 40. Graph of relation. 41. Graph of relation. 42. Graph of relation. 43. Graph of relation. 44. Graph of relation. 45. Graph of relation. 46. Graph of relation. 47. Graph of relation. 48. Graph of relation. 49. Graph of relation. 50. Graph of relation. 51. Graph of relation. 52. Given the following graph, evaluate letter 1D453, minus 1. B. Solve for letter 1D453, letter 1D465 equals 3. Graph of relation. 53. Given the following graph, evaluate letter 1D453, 0. B. Solve for letter 1D453, letter 1D465 equals minus 3. Graph of relation. 54. Given the following graph, evaluate letter 1D453, 4. B. Solve for letter 1D453, letter 1D465 equals 1. Graph of relation. For the following exercises, determine if the given graph is a one-to-one function. 55. Graph of a circle. 56. Graph of a parabola. 57. Graph of a rotated cubic function. 58. Graph of half of 1x. 59. Graph of a one-to-one function. Numeric. For the following exercises, determine whether the relation represents a function. 60, minus 1, minus 1, minus 2, minus 2, minus 3, minus 3. 61, 3, 4, 4, 5, 5, 6. 62, 2, 5, 7, 11, 15, 8, 7, 9. For the following exercises, determine if the relation represented in table form represents letter 1D466 as a function of letter 1D465. 63, x, 5, 10, 15. Y, 3, 8, 14. 64, x, 5, 10, 15. Y, 3, 8, 8. 65, x, 5, 10, 10. Y, 3, 8, 14. For the following exercises, use the function letter 1D453, represented in the table below. X, 1, 2, 3, 4, 5, 6, 7, 8, 9. Letter 1D453, letter 1D465. 74, 28, 153, 56. 336, 45, 14, 47. Table 14. 66. Evaluate letter 1D453, 3. 67. Solve letter 1D453, letter 1D465 equals 1. For the following exercises, evaluate the function letter 1D453. At the values letter 1D453, minus 2, letter 1D453, minus 1, letter 1D453, 0. Letter 1D453, 1. And letter 1D453, 2. 68. Letter 1D453, letter 1D465, equals 4 minus 2 letter 1D465. 69. Letter 1D453, letter 1D465, equals 8 minus 3 letter 1D465. 70. Letter 1D453. Letter 1D465 equals 8 letter 1D465, 2 minus 7 letter 1D465 plus 3. 71. Letter 1D453, letter 1D465 equals 3 plus letter 1D465 plus 3 square. 72. Letter 1D453, letter 1D465 equals letter 1D465 minus 2 letter 1D465 plus 3. 73. Letter 1D453, letter 1D465 equals 3 letter 1D465. For the following exercises, evaluate the expressions given functions letter 1D453, letter 1D454, and letter 210e. Letter 1D453, letter 1D465 equals 3 letter 1D465 minus 2. Letter 1D454, letter 1D465 equals 5 minus letter 1D465 2. Letter 210e. Letter 1D465 equals minus 2 letter 1D465 2 plus 3 letter 1D465 minus 1. 74. 3 letter 1D453, 1 minus 4 letter 1D454, minus 2. 75. Letter 1D453, 73 minus letter 210e, minus 2. Technology. For the following exercises, graph letter 1D466 equals letter 1D465 2. On the given domain, determine the corresponding range. Show each graph 76 minus 0, 10, 1. 77 minus 10, 10. 78 minus 100, 100. For the following exercises, graph letter 1D466 equals letter 1D465 3. On the given domain, determine the corresponding range. Show each graph 79 minus 0, 10, 1. 80 minus 10, 10. 81 minus 100, 100. For the following exercises, graph letter 1D466 equals letter 1D465 square. On the given domain, determine the corresponding range. Show each graph 82, 0, 0, 1. 83, 0, 100. 84, 0, 10, 0, 0, 0. For the following exercises, graph letter 1D466 equals letter 1D465 square 3. On the given domain, determine the corresponding range. Show each graph 85 minus 0, 10, 1. 86 minus 1000, 1000. 87 minus 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. Real-world applications. 88. The amount of garbage, letter 1D43a, produced by a city with population, letter 1D45d, is given by J, is measured in tons per week, and letter 1D45d is measured in thousands of people. The town of Tola has a population of 40,000 and produces 13 tons of garbage each week. Express this information in terms of the function letter 1D453. B. Explain the meaning of the statement letter 1D453, 5 equals 2. 89. The number of cubic yards of dirt, letter 1D437, needed to cover a garden, with area letter 1D440. Square feet is given by A garden with area 5,000 ft2 requires 50 yd3 of dirt. Express this information in terms of the function letter 1D454. B. Explain the meaning of the statement letter 1D454, 100 equals 1. 90. Let letter 1D453, letter 1D461, be the number of ducks in a lake letter 1D461. Years after 1990. Explain the meaning of each statement. A. Letter 1D453, 5 equals 30. B. Letter 1D453, 10 equals 40. 91. Let letter 210e, letter 1D461, be the height above ground, in feet, of a rocket letter 1D461. Seconds after launching. Explain the meaning of each statement. A. Letter 210e, 1 equals 200. B. 92. Show that the function letter 1D453, letter 1D465 equals 3, letter 1D465 minus 5, 2 plus 7, is underline notend underline 1-to-1. Learning objectives. In this section, you will find the domain of a function defined by an equation. Graph piecewise defined functions. Horror and thriller movies are both popular and, very often, extremely profitable. When big-budget actors, shooting locations, and special effects are included, however, studios count on even more viewership to be successful. Consider 5 major thriller horror entries from the early 2000s: I Am Legend, Hannibal, The Ring, The Grudge, and The Conjuring. Figure 1 shows the amount, in dollars, each of those movies grossed when they were released, as well as the ticket sales for horror movies in general by year. Notice that we can use the data to create a function of the amount each movie earned or the total ticket sales for all horror movies by year. In creating various functions using the data, we can identify different independent and dependent variables, and we can analyze the data and the functions to determine the domain and range. In this section, we will investigate methods for determining the domain and range of functions, such as these. Two graphs where the first graph is of the top 5 grossing horror movies for years 2000-2003 and market share of horror movies by year. Figure 1, based on data compiled by www. The numbers, com3, finding the domain of a function, defined by an equation. In functions and function notation, we were introduced to the concepts of domain and range. In this section, we will practice determining domains and ranges for specific functions. Keep in mind that, in determining domains and ranges, we need to consider what is physically possible or meaningful in real-world examples, such as ticket sales and year in the horror movie example above. We also need to consider what is mathematically permitted. For example, we cannot include any input value that leads us to take an even root of a negative number if the domain and range consist of real numbers. Or in a function expressed as a formula, we cannot include any input value in the domain that would lead us to divide by 0. We can visualize the domain as a holding area that contains raw materials for a function machine and the range as another holding area for the machine's products. See Figure 2, diagram of how a function relates to relations. Figure 2. We can write the domain and range in interval notation, which uses values within brackets to describe a set of numbers. In interval notation, we use a square bracket, when the set includes the endpoint and a parenthesis, to indicate that the endpoint is either not included or the interval is unbounded. For example, if a person has $100 to spend, they would need to express the interval that is more than 0 and less than or equal to 100 and write 100. We will discuss interval notation in greater detail later. Let's turn our attention to finding the domain of a function whose equation is provided. Oftentimes, finding the domain of such functions involves remembering 3 different forms. First, if the function has no denominator or an odd root, consider whether the domain could be all real numbers. Second, if there is a denominator in the function's equation, exclude values in the domain that force the denominator to be 0. Third, if there is an even root, consider excluding values that would make the radicand negative. Before we begin, let us review the conventions of interval notation. The smallest number from the interval is written first. The largest number in the interval is written second, following a comma. Parentheses, or, are used to signify that an endpoint value is not included, called exclusive. Brackets, or, are used to indicate that an endpoint value is included, called inclusive. See Figure 3 for a summary of interval notation. Summary of interval notation. Figure 3. Example 1. Finding the domain of a function as a set of ordered pairs. Find the domain of the following function: 210, 310, 420, 530, 640. Solution. First, identify the input values. The input value is the first coordinate in an ordered pair. There are no restrictions, as the ordered pairs are simply listed. The domain is the set of the first coordinates of the ordered pairs, 23,456. Try it 1. Find the domain of the function, -5, 4, 0, 0, 5, -4, 10, -8, 15, -12. How to? Given a function written in equation form, find the domain. Identify the input values. Identify any restrictions on the input and exclude those values from the domain. Write the domain in interval form if possible. Example 2. Finding the domain of a function. Find the domain of the function letter 1d453, letter 1d465, equals letter 1d465 2-1. Solution. The input value, shown by the variable x, in the equation, is squared and then the result is lowered by 1. Any real number may be squared and then be lowered by 1, so there are no restrictions on the domain of this function. The domain is the set of real numbers. In interval form, the domain of f is minus infinity, infinity. Try it too. Find the domain of the function. Letter 1d453, letter 1d465 equals 5 minus letter 1d465 plus letter 1d4653. How to? Given a function written in an equation form that includes a fraction, find the domain. Identify the input values. Identify any restrictions on the input. If there is a denominator in the function's formula, set the denominator equal to 0 and solve for x. If the function's formula contains an even root, set the radicand greater than or equal to 0, and then solve. Write the domain in interval form, making sure to exclude any restricted values from the domain. Example 3. Finding the domain of a function involving a denominator. Find the domain of the function letter 1d453, letter 1d465, equals letter 1d465 plus 12 minus letter 1d465. Solution. When there is a denominator, we want to include only values of the input that do not force the denominator to be 0. So, we will set the denominator equal to 0 and solve for x. 2 minus letter 1d465 minus letter 1d465 letter 1d465 equals 0 minus 22. Now, we will exclude 2 from the domain. The answers are all real numbers, where letter 1d465 2, or letter 1d465 2. As shown in Figure 4, we can use a symbol known as the union to combine the two sets. In interval notation, we write the solution, minus infinity to infinity, line graph of x, to Figure 4. Try it 3. Find the domain of the function. Letter 1d453, letter 1d465, equals 1 plus 4 letter 1d465 to letter 1d465 minus 1. How to? Given a function written in equation form including an even root, find the domain. Identify the input values. Since there is an even root, exclude any real numbers that result in a negative number in the radicand. Set the radicand greater than or equal to 0 and solve for x. The solution, s, are the domain of the function. If possible, write the answer in interval form. Example 4. Finding the domain of a function with an even root. Find the domain of the function letter 1d453, letter 1d465, equals 7 minus letter 1d465 square. Solution. When there is an even root in the formula, we exclude any real numbers that result in a negative number in the radicand. Set the radicand greater than or equal to 0 and solve for x. 7 minus letter 1d465 minus letter 1d465 letter 1d465 greater less 0 minus 77. Now, we will exclude any number greater than 7 from the domain. The answers are all real numbers less than or equal to 7, or minus infinity 7. Try it 4. Find the domain of the function letter 1d453, letter 1d465, equals 5 plus 2 letter 1d465 square. Q&A. Can there be functions in which the domain and range do not intersect at all? Yes. For example, the function letter 1d453, letter 1d465, equals minus 1 letter 1d465 square root, has the set of all positive real numbers as its domain, but the set of all negative real numbers as its range. As a more extreme example, a function's inputs and outputs can be completely different categories. For example, names of weekdays as inputs and numbers as outputs, as on an attendance chart. In such cases, the domain and range have no elements in common. Using notations to specify domain and range. In the previous examples, we used inequalities and lists to describe the domain of functions. We can also use inequalities or other statements that might define sets of values or data to describe the behavior of the variable in set builder notation. For example, letter 1d465 10 less or equal to letter 1d465 30 describes the behavior of x. In set builder notation, the braces are read as the set of, and the vertical bar is read as such that. So we would read letter 1d465 10 less or equal to letter 1d465 30 as the set of x values such that 10 is less than or equal to x, and x is less than 30. Figure 5 compares inequality notation, set builder notation, and interval notation. Summary of notations for inequalities, set builder, and intervals. Figure 5. To combine two intervals using inequality notation or set builder notation, we use the word or. As we saw in earlier examples, we use the union symbol to combine two unconnected intervals. For example, the union of the sets 235 and 46 is the set 23,456. It is the set of all elements that belong to one or the other, or both, of the original two sets. For sets with a finite number of elements like these, the elements do not have to be listed in ascending order of numerical value. If the original two sets have some elements in common, those elements should be listed only once in the union set. For sets of real numbers on intervals, another example of a union is letter 1d465, letter 1d465 greater 3 equals minus infinity, minus 33, infinity. Set builder notation and interval notation. Set builder notation is a method of specifying a set of elements that satisfy a certain condition. It takes the form letter 1d465 statement about x, which is read as the set of all x, such that the statement about x is true. For example, letter 1d465 for letter 1d465 less or equal to 12. Interval notation is a way of describing sets that include all real numbers between a lower limit that may or may not be included and an upper limit that may or may not be included. The endpoint values are listed between brackets or parentheses. A square bracket indicates inclusion in the set, and a parenthesis indicates exclusion from the set. For example, 412's how to, given a line graph, describe the set of values using interval notation. Identify the intervals to be included in the set by determining where the heavy line overlays the real line. At the left end of each interval, use with each end value to be included in the set solid dot, or for each excluded end value open dot. At the right end of each interval, use with each end value to be included in the set filled dot, or for each excluded end value open dot. Use the union symbol to combine all intervals into one set. Example 5. Describing sets on the real number line. Describe the intervals of values shown in Figure 6 using inequality notation, set builder notation, and interval notation. Line graph of 1 lesser equal x lesser equal 3 and 5x. Figure 6. Solution. To describe the values x included in the intervals shown, we would say x is a real number greater than or equal to 1 and less than or equal to 3, or a real number greater than 5. Inequality 1 less or equal to letter 1d465, less or equal to 30r letter 1d465 5. Set builder notation. Letter 1d465 1 less or equal to letter 1d465, less or equal to 30r letter 1d465 5. Interval notation 1, 3, 5 infinity. Remember that, when writing or reading interval notation, using a square bracket means the boundary is included in the set. Using a parenthesis means the boundary is not included in the set. Try at 5. Given Figure 7, specify the graphed set in A. Words, B. Set builder notation, C. Interval notation. Line graph of -2 lesser equal x, -1 lesser equal x3. Figure 7. Finding domain and range from graphs. Another way to identify the domain and range of functions is by using graphs. Because the domain refers to the set of possible input values, the domain of a graph consists of all the input values shown on the x-axis. The range is the set of possible output values, which are shown on the y-axis. Keep in mind that if the graph continues beyond the portion of the graph we can see, the domain and range may be greater than the visible values. See Figure 8. Graph of a polynomial that shows the x-axis is the domain and the y-axis is the range. Figure 8. We can observe that the graph extends horizontally from -5 to the right without bound, so the domain is -5 infinity. The vertical extent of the graph is all range values 5, and below, so the range is -infinity, 5. Note that the domain and range are always written from smaller to larger values, or from left to right for domain, and from the bottom of the graph to the top of the graph for range. Example 6. Finding domain and range from a graph. Find the domain and range of the function f, whose graph is shown in Figure 9. Graph of a function from -3, 1. Figure 9. Solution. We can observe that the horizontal extent of the graph is 3 to 1, so the domain of f is -3, 1. The vertical extent of the graph is 0 to 4, so the range is -4, 0. See Figure 10. Graph of the previous function shows the domain and range. Figure 10. Example 7. Finding domain and range from a graph of oil production. Find the domain and range of the function f, whose graph is shown in Figure 11. Graph of the Alaska crude oil production, where the y-axis is 1,000 barrels per day and the axis is the years. Figure 11, credit, modification of work by the U.S. Energy Information Administration 4. Solution. The input quantity along the horizontal axis is years, which we represent with the variable t. For time, the output quantity is thousands of barrels of oil per day, which we represent with the variable b. For barrels, the graph may continue to the left and right beyond what is viewed, but based on the portion of the graph that is visible, we can determine the domain as 1973 less or equal to letter 1D461 less or equal to 2008, and the range as approximately 180 less or equal to letter 1D44F less or equal to 2010. In interval notation, the domain is 1973, 2008, and the range is about 180, 2010. For the domain and the range, we approximate the smallest and largest values since they do not fall exactly on the grid lines. Try it 6. Given Figure 12, identify the domain and range using interval notation. Graph of world population increase where the y-axis represents millions of people and the x-axis represents the year. Figure 12, Q&A. Can a function's domain and range be the same? Yes. For example, the domain and range of the cube root function are both the set of all real numbers. Finding domains and ranges of the toolkit functions. We will now return to our set of toolkit functions to determine the domain and range of each. Constant function f x equals c. Figure 13, for the constant function letter 1D453. Letter 1D465 equals letter 1D450. The domain consists of all real numbers. There are no restrictions on the input. The only output value is the constant c, so the range is the set c. That contains this single element. In interval notation, this is written as letter 1D450, letter 1D450. The interval that both begins and ends with c. Identity function f x equals x. Figure 14 for the identity function letter 1D453, letter 1D465 equals letter 1D465. There is no restriction on x. Both the domain and range are the set of all real numbers. Absolute function f x equals x. Figure 15 for the absolute value function letter 1D453, letter 1D465 equals letter 1D465. There is no restriction on letter 1D465. However, because absolute value is defined as a distance from 0, the output can only be greater than or equal to 0. Quadratic function f x equals x2. Figure 16 for the quadratic function letter 1D453. Letter 1D465 equals letter 1D465 The domain is all real numbers, since the horizontal extent of the graph is the whole real number line. Because the graph does not include any negative values for the range is only non-negative real numbers. Cubic function f x x3. Figure 17 for the cubic function letter 1D453, letter 1D465 equals letter 1D465 The domain is all real numbers, because the horizontal extent of the graph is the whole real number line. The same applies to the vertical extent of the graph, so the domain and range include all real numbers. Reciprocal function f x equals 1/x. Figure 18 for the reciprocal function letter 1D453, letter 1D465 equals 1 letter 1D465. We cannot divide by 0, so we must exclude 0 from the domain. Further, 1 divided by any value can never be 0, so the range also will not include 0. In set builder notation, we could also write letter 1D465, letter 1D465 not equal to 0. The set of all real numbers that are not 0. Reciprocal squared function f x equals 1/x2. Figure 19 for the reciprocal squared function letter 1D453. Letter 1D465 equals 1 letter 1D465 We cannot divide by 0, so we must exclude 0. From the domain, there is also no letter 1D465. That can give an output of 0, so 0 is excluded from the range as well. Note that the output of this function is always positive due to the square in the denominator, so the range includes only positive numbers. Square root function f x equals sqrt x. Figure 20 for the square root function. We cannot take the square root of a negative real number, so the domain must be 0 or greater. The range also excludes negative numbers, because the square root of a positive number letter 1d465 is defined to be positive, even though the square of the negative number minus letter 1d465 square also gives us letter 1d465. Cube root function f x equals x 1/3. Figure 21 for the cube root function letter 1d453, letter 1d465 equals letter 1d465 square 3. The domain and range include all real numbers. Note that there is no problem taking a cube root or any odd integer root of a negative number, and the resulting output is negative. It is an odd function. How to? Given the formula for a function, determine the domain and range. Exclude from the domain any input values that result in division by 0. Exclude from the domain any input values that have non-real or undefined number outputs. Use the valid input values to determine the range of the output values. Look at the function graph and table values to confirm the actual function behavior. Example 8. Finding the domain and range using toolkit functions. Find the domain and range of letter 1d453, letter 1d465, equals 2 letter 1d465, 3 minus letter 1d465. Solution. There are no restrictions on the domain, as any real number may be cubed and then subtracted from the result. The domain is minus infinity, infinity, and the range is also minus infinity, infinity. Example 9. Finding the domain and range. Find the domain and range of letter 1d453, letter 1d465, equals 2 letter 1d465 plus 1. Solution. We cannot evaluate the function at -1, because division by 0 is undefined. The domain is minus infinity, -1, -1, infinity. Because the function is never 0, we exclude 0 from the range. The range is minus infinity 0, 0, infinity. Example 10. Finding the domain and range. Find the domain and range of letter 1d453, letter 1d465, equals 2 letter 1d465 plus 4 square. Solution. We cannot take the square root of a negative number, so the value inside the radical must be non-negative. Letter 1d465 plus 4 greater or equal to 0 when letter 1d465 greater minus 4. The domain of letter 1d453, letter 1d465, is minus 4 infinity. We then find the range. We know that letter 1d453 minus 4 equals 0, and the function value increases as letter 1d465 increases without any upper limit. We conclude that the range of letter 1d453 is 0, infinity. Analysis. Figure 22 represents the function letter 1d453. Graph of a square root function at -4, 0. Figure 22. Try it 7. Find the domain and range of letter 1d453, letter 1d465, equals -2 minus letter 1d465 square. Graphing piecewise defined functions. Sometimes, we come across a function that requires more than one formula in order to obtain the given output. For example, in the toolkit functions, we introduced the absolute value function letter 1d453, letter 1d465 equals letter 1d465. With a domain of all real numbers and a range of values greater than or equal to 0, absolute value can be defined as the magnitude, or modulus, of a real number value regardless of sign. It is the distance from 0 on the number line. All of these definitions require the output to be greater than or equal to 0. If we input 0, or a positive value, the output is the same as the input. Letter 1d453. Letter 1d465 equals letter 1d465, if letter 1d465 greater or equal to 0. If we input a negative value, the output is the opposite of the input. Letter 1d453, letter 1d465, equals minus letter 1d465, if letter 1d465 0. Because this requires two different processes or pieces, the absolute value function is an example of a piecewise function. A piecewise function is a function in which more than one formula is used to define the output over different pieces of the domain. We use piecewise functions to describe situations in which a rule or relationship changes as the input value crosses certain boundaries. For example, we often encounter situations in business for which the cost per piece of a certain item is discounted once the number ordered exceeds a certain value. Tax brackets are another real-world example of piecewise functions. For example, consider a simple tax system in which incomes up to $10,000 are taxed at 10% and any additional income is taxed at 20%. The tax on a total income letter 1D446 would be 0, 1s, if letter 1D446 less $10,000 and 1,000 plus 0, 2 letter 1D446 minus $10,000, if letter 1D446 $10,000. Piecewise function. A piecewise function is a function in which more than one formula is used to define the output. Each formula has its own domain, and the domain of the function is the union of all these smaller domains. We notate this idea like this. Letter 1D453. Letter 1D465 equals formula 1 if size in domain 1 formula 2, if size in domain 2 formula 3, if size in domain 3. In piecewise notation, the absolute value function is letter 1D465 equals letter 1D465 if letter 1D465 greater or equal to 0 minus letter 1D465 if letter 1D465 0. How to? Given a piecewise function, write the formula and identify the domain for each interval. Identify the intervals for which different rules apply. Determine formulas that describe how to calculate an output from an input in each interval. Use braces and if statements to write the function. Example 11. Writing a piecewise function. A museum charges $5 per person for a guided tour with a group of 1 to 9 people, or a fixed $50 fee for a group of 10 or more people. Write a function relating the number of people, letter 1D45b, to the cost, letter 1D436. Solution. 2 different formulas will be needed. For n values under 10, letter 1D436 equals 5 letter 1D45b. For values of letter 1D45b that are 10 or greater, letter 1D436 equals 50. Letter 1D436, letter 1D45b, equals 5 letter 1D45b 50 if 0 letter 1D45b 10 letter 1D45b greater or equal to 10. Analysis. The function is represented in figure 23. The graph is a diagonal line from letter 1D45b equals 0 to letter 1D45b equals 10, and a constant after that. In this example, the two formulas agree at the meeting point where letter 1D45b equals 10, but not all piecewise functions have this property. Graph of Cn, figure 23. Example 12. Working with a piecewise function. A cell phone company uses the function below to determine the cost, letter 1D436, in dollars for letter 1D454, gigabytes of data transfer, letter 1D436. Letter 1D454 equals 2,525 plus 10, letter 1D454 minus 2, if 0, letter 1D454, 2 letter 1D454 greater or equal to 2. Find the cost of using 5 gigabytes of data and the cost of using 4 gigabytes of data. Solution. To find the cost of using 5 gigabytes of data, letter 1D436. 5. We first look to see which part of the domain our input falls in. Because 5 is less than 2, we use the first formula. 5 equals $25. To find the cost of using 4 gigabytes of data, letter 1D436. 4. We see that our input of 4 is greater than 2, so we use the second formula. Letter 1D436. 4 equals 25 plus 10, 4 minus 2 equals $45. Analysis. The function is represented in figure 24. We can see where the function changes from a constant to a shifted and stretched identity at letter 1D454 equals 2. We plot the graphs for the different formulas on a common set of axes, making sure each formula is applied on its proper domain. Graph of C.G. Figure 24. How to. Given a piecewise function, sketch a graph. Indicate on the x-axis the boundaries defined by the intervals on each piece of the domain. For each piece of the domain, graph on that interval using the corresponding equation pertaining to that piece. Do not graph two functions over one interval because it would violate the criteria of a function. Example 13. Graphing a piecewise function. Sketch a graph of the function letter 1d453, letter 1d465, equals letter 1d465, 23 letter 1d465, if, letter 1d465, less or equal to 11 letter 1d465, less or equal to 2 letter 1d465 2. Solution. Each of the component functions is from our library of toolkit functions, so we know their shapes. We can imagine graphing each function and then limiting the graph to the indicated domain. At the endpoints of the domain, we draw open circles to indicate where the endpoint is not included because of a less than or greater than inequality. We draw a closed circle where the endpoint is included because of a less than or equal to or greater than or equal to inequality. Figure 25 shows the three components of the piecewise function graphed on separate coordinate systems. Graph of each part of the piecewise function fx. Figure 25, a, letter 1d453, letter 1d465, equals letter 1d465 to if letter 1d465 less or equal to 1. B, letter 1d453, letter 1d465, equals 3 if 1 letter 1d465 less or equal to 2. C, letter 1d453, letter 1d465 equals letter 1d465 if letter 1d465 2. Now that we have sketched each piece individually, we combine them in the same coordinate plane. See Figure 26, graph of the entire function, Figure 26, analysis. Note that the graph does pass the vertical line test even at letter 1d465 equals 1, and letter 1d465 equals 2. Because the points 13 and 22 are not part of the graph of the function, though 11 and 23 are. Try at 8. Graph the following piecewise function. Letter 1d453, letter 1d465, equals letter 1d465, 3 minus 2 letter 1d465 square. If, letter 1d465 minus 1, letter 1d465, 4 letter 1d465 4. Q&A. Can more than one formula from a piecewise function be applied to value in the domain? No, each value corresponds to one equation in a piecewise formula. Media. Access these online resources for additional instruction and practice with domain and range. Domain and range of square root functions. Determining domain and range. Find domain and range given the graph. Find domain and range given a table. Find domain and range given points on a coordinate plane. 3. Two-section exercises. Verbal. 1. Why does the domain differ for different functions? 2. How do we determine the domain of a function defined by an equation? 3. Explain why the domain of letter 1d453, letter 1d465, equals letter 1d465 square 3, is different from the domain of letter 1d453, letter 1d465, equals letter 1d465 square. 4. When describing sets of numbers using interval notation, when do you use a parenthesis, and when do you use a bracket? 5. How do you graph a piecewise function? Algebraic. For the following exercises, find the domain of each function using interval notation. 6. Letter 1d453, letter 1d465, equals minus 2 letter 1d465, letter 1d465 minus 1, letter 1d465 minus 2. 7. Letter 1d453, letter 1d465, equals 5 minus 2 letter 1d465 2. 8. Letter 1d453, letter 1d465, equals 3 letter 1d465 minus 2 square. 9. Letter 1d453, letter 1d465, equals 3 minus 6 minus 2 letter 1d465 square. 10. Letter 1d453, letter 1d465, equals 4 minus 3 letter 1d465 square. 11. Letter 1d453, letter 1d465, equals letter 1d465 2 plus 4 square. 12. Letter 1d453, letter 1d465, equals 1 minus 2 letter 1d465 square 3. 13. Letter 1d453, letter 1d465, equals letter 1d465 minus 1 square 3. 14. Letter 1d453, letter 1d465, equals 9 letter 1d465 minus 6. 15. Letter 1d453, letter 1d465, equals 3 letter 1d465 plus 14 letter 1d465 plus 2. 16, letter 1d453, letter 1d465, equals letter 1d465 plus 4 square root letter 1d465 minus 4. 17, letter 1d453, letter 1d465, equals letter 1d465 minus 3 letter 1d465, 2, plus 9 letter 1d465 minus 22. 18, 19, letter 1d453, letter 1d465, equals 2 letter 1d465, 3 minus 250, letter 1d465, 2 minus 2 letter 1d465 minus 15. 20, letter 1d453, letter 1d465, equals 5 letter 1d465 minus 3 square root. 21, letter 1d453, letter 1d465, equals 2 letter 1d465 plus 15 minus letter 1d465 square root. 22, letter 1d453, letter 1d465, equals letter 1d465 minus 4 square root letter 1d465 minus 6 square root. 23, letter 1d453, letter 1d465, equals letter 1d465 minus 6 square root letter 1d465 minus 4 square root. 24, letter 1d453, letter 1d465 equals letter 1d465 letter 1d465. 25, letter 1d453, letter 1d465, equals letter 1d465 2 minus 9, letter 1d465 letter 1d465, 2 minus 81. 26, find the domain of the function letter 1d453, letter 1d465, equals 2 letter 1d465, 3 minus 50, letter 1d465 square. By A. Using algebra. B. Graphing the function in the radicand and determining intervals on the x-axis for which the radicand is non-negative. Graphic. For the following exercises, write the domain and range of each function using interval notation. 27. Graph of a function from 2, 8, 28. Graph of a function from 4, 8, 29. Graph of a function from minus 4, 4, 30. Graph of a function from 2, 6, 31. Graph of a function from minus 5, 3, 32. Graph of a function from minus 3, 2, 33. Graph of a function from infinity 2, 34. Graph of a function from minus 4, infinity, 35. Graph of a function from minus 6, minus 1 slash 6u1 slash 6, 6 slash, 36. Graph of a function from minus 2, 5, infinity, 37. Graph of a function from minus 3, infinity. For the following exercises, sketch a graph of the piecewise function. Write the domain in interval notation. 38. Letter 1d453, letter 1d465, equals letter 1d465 plus 1 minus 2 letter 1d465 minus 3 if letter 1d465 minus 2 letter 1d465 greater minus 2. 39. Letter 1d453, letter 1d465, equals to letter 1d465 minus 11 plus letter 1d465, if letter 1d465, 1 letter 1d465 greater or equal to 1. 40. Letter 1d453, letter 1d465, equals letter 1d465 plus 1 if letter 1d465 0, letter 1d465 minus 1 if letter 1d465 0. 41. Letter 1d453, letter 1d465, equals 3 letter 1d465 square, if letter 1d465 0, letter 1d465 greater or equal to 0. 42. Letter 1d453, letter 1d465, equals letter 1d465 2, if letter 1d465 0, 1 minus letter 1d465, if letter 1d465 0. 43. Letter 1d453, letter 1d465, equals letter 1d465 to letter 1d465, plus 2 if letter 1d465 0, if letter 1d465 greater or equal to 0. 44. Letter 1d453, letter 1d465, equals letter 1d465 plus 1 letter 1d465 3 if letter 1d465, 1 letter 1d465 greater or equal to 1. 45. Letter 1d453, letter 1d465, equals letter 1 d465 1 if letter 1 d465 2 if letter 1 d465 greater or equal to 2. Numeric. For the following exercises, given each function f, evaluate letter 1 d453 minus 3, letter 1 d453 minus 2, letter 1 d453 minus 1, and letter 1 d453 0. 46. Letter 1 d453, letter 1 d465 equals letter 1 d465 plus 1 minus 2 letter 1 d465 minus 3 if letter 1 d465 minus 2 letter 1 d465 greater minus 2. 47. Letter 1 d453, letter 1 d465 equals 10 if letter 1 d465 less minus 3 if letter 1 d465 minus 3. 48. Letter 1 d453, letter 1 d465 equals minus 2 letter 1 d465 2 plus 35 letter 1 d465 minus 7 if letter 1 d465 less minus 1 if letter 1 d465 minus 1. For the following exercises, given each function f, evaluate letter 1 d453 minus 1, letter 1 d453 0, letter 1 d453 2, and letter 1 d453 4. 49. Letter 1 d453, letter 1 d465 equals 7 letter 1 d465 plus 37 letter 1 d465 plus 6 if letter 1 d465 0 letter 1 d465 greater or equal to 0. 50. Letter 1 d453, letter 1 d465 equals letter 1 d465 2 minus 24 plus letter 1 d465 minus 5 if letter 1 d465 2 letter 1 d465 greater or equal to 2. 51. Letter 1 d453, letter 1 d465 equals 5 letter 1 d465 3 letter 1 d465 die if letter 1 d465 0 0 less or equal to letter 1 d465 less or equal to 3 letter 1 d465 3. For the following exercises, write the domain for the piecewise function in interval notation. 52. Letter 1 d453, letter 1 d465 equals letter 1 d465 plus 1 if letter 1 d465 minus 2 letter 1 d465 minus 3 if letter 1 d465 greater minus 2. 53. Letter 1 d453, letter 1 d465 equals letter 1 d465 2 minus 2 if letter 1 d465 1 minus letter 1 d465 2 plus 2 if letter 1 d465 1. 54. Letter 1 d453, letter 1 d465 equals 2 letter 1 d465 minus 3 letter 1 d465 die f letter 1 d465 0 if letter 1 d465 greater or equal to 2. Technology. 55. Graph letter 1 d466 equals 1 letter 1 d465 2. On the viewing window minus 0, 5 minus 0, 1, and 0, 10, 5, determine the corresponding range for the viewing window. Show the graphs. 56. Graph letter 1 d466 equals 1 letter 1 d465. On the viewing window minus 0, 5 minus 0, 1, and 0, 10, 5, determine the corresponding range for the viewing window. Show the graphs. Extension. 57. Suppose the range of a function f is minus 5, 8. What is the range of letter 1 d453, letter 1 d465? 58. Create a function in which the range is all non-negative real numbers. 59. Create a function in which the domain is letter 1 d465 2. Real-world applications. 60. The height h of a projectile is a function of the time t. It is in the air. The height in feet for t. Seconds is given by the function letter 210e. Letter 1 d461 equals minus 16 letter 1 d461 2 plus 96 letter 1 d461. What is the domain of the function? What does the domain mean in the context of the problem? 61. The cost in dollars of making x items is given by the function letter 1 d436. Letter 1 d465 equals 10 letter 1 d465 plus 500. The fixed cost is determined when 0 items are produced. Find the fixed cost for this item. B. What is the cost of making 25 items? C. Suppose the maximum cost allowed is $1,500. What are the domain and range of the cost function, letter 1d436, letter 1d465. Learning objectives in this section, you will find the average rate of change of a function. Use a graph to determine where a function is increasing, decreasing, or constant. Use a graph to locate local maxima and local minima. Use a graph to locate the absolute maximum and absolute minimum. Gasoline costs have experienced some wild fluctuations over the last several decades. Table 15 lists the average cost, in dollars, of a gallon of gasoline for the years 2005-2012. The cost of gasoline can be considered as a function of year. Why 2005, 2006, 2007, 2008, 2009, 2010, 2011, 2012, letter 1d436, letter 1d466, 2, 31 2, 62 2, 84 3 32, 41 2, 84 3, 58 3. 68 Table 1, if we were interested only in how the gasoline prices changed between 2005 and 2012, we could compute that the cost per gallon had increased from $2.31 to $3.68, an increase of $1. $37. While this is interesting, it might be more useful to look at how much the price changed per year. In this section, we will investigate changes such as these. Finding the average rate of change of a function, the price change per year is a rate of change because it describes how an output quantity changes relative to the change in the input quantity. We can see that the price of gasoline in Table 1 did not change by the same amount each year, so the rate of change was not constant. If we use only the beginning and ending data, we would be finding the average rate of change over the specified period of time. To find the average rate of change, we divide the change in the output value by the change in the input value. Average rate of change equals change in output change in input letter 1d65 letter 1d466 letter 1d65 letter 1d465 letter 1d466 2 minus letter 1d466 1 letter 1d465 2 minus letter 1d465 1 letter 1d453 letter 1d465 2 minus letter 1d453 letter 1d465 1 letter 1d465 2 minus letter 1d465 1. The Greek letter delta signifies the change in a quantity. We read the ratio as delta y over delta x, or the change in y divided by the change in x. Occasionally, we write delta letter 1d453 instead of delta letter 1d466, which still represents the change in the function's output value resulting from a change to its input value. It does not mean we are changing the function into some other function. In our example, the gasoline price increased by $137 from 2005 to 2012. Over 7 years, the average rate of change was delta letter 1d466, delta letter 1d465 equals $1. 377 years, approximately 0. $196 per year on average, the price of gas increased by about 19.6 cents each year. Other examples of rates of change include a population of rats increasing by 40 rats per week, a car traveling 68 miles per hour. Distance traveled changes by 68 miles each hour as time passes. A car driving 27 miles per gallon. Distance traveled changes by 27 miles for each gallon. The current through an electrical circuit increasing by 125 amperes for every volt of increased voltage. The amount of money in a college account decreasing by $4,000 per quarter rate of change. A rate of change describes how an output quantity changes relative to the change in the input quantity. The units on a rate of change are output units per input units. The average rate of change between two input values is the total change of the function values, output values, divided by the change in the input values. Letter 1d65 letter 1d466, letter 1d65 letter 1d465 equals letter 1d453. Letter 1d465 2 minus letter 1d453, letter 1d465 1 letter 1d465 2 minus letter 1d465 1. How to given the value of a function at different points. Calculate the average rate of change of a function for the interval between two values x1 and x2. Calculate the difference letter 1d466 2 minus letter 1d466 1 equals delta letter 1d466. Calculate the difference letter 1d465 2 minus letter 1 d465, 1 equals delta letter 1 d465. Find the ratio delta, letter 1 d466 delta, letter 1 d465. Example 1, computing an average rate of change, using the data in Table 1, find the average rate of change of the price of gasoline between 2007 and 2009. Analysis, note that a decrease is expressed by a negative change or negative increase. A rate of change is negative when the output decreases as the input increases, or when the output increases as the input decreases. Try it 1 using the data in Table 1. Find the average rate of change between 2005 and 2010. Example 2, computing average rate of change from a graph given the function letter 1 d454, letter 1 d461, shown in Figure 1. Find the average rate of change on the interval -1, 2. Graph of a parabola. Figure 1 solution at letter 1 d461 equals -1. Figure 2 shows letter 1 d454, -1 equals 4. At letter 1 d461 equals 2, the graph shows letter 1 d454, 2 equals 1. Graph of a parabola with a line from points -1, 4, and 2, 1 to show the changes for g, t, and t. Figure 2, the horizontal change is shown by the red arrow, and the vertical change delta letter 1 d454, letter 1 d461 equals -3 is shown by the turquoise arrow. The average rate of change is shown by the slope of the orange line segment. The output changes by 3, while the input changes by 3, giving an average rate of change of 1 minus 42 minus -1 equals -33 equals -1. Analysis, note that the order we choose is very important. If, for example, we use letter 1 d466, 2 minus letter 1 d466, 1 letter 1 d465, 1 minus letter 1 d465, 2, we will not get the correct answer. Decide which point will be 1 and which point will be 2, and keep the coordinates fixed as x1, y1 and x2, y2. Example 3, computing average rate of change from a table after picking up a friend who lives 10 miles away and leaving on a trip. Anna records her distance from home over time. The values are shown in Table 2. Find her average speed over the first 6 hours. T, hours, 0, 1, 2, 3, 4, 5, 6, 7 d, t. Miles, 10, 55, 90, 153, 214, 240, 292, 300. Table 2 solution here. The average speed is the average rate of change. She traveled 282 miles in 6 hours. 292 minus 106 minus 0 equals 282,647. The average speed is 47 miles per hour. Analysis, because the speed is not constant, the average speed depends on the interval chosen. For the interval 2, 3, the average speed is 63 miles per hour. Example 4, computing average rate of change. For a function expressed as a formula compute, the average rate of change of letter 1 d453, letter 1 d465, equals letter 1 d465, 2 minus 1 letter 1 d465 on the interval 2, 4. Solution, we can start by computing the function values at each endpoint of the interval. Letter 1 d453, 2 equals 22 minus 124 minus 1,272, letter 1 d453. 4 equals 42 minus 1,416 minus 14,634. Now, we compute the average rate of change. Average rate of change equals letter 1 d453, 4 minus letter 1 d453. 2, 4 minus 2,630, 4 minus 724, minus 24,940,2,498. Try it 2. Find the average rate of change of letter 1 d453. Letter 1 d465 equals letter 1 d465 minus 2 letter 1 d465 square on the interval 1. 9. Example 5, finding the average rate of change of a force, the electrostatic force F, measured in newtons, between two charged particles can be related to the distance between the particles d in centimeters by the formula letter 1 d439, letter 1 d451, equals 2 letter 1 d4512. Find the average rate of change of force if the distance between the particles is increased from 2 cm to 6 cm. Solution, we are computing the average rate of change of letter 1D439, letter 1D451, equals 2 letter 1D4512 on the interval 2, 6. Average rate of change equals letter 1D439, 6, minus letter 1D439, 2, 6 minus 2,262, minus 2,226, minus 2,236, minus 244, minus 16,364, minus 19. Simplify. Combine numerator terms. Simplify the average rate of change is minus 19 Newton per centimeter. Example 6, finding an average rate of change. As an expression, find the average rate of change of letter 1D454. Letter 1D461 equals letter 1D461 2 plus 3 letter 1D461 plus 1 on the interval 0, letter 1D440. The answer will be an expression involving A in simplest form. Solution, we use the average rate of change formula. Average rate of change equals letter 1D454, letter 1D440, minus letter 1D454 letter 1D440 minus 0, letter 1D440 2, plus 3 letter 1D440 plus 1 minus 0 2 plus 3 0 plus 1, letter 1D440 minus 0, letter 1D440 2, plus 3 letter 1D440, plus 1 minus 1 letter 1D440 letter 1D440, letter 1D440, plus 3 letter 1D440 let. Simplify. Simplify and factor. Divide by the common factor, A. This result tells us the average rate of change in terms of A between letter 1D461 equals 0 and any other point letter 1D461 equals letter 1D440. For example, on the interval 0, 5, the average rate of change would be 5 plus 3 equals 8. Try at 3, find the average rate of change of letter 1D453, letter 1D465, equals letter 1D465 2 plus 2 letter 1D465 minus 8 on the interval 5, letter 1D440 in simplest forms in terms of A. Using a graph to determine where a function is increasing, decreasing, or constant as part of exploring how functions change. We can identify intervals over which the function is changing in specific ways. We say that a function is increasing on an interval if the function values increase as the input values increase within that interval. Similarly, a function is decreasing on an interval if the function values decrease as the input values increase over that interval. The average rate of change of an increasing function is positive, and the average rate of change of a decreasing function is negative. Figure 3 shows examples of increasing and decreasing intervals on a function. Graph of a polynomial that shows the increasing and decreasing intervals and local maximum and minimum. Figure 3, the function letter 1D453, letter 1D465, equals letter 1D465 3 minus 12 letter 1D465 is increasing on minus infinity, minus 2, 2 infinity, and is decreasing on minus 2, 2. While some functions are increasing or decreasing over their entire domain, many others are not. A value of the input where a function changes from increasing to decreasing as we go from left to right, that is, as the input variable increases, is the location of a local maximum. The function value at that point is the local maximum. If a function has more than one, we say it has local maxima. Similarly, a value of the input where a function changes from decreasing to increasing as the input variable increases is the location of a local minimum. The function value at that point is the local minimum. The plural form is local minima. Together, local maxima and minima are called local extrema or local extreme values of the function. The singular form is extremum. Often, the term local is replaced by the term relative. In this text, we will use the term local. Clearly, a function is neither increasing nor decreasing on an interval where it is constant. A function is also neither increasing nor decreasing at extrema. Note that we have to speak of local extrema, because any given local extremum as defined here is not necessarily the highest maximum or lowest minimum in the function's entire domain. For the function whose graph is shown in Figure 4, the local maximum is 16, and it occurs at letter 1D465 equals minus 2. The local minimum is minus 16, and it occurs at letter 1D465 equals 2. A graph is shown on a set of x and y axes. The scale is -5 to +5 for x and -20 to 20 for y. The graph rises from below in the third quadrant, crossing the x-axis between -3 and -4, has a turning point at -2, 16, crosses the x-axis again at the origin, has another turning point at 2, -16, and crosses the x-axis one last time between 3 and 4, rising from there. The turning points are labeled local maximum and local minimum, respectively. The curve is labeled increasing or decreasing as appropriate. Figure 4, to locate the local maxima and minima from a graph, we need to observe the graph to determine where the graph attains its highest and lowest points, respectively, within an open interval. Like the summit of a roller coaster, the graph of a function is higher at a local maximum than at nearby points on both sides. The graph will also be lower at a local minimum than at neighboring points. Figure 5 illustrates these ideas for a local maximum. Graph of a polynomial that shows the increasing and decreasing intervals and local maximum. Figure 5 definition of a local maximum. These observations lead us to a formal definition of local extrema. Local minima and local maxima. A function f is an increasing function on an open interval if letter 1 d453, letter 1 d44f, letter 1 d453, letter 1 d44e, for any two input values a and b in the given interval where letter 1 d44f, letter 1 d44e. A function f is a decreasing function on an open interval if letter 1 d453, letter 1 d44f, letter 1 d453, letter 1 d44e, for any two input values a and b in the given interval where letter 1 d44f, letter 1 d44e. A function f has a local maximum at letter 1 d465 equals letter 1 d44f if there exists an interval a. C with letter 1 d44e, letter 1 d44f, letter 1 d450, such that, for any x in the interval a, c, letter 1 d453, letter 1 d465 less or equal to letter 1 d453, letter 1 d44f. Likewise, f has a local minimum at letter 1 d465 equals letter 1 d44f if there exists an interval a. C with letter 1 d44e, letter 1 d44f, letter 1 d450, such that, for any x in the interval a, c, letter 1 d453, letter 1 d465 greater or equal to letter 1 d453, letter 1 d44f. Example 7, finding increasing and decreasing intervals on a graph given the function letter 1 d45d, letter 1 d461, in figure 6. Identify the intervals on which the function appears to be increasing. Graph of a polynomial. Figure 6 solution, we see that the function is not constant on any interval. The function is increasing where it slants upward as we move to the right and decreasing where it slants downward as we move to the right. The function appears to be increasing from letter 1 d461 equals 1 to letter 1 d461 equals 3, and from letter 1 d461 equals 4 on. In interval notation, we would say the function appears to be increasing on the interval 13 and the interval 4 infinity. Analysis. Notice in this example that we used open intervals, intervals that do not include the endpoints, because the function is neither increasing nor decreasing at letter 1 d461 equals 1, letter 1 d461 equals 3, and letter 1 d461 equals 4. These points are the local extrema, two minima, and a maximum. Example 8, finding local extrema from a graph. The function letter 1 d453, letter 1 d465 equals 2 letter 1 d465 plus letter 1 d465 3. Then use the graph to estimate the local extrema of the function and to determine the intervals on which the function is increasing. Solution. Using technology, we find that the graph of the function looks like that in figure 7. It appears there is a low point, or local minimum, between letter 1 d465 equals 2 and letter 1 d465 equals 3, and a mirror image high point, or local maximum, somewhere between letter 1 d465 equals -3 and letter 1 d465 equals -2. Graph of a reciprocal function. Figure 7 analysis. Most graphing calculators and graphing utilities can estimate the location of maxima and minima. Figure 8 provides screen images from two different technologies, showing the estimate for the local maximum and minimum. Graph of the reciprocal function on a graphing calculator. Figure 8. Based on these estimates, the function is increasing on the interval -infinity, -2, 449, and 2, 449, infinity. Notice that, while we expect the extrema to be symmetric, the two different technologies agree only up to 4 decimals due to the differing approximation algorithms used by each. The exact location of the extrema is at plus or -6 square, but determining this requires calculus. Try it for graph the function letter 1 d453, letter 1 d465, equals letter 1 d465 3 minus 6 letter 1 d465 2 minus 15 letter 1 d465 plus 20 to estimate the local extrema of the function. Use these to determine the intervals on which the function is increasing and decreasing. Example 9. Finding local maxima and minima from a graph for the function f whose graph is shown in Figure 9. Find all local maxima and minima. Graph of a polynomial. Figure 9. Analyzing the toolkit functions for increasing or decreasing intervals, we will now return to our toolkit functions and discuss their graphical behavior in Figure 10, Figure 11, and Figure 12. Table showing the increasing and decreasing intervals of the toolkit functions. Figure 10. Table showing the increasing and decreasing intervals of the toolkit functions. Figure 11. Table showing the increasing and decreasing intervals of the toolkit functions. Figure 12. Use a graph to locate the absolute maximum and absolute minimum. There is a difference between locating the highest and lowest points on a graph in a region around an open interval locally, and locating the highest and lowest points on the graph for the entire domain. The y-coordinates, output, at the highest and lowest points are called the absolute maximum and absolute minimum, respectively. To locate absolute maxima and minima from a graph, we need to observe the graph to determine where the graph attains its highest and lowest points on the domain of the function. See Figure 13. Graph of a segment of a parabola with an absolute minimum at 0, -2, and absolute maximum at 2, 2. Figure 13. Not every function has an absolute maximum or minimum value. The toolkit function letter 1 d453, letter 1 d465, equals letter 1 d4653 is one such function. Absolute maxima and minima. The absolute maximum of f at letter 1 d465 equals letter 1 d450 is letter 1 d453. Letter 1 d450, where letter 1 d453, letter 1 d450, greater or equal to letter 1 d453, letter 1 d465, for all x in the domain of f. The absolute minimum of f at letter 1 d465 equals letter 1 d451 is letter 1 d453, letter 1 d451, where letter 1 d453, letter 1 d451, less or equal to letter 1 d453, letter 1 d465, for all x in the domain of f. Example 10. Finding absolute maxima and minima from a graph for the function f shown in Figure 14. Find all absolute maxima and minima. Graph of a polynomial. Figure 14 solution. Observe the graph of f. The graph attains an absolute maximum in 2 locations. Letter 1 d465 equals -2 and letter 1 d465 equals 2. Because at these locations, the graph attains its highest point on the domain of the function. The absolute maximum is the y-coordinate at letter 1 d465 equals -2 and letter 1 d465 equals 2, which is 16. The graph attains an absolute minimum at letter 1 d465 equals 3, because it is the lowest point on the domain of the function's graph. The absolute minimum is the y-coordinate at letter 1 d465 equals 3, which is -10. Media access this online resource for additional instruction and practice with rates of change. Average rate of change 3. 3-section exercises verbal 1. Can the average rate of change of a function be constant? 2. If a function f is increasing on AB and decreasing on BC, then what can be said about the local extremum of f on AC? 3. How are the absolute maximum and minimum similar to and different from the local extrema? 4. How does the graph of the absolute value function compare to the graph of the quadratic function, letter 1 d466 equals letter 1 d4652, in terms of increasing and decreasing intervals? Algebraic for the following exercises, Find the average rate of change of each function on the interval specified for real numbers b or h in simplest form. 5. Letter 1d453, letter 1d465, equals 4 letter 1d465 2 minus 7 on 1, letter 1d44f. 6. Letter 1d454, letter 1d465, equals 2 letter 1d465 2 minus 9 on 4, letter 1d44f. 7. Letter 1d45d, letter 1d465, equals 3 letter 1d465 plus 4 on 2 2 plus letter 210e. 8. Letter 1d458, letter 1d465 equals 4 letter 1d465 minus 2 on 3 3 plus letter 210e. 9. Letter 1d453, letter 1d465, equals 2 letter 1d465 2 plus 1 on letter 1d465, letter 1d465 plus letter 210e. 10. Letter 1d454, letter 1d465, equals 3 letter 1d465 2 minus 2 on xx plus h. 11. Letter 1d440, letter 1d461 equals 1 letter 1d461 plus 4 on 9, 9 plus letter 210e. 12. Letter 1d44f, letter 1d465 equals 1 letter 1d465 plus 3 on 1, 1 plus letter 210e. 13. Letter 1d457, letter 1d465, equals 3 letter 1d465 3 on 1, 1 plus letter 210e. 14. Letter 1d45f, letter 1d461, equals 4 letter 1d461 3 on 2, 2 plus letter 210e. 15. Find letter 1d453, letter 1d465 plus letter 210e minus letter 1d453. Letter 1d465, letter 210e given letter 1d453, letter 1d465 equals 2 letter 1d465 2 minus 3 letter 1d465 on letter 1d465. X plus h, graphical for the following exercises. Consider the graph of f shown in Figure 15. Graph of a polynomial. Figure 15:16. Estimate the average rate of change from letter 1d465 equals 1 to letter 1d465 equals 4. 17. Estimate the average rate of change from letter 1d465 equals 2 to letter 1d465 equals 5. For the following exercises, use the graph of each function to estimate the intervals on which the function is increasing or decreasing. 18. Graph of an absolute function. 19. Graph of a cubic function. 20. Graph of a cubic function. 21. Graph of a reciprocal function. For the following exercises, consider the graph shown in Figure 16. Graph of a cubic function. Figure 16:22. Estimate the intervals where the function is increasing or decreasing. 23. Estimate the point, S, at which the graph of f has a local maximum or a local minimum. For the following exercises, consider the graph in Figure 17. Graph of a cubic function. Figure 17:24. If the complete graph of the function is shown, estimate the intervals where the function is increasing or decreasing. 25. If the complete graph of the function is shown, estimate the absolute maximum and absolute minimum. Numeric 26. Table 3 gives the annual sales, in millions of dollars, of a product from 1998 to 2006. What was the average rate of change of annual sales? A. Between 2001 and 2002, and B. Between 2001 and 2004. Year sales, millions of dollars. 1998, 201, 1999, 219, 2,233, 2001, 243, 2002, 249, 2003, 251, 2004, 249, 2005, 243, 2006, 233. Table 327. Table 4 gives the population of a town in thousands from 2000 to 2008. What was the average rate of change of population? A. Between 2002 and 2004, and B. Between 2002 and 2006. Year population, thousands. 2087, 2001, 84, 2002, 83, 2003, 80, 2004, 77, 2005, 76, 2006, 78, 2007, 81, 2008, 85. Table 4 for the following exercises. Find the average rate of change of each function on the interval specified. 28. Letter 1d453, letter 1d465 equals letter 1d4652 on 1, 5, 29. Letter 210e, letter 1d465 equals 5 minus 2 letter 1d4652 on minus 2, 430. Letter 1d45e, letter 1d465 equals letter 1d4653 on minus 4, 2, 31. Letter 1d454, letter 1d465 equals 3 letter 1d465 3 minus 1 on minus 3, 332. Letter 1d466 equals 1 letter 1d465 on 1, 333. Letter 1d45d, letter 1d461 equals letter 1d461 2 minus 4. Letter 1d461 plus 1, letter 1d461 2 plus 3 on minus 3, 1, 34. Letter 1d458, letter 1d461 equals 6 letter 1d461 2 plus 4 letter 1d461 3 on minus 1, 3. Technology for the following exercises. Use a graphing utility to estimate the local extrema of each function and to estimate the intervals on which the function is increasing and decreasing. 35. Letter 1d453, letter 1d465 equals letter 1d465 4 minus 4 letter 1d465 3 plus 536. Letter 210e. Letter 1d465 equals letter 1d465 5 plus 5 letter 1d465 4 plus 10 letter 1d465 3 plus 10 letter 1d465 2 minus 137. Letter 1d454. Letter 1d461 equals letter 1d461 letter 1d461 plus 3 square 38. Letter 1d458, letter 1d461 equals 3 letter 1d461 23 minus letter 1d461 39. Letter 1d45a, letter 1d465 equals letter 1d465 4 plus 2 letter 1d465 3 minus 12 letter 1d465 2 minus 10 letter 1d465 plus 440. Letter 1d45b. Letter 1d465 equals letter 1d465 4 minus 8 letter 1d465 3 plus 18 letter 1d465 2 minus 6 letter 1d465 plus 2 extension 41. The graph of the function f is shown in Figure 18. Graph of f, x on a graphing calculator. Figure 18 based on the calculator screenshot, the point 13,335. 185 is which of the following? A. Relative local. Maximum of the function b, the vertex of the function c, the absolute maximum of the function to 0, of the function 42. Let letter 1d453, letter 1d465 equals 1 letter 1d465. Find a number c such that the average rate of change of the function f on the interval 1c is minus 14. 43. Let letter 1d453, letter 1d465 equals 1 letter 1d465. Find the number b such that the average rate of change of f on the interval 2b is minus 110. Real-world applications 44. At the start of a trip, the odometer on a car read 21,395. At the end of the trip, 13. 5 hours later, the odometer read 22,125. Assume the scale on the odometer is in miles. What is the average speed the car traveled during this trip? 45. A driver of a car stopped at a gas station to fill up their gas tank. They looked at their watch, and the time read exactly 3:40 p.m. At this time, they started pumping gas into the tank. At exactly 3:44, the tank was full, and the driver noticed that they had pumped 7 gallons. What is the average rate of flow of the gasoline into the gas tank? 46. Near the surface of the moon, the distance that an object falls is a function of time. It is given by letter 1d451, letter 1d461 equals 2. 6667 t2, where t is in seconds and letter 1d451, letter 1d461 is in feet. If an object is dropped from a certain height, find the average velocity of the object from letter 1d461 equals 1 to letter 1d461 equals 2. 47. The graph in Figure 19 illustrates the decay of a radioactive substance over t days. Graph of an exponential function. Figure 19, use the graph to estimate the average decay rate from letter 1D461 equals 5 to letter 1D461 equals 15. Learning objectives in this section, you will combine functions using algebraic operations, create a new function by composition of functions, evaluate composite functions, find the domain of a composite function, decompose a composite function into its component functions. Suppose we want to calculate how much it costs to heat a house on a particular day of the year. The cost to heat a house will depend on the average daily temperature, and in turn, the average daily temperature depends on the particular day of the year. Notice how we have just defined two relationships. The cost depends on the temperature, and the temperature depends on the day. Using descriptive variables, we can notate these two functions. The function letter 1D436, letter 1D447, gives the cost C of heating a house for a given average daily temperature in T degrees Celsius. The function letter 1D447, letter 1D451, gives the average daily temperature on day D of the year. For any given day, cost equals letter 1D436, letter 1D447, letter 1D451, means that the cost depends on the temperature, which in turn depends on the day of the year. Thus, we can evaluate the cost function at the temperature letter 1D447, letter 1D451. For example, we could evaluate letter 1D447, 5, to determine the average daily temperature on the 5th day of the year. Then we could evaluate the cost function at that temperature. We would write letter 1D436, letter 1D447, 5. Explanation of CT5, which is the cost for the temperature, and T5 is the temperature on day 5. By combining these two relationships into one function, we have performed function composition, which is the focus of this section. Combining functions using algebraic operations function composition is only one way to combine existing functions. Another way is to carry out the usual algebraic operations on functions, such as addition, subtraction, multiplication, and division. We do this by performing the operations with the function outputs, defining the result as the output of our new function. Suppose we need to add two columns of numbers that represent a husband and wife's separate annual incomes over a period of years, with the result being their total household income. We want to do this for every year, adding only that year's incomes and then collecting all the data in a new column. If letter 1D464, letter 1D466, is the wife's income and letter 210E, letter 1D466 is the husband's income in year Y, and we want T to represent the total income, then we can define a new function. Letter 1D447, letter 1D466 equals letter 210E, letter 1D466, plus letter 1D464, letter 1D466, if this holds true for every year. Then we can focus on the relation between the functions without reference to a year and write letter 1D447 equals letter 210E plus letter 1D464, just as for this sum of two functions. We can define difference, product, and ratio functions for any pair of functions that have the same kinds of inputs, not necessarily numbers, and also the same kinds of outputs, which do have to be numbers so that the usual operations of algebra can apply to them, and which also must have the same units or no units when we add and subtract. In this way, we can think of adding, subtracting, multiplying, and dividing functions. For two functions, letter 1D453, letter 1D465, and letter 1D454, letter 1D465, with real number outputs, we define new functions f plus g, letter 1D453 minus letter 1D454, letter 1D453, letter 1D454, and letter 1D453, letter 1D454 by the relations letter 1D453 plus letter 1D454, letter 1D465, letter 1D453 minus letter 1D454, letter 1D465, letter 1D453, letter 1D454, letter 1D465, letter 1D453, letter 1D454, letter 1D465 equals, letter 1D453, letter 1D465 plus, letter 1D454, letter 1D465, letter 1D453, letter 1D465, minus, letter 1D454, letter 1D465, letter 1D453, letter 1D465, letter 1D454, letter 1D465. Example 1, performing algebraic operations on functions. Find and simplify the functions. Letter 1 D454 minus letter 1 D453. Letter 1 D465, and letter 1 D454, letter 1 D453. Letter 1 D465. Given letter 1 D453, letter 1 D465 equals letter 1 D465 minus 1 and letter 1 D454. Letter 1 D465 equals letter 1 D465 2 minus 1. Are they the same function? Try it. 1. Find and simplify the functions. Letter 1 D453, letter 1 D454. Letter 1 D465, and letter 1 D453 minus letter 1 D454. Letter 1 D465. Letter 1 D453. Letter 1 D465 equals letter 1 D465 minus 1 and letter 1 D454. Letter 1 D465 equals letter 1 D465 2 minus 1. Are they the same function? Create a function by composition of functions. Performing algebraic operations on functions combines them into a new function. But we can also create functions by composing functions. When we wanted to compute a heating cost from a day of the year, we created a new function that takes a day as input and yields a cost as output. The process of combining functions so that the output of one function becomes the input of another is known as a composition of functions. The resulting function is known as a composite function. We represent this combination by the following notation. Letter 1 D453, letter 1 D454. Letter 1 D465 equals letter 1 D453, letter 1 D454, letter 1 D465. We read the left-hand side as f composed with g at x, and the right-hand side as f of g of x. The two sides of the equation have the same mathematical meaning and are equal. The open circle symbol is called the composition operator. We use this operator mainly when we wish to emphasize the relationship between the functions themselves without referring to any particular input value. Composition is a binary operation that takes two functions and forms a new function, much as addition or multiplication takes two numbers and gives a new number. However, it is important not to confuse function composition with multiplication because, as we learned above, in most cases letter 1 D453, letter 1 D454, letter 1 D465, not equal to letter 1 D453, letter 1 D465, letter 1 D454, letter 1 D465. It is also important to understand the order of operations in evaluating a composite function. We follow the usual convention with parentheses by starting with the innermost parentheses first, and then working to the outside. In the equation above, the function g takes the input x first and yields an output letter 1 D454, letter 1 D465. Then the function f takes letter 1 D454, letter 1 D465, as an input and yields an output letter 1 D453, letter 1 D454, letter 1 D465. Explanation of the composite function. In general, letter 1 D453, letter 1 D454, and letter 1 D454, letter 1 D453 are different functions. In other words, in many cases letter 1 D453, letter 1 D454, letter 1 D465, not equal to letter 1 D454, letter 1 D453, letter 1 D465 for all x. We will also see that sometimes two functions can be composed only in one specific order. For example, if letter 1 D453, letter 1 D465 equals letter 1 D465 2 and letter 1 D454. Letter 1 D465 equals letter 1 D465 plus 2. Then letter 1 D453, letter 1 D454, letter 1 D465 equals letter 1 D453, letter 1 D465 plus 2. Letter 1 D465 plus 2 2 letter 1 D465 2 plus 4 letter 1 D465 plus 4 but letter 1 D454, letter 1 D453, letter 1 D465 equals letter 1 D454, letter 1 D465 2 letter 1 D465 2 plus 2. These expressions are not equal for all values of x, so the two functions are not equal. It is irrelevant that the expressions happen to be equal for the single input value letter 1 D465 equals minus 12. Note that the range of the inside function, the first function to be evaluated, needs to be within the domain of the outside function. Less formally, The composition has to make sense in terms of inputs and outputs. Composition of functions: when the output of one function is used as the input of another, we call the entire operation a composition of functions. For any input x in functions f and g, this action defines a composite function, which we write as letter 1 d453 letter 1 d454, such that letter 1 d453 letter 1 d454. Letter 1 d465 equals letter 1 d453, letter 1 d454, letter 1 d465. The domain of the composite function letter 1 d453 letter 1 d454 is all x such that x is in the domain of g, and letter 1 d454, letter 1 d465, is in the domain of f. It is important to realize that the product of functions letter 1 d453 letter 1 d454 is not the same as the function composition letter 1 d453, letter 1 d454, letter 1 d465, because, in general, letter 1 d453, letter 1 d465, letter 1 d454, letter 1 d465 not equal to letter 1 d453, letter 1 d454, letter 1 d465. Example 2, determining whether composition of functions is commutative using the functions provided. Find letter 1 d453, letter 1 d454, letter 1 d465, and letter 1 d454, letter 1 d453, letter 1 d465. Determine whether the composition of the functions is commutative. Letter 1 d453, letter 1 d465 equals 2 letter 1 d465 plus 1 letter 1 d454. Letter 1 d465 equals 3 minus letter 1 d465. Solution: let's begin by substituting letter 1 d454, letter 1 d465, into letter 1 d453, letter 1 d465. Letter 1 d453, letter 1 d454, letter 1 d465 equals 2, 3 minus letter 1 d465, plus 16 minus 2 letter 1 d465, plus 17 minus 2 letter 1 d465. Now we can substitute letter 1 d453, letter 1 d465, into letter 1 d454, letter 1 d465. Letter 1 d454, letter 1 d453, letter 1 d465 equals 3 minus 2 letter 1 d465 plus 1 3 minus 2 letter 1 d465 minus 1 minus 2 letter 1 d465 plus 2. We find that letter 1 d454, letter 1 d453, letter 1 d465 not equal to letter 1 d453, letter 1 d454, letter 1 d465. So the operation of function composition is not commutative. Example 3, interpreting composite functions: the function letter 1 d450, letter 1 d460 gives the number of calories burned completing S sit-ups, and letter 1 d460, letter 1 d461 gives the number of sit-ups a person can complete in T minutes. Interpret letter 1 d450, letter 1 d460, 3. Solution: the inside expression in the composition is letter 1 d460, 3. Because the input to the S function is time, letter 1 d461 equals 3 represents 3 minutes, and letter 1 d460, 3, is the number of sit-ups completed in 3 minutes. Using letter 1 d460, 3, as the input to the function letter 1 d450, letter 1 d460, gives us the number of calories burned during the number of sit-ups that can be completed in 3 minutes, or simply the number of calories burned in 3 minutes by doing sit-ups. Example 4, investigating the order of function composition. Suppose letter 1 d453, letter 1 d465 gives miles that can be driven in X hours, and letter 1 d454, letter 1 d466 gives the gallons of gas used in driving Y miles. Which of these expressions is meaningful? Letter 1 d453, letter 1 d454, letter 1 d466, or letter 1 d454, letter 1 d453, letter 1 d465. Solution: the function letter 1 d466 equals letter 1 d453, letter 1 d465, is a function whose output is the number of miles driven corresponding to the number of hours driven. Number of miles equals letter 1 d453. Number of hours: the function letter 1 d454, letter 1 d466, is a function whose output is the number of gallons used corresponding to the number of miles driven. This means number of gallons equals letter 1 d454. Number of miles, the expression letter 1 d454, letter 1d466, takes miles as the input and a number of gallons as the output. The function letter 1d453, letter 1d465, requires a number of hours as the input. Trying to input a number of gallons does not make sense. The expression letter 1d453, letter 1d454, letter 1d466 is meaningless. The expression letter 1d453, letter 1d465 takes hours as input and a number of miles driven as the output. The function letter 1d454, letter 1d466 requires a number of miles as the input. Using letter 1d453, letter 1d465, miles driven as an input value for letter 1d454, letter 1d466, where gallons of gas depends on miles driven, does make sense. The expression letter 1d454, letter 1d453, letter 1d465 makes sense and will yield the number of gallons of gas used, G, driving a certain number of miles, letter 1d453, letter 1d465, in X hours. Q and A, are there any situations where letter 1d453, letter 1d454, letter 1d466, and letter 1d454, letter 1d453, letter 1d465 would both be meaningful or useful expressions? Yes, for many pure mathematical functions, both compositions make sense, even though they usually produce different new functions. In real-world problems, functions whose inputs and outputs have the same units also may give compositions that are meaningful in either order. Try it too. The gravitational force on a planet, a distance r from the Sun, is given by the function letter 1d43a, letter 1d45f. The acceleration of a planet subjected to any force F is given by the function letter 1d44e, letter 1d439. Form a meaningful composition of these two functions and explain what it means. Evaluating composite functions. Once we compose a new function from two existing functions, we need to be able to evaluate it for any input in its domain. We will do this with specific numerical inputs for functions expressed as tables, graphs, and formulas, and with variables as inputs to functions expressed as formulas. In each case, we evaluate the inner function using the starting input, and then use the inner function's output as the input for the outer function. Evaluating composite functions using tables. When working with functions given as tables, we read input and output values from the table entries and always work from the inside to the outside. We evaluate the inside function first, and then use the output of the inside function as the input to the outside function. Example 5. Using a table to evaluate a composite function. Using table 1, evaluate letter 1d453, letter 1d454, 3, and letter 1d454, letter 1d453, 3. X letter 1d453, letter 1d465, letter 1d454, letter 1d465, 163285332417. Table 1. Try it. 3. Using table 1, evaluate letter 1d453, letter 1d454, 1, and letter 1d454, letter 1d4534. Evaluating composite functions using graphs. When we are given individual functions as graphs, the procedure for evaluating composite functions is similar to the process we use for evaluating tables. We read the input and output values, but this time from the x and y axes of the graphs. How to given a composite function and graphs of its individual functions, evaluate it using the information provided by the graphs. Locate the given input to the inner function on the x-axis of its graph. Read off the output of the inner function from the y-axis of its graph. Locate the inner function output on the x-axis of the graph of the outer function. Read the output of the outer function from the y-axis of its graph. This is the output of the composite function. Example 6. Using a graph to evaluate a composite function. Using figure 1, evaluate letter 1d453, letter 1d454, 1. Explanation of the composite function. Figure 1 solution to evaluate letter 1d453, letter 1d454, 1. We start with the inside evaluation. See figure 2. Two graphs of a positive parabola, gx, and a negative parabola, fx. The following points are plotted. g1 equals 3 and f3 equals 6. Figure 2, we evaluate letter 1D454. 1. Using the graph of letter 1D454, letter 1D465, finding the input of 1 on the x-axis, and finding the output value of the graph at that input. Here, letter 1D454, 1 equals 3. We use this value as the input to the function f. Letter 1D453, letter 1D454, 1 equals letter 1D453, 3. We can then evaluate the composite function by looking to the graph of letter 1D453, letter 1D465, finding the input of 3 on the x-axis, and reading the output value of the graph at this input. Here, letter 1D453, 3 equals 6, so letter 1D453, letter 1D454, 1 equals 6. Analysis figure 3 shows how we can mark the graphs with arrows to trace the path from the input value to the output value. 2 graphs of a positive and negative parabola. Figure 3, try it 4 using figure 1, evaluate letter 1D454, letter 1D453, 2. Evaluating composite functions, using formulas when evaluating a composite function, where we have either created or been given formulas. The rule of working from the inside out remains the same. The input value to the outer function will be the output of the inner function, which may be a numerical value, a variable name, or a more complicated expression. While we can compose the functions for each individual input value, it is sometimes helpful to find a single formula that will calculate the result of a composition letter 1D453, letter 1D454, letter 1D465. To do this, we will extend our idea of function evaluation. Recall that, when we evaluate a function like letter 1D453, letter 1D461 equals letter 1D461 2 minus letter 1D461, we substitute the value inside the parentheses into the formula wherever we see the input variable. How to given a formula for a composite function, evaluate the function. Evaluate the inside function using the input value or variable provided. Use the resulting output as the input to the outside function. Example 7, evaluating a composition of functions expressed as formulas with a numerical input given letter 1D453, letter 1D461, equals letter 1D461 2 minus letter 1D461 and letter 210e, letter 1D465, equals 3 letter 1D465 plus 2. Evaluate letter 1D453, letter 210e. 1. Solution because the inside expression is letter 210e. 1. We start by evaluating letter 210e, letter 1D465 at 1. Letter 210e, 1, letter 210e, 1 equals 3, 1, plus 25 then letter 1D453, letter 210e, 1, equals letter 1D453, 5. So we evaluate letter 1D453, letter 1D461 at an input of 5. Letter 1D453, letter 210e, 1, letter 1D453, letter 210e, 1, letter 1D453, letter 210e, 1, equals letter 1D453, 5, 52 minus 520 analysis, it makes no difference what the input variables t and x were called in this problem, because we evaluated for specific numerical values. Try it 5 given letter 1D453, letter 1D461, equals letter 1D461, 2 minus letter 1D461, and letter 210e. Letter 1D465 equals 3 letter 1D465 plus 2. Evaluate A letter 210e, letter 1D453, 2, B letter 210e, letter 1D453, minus 2. Finding the domain of a composite function as we discussed previously. The domain of a composite function, such as letter 1D453, letter 1D454, is dependent on the domain of G and the domain of F. It is important to know when we can apply a composite function and when we cannot, that is, to know the domain of a function such as, let us assume we know the domains of the functions f and g separately. If we write the composite function for an input x as letter 1D453, letter 1D454, letter 1D465, we can see right away that x must be a member of the domain of g in order for the expression to be meaningful, because otherwise we cannot complete the inner function evaluation. However, we also see that letter 1D454, letter 1d465, must be a member of the domain of F. Otherwise, the second function evaluation in letter 1d453, letter 1d454, letter 1d465, cannot be completed, and the expression is still undefined. Thus, the domain of letter 1d453, letter 1d454, consists of only those inputs in the domain of G that produce outputs from G belonging to the domain of F. Note that the domain of F composed with G is the set of all x such that x is in the domain of G, and letter 1d454, letter 1d465, is in the domain of F. Domain of a composite function, the domain of a composite function, letter 1d453, letter 1d454, letter 1d465, is the set of those inputs x in the domain of G for which letter 1d454, letter 1d465, is in the domain of F. How to given a function composition letter 1d453, letter 1d454, letter 1d465, determine its domain. Find the domain of G. Find the domain of F. Find those inputs x in the domain of G for which letter 1d454, letter 1d465, is in the domain of F. That is, exclude those inputs x from the domain of G for which letter 1d454, letter 1d465, is not in the domain of F. The resulting set is the domain of letter 1d453, letter 1d454. Example 8. Finding the domain of a composite function. Find the domain of letter 1d453, letter 1d454, letter 1d465, WHERE letter 1d453, letter 1d465, equals 5 letter 1d465 minus 1 AND letter 1d454, letter 1d465, equals 43 letter 1d465 minus 2. Solution. The domain of letter 1d454, letter 1d465, consists of all real numbers except letter 1d465 equals 23, since that input value would cause us to divide by 0. Likewise, the domain of F consists of all real numbers except 1. So we need to exclude from the domain of letter 1d454, letter 1d465, that value of x for which 43 letter 1d465 minus 246 letter 1d465 equals 13 letter 1d465 minus 23 letter 1d465, 2. So the domain of letter 1d453, letter 1d454, is the set of all real numbers except 23 and 2. This means that letter 1d465 not equal to 23 or letter 1d465 not equal to 2, we can write this in interval notation as minus infinity, 23, 23, 2, 2, infinity. Example 9. Finding the domain of a composite function involving radicals. Find the domain of letter 1d453, letter 1d454, letter 1d465, WHERE letter 1d453, letter 1d465, equals letter 1d465 plus 2 square and letter 1d454, letter 1d465 equals 3 minus letter 1d465 square. Solution. Because we cannot take the square root of a negative number. The domain of G is minus infinity, 3. Now we check the domain of the composite function, letter 1d453, letter 1d454, letter 1d465, equals 3 minus letter 1d465 square plus 2 square for letter 1d453, letter 1d454. Letter 1d465 equals 3 minus letter 1d465 square plus 2 square. 3 minus letter 1d465 square plus 2 greater or equal to 0. Since the radicand of a square root must be positive. Since square roots are positive, 3 minus letter 1d465 square greater 0. Or 3 minus letter 1d465 greater or equal to 0, which gives a domain of minus infinity, 3. Analysis. This example shows that knowledge of the range of functions, specifically the inner function, can also be helpful in finding the domain of a composite function. It also shows that the domain of letter 1d453, letter 1d454 can contain values that are not in the domain of F, though they must be in the domain of G. Try it 6. Find the domain of letter 1d453, letter 1d454, letter 1d465, WHERE letter 1d453, letter 1d465, equals 1 letter 1d465 minus 2 and letter 1d454, letter 1d465 equals letter 1d465 plus 4 square, decomposing a composite function into its component functions in some cases. It is necessary to decompose a complicated function. In other words, we can write it as a composition of two simpler functions. There may be more than one way to decompose a composite function, so we may choose the decomposition that appears to be most expedient. Example 10, decomposing a function, write letter 1d453. Letter 1d465 equals 5 minus letter 1d465 2 square as the composition of two functions. Solution: we are looking for two functions, g and h, so letter 1d453, letter 1d465 equals letter 1d454, letter 210e, letter 1d465. To do this, we look for a function inside a function in the formula for letter 1d453, letter 1d465. As one possibility, we might notice that the expression 5 minus letter 1d465 2 is the inside of the square root. We could then decompose the function as letter 210e, letter 1d465, equals 5 minus letter 1d465 2, and we can check our answer by recomposing the functions. Letter 1d454, letter 210e, letter 1d465, equals letter 1d454, 5 minus letter 1d465 2 equals 5 minus letter 1d465 2 square. Try it 7, write letter 1d453, letter 1d465, equals 43 minus 4 plus letter 1d465 2 square root as the composition of two functions. Media access: these online resources for additional instruction and practice with composite functions. Composite functions, composite function notation application, composite functions, using graphs, decompose functions, composite function values 3. 4 section exercises verbal 1. How does one find the domain of the quotient of two functions, letter 1d453, letter 1d454? 2. What is the composition of two functions, letter 1d453, letter 1d454? 3. If the order is reversed when composing two functions, can the result ever be the same as the answer in the original order of the composition? If yes, give an example. If no, explain why not. 4. How do you find the domain for the composition of two functions, letter 1d453, letter 1d454? Algebraic for the following exercises, determine the domain for each function in interval notation. 5. Given letter 1d453, letter 1d465 equals letter 1d465 2 plus 2 letter 1d465 and letter 1d454. Letter 1d465 equals 6 minus letter 1d465 2. Find f plus g. Letter 1d453 minus letter 1d454. Letter 1d453, letter 1d454. And letter 1d453, letter 1d454. 6. Given letter 1d453, letter 1d465 equals minus 3 letter 1d465 2 plus letter 1d465 and letter 1d454. Letter 1d465 equals 5. Find f plus g. Letter 1d453 minus letter 1d454. Letter 1d453, letter 1d454. And letter 1d453, letter 1d454. 7. Given letter 1d453, letter 1d465 equals 2 letter 1d465 2 plus 4 letter 1d465 and letter 1d454. Letter 1d465 equals 12 letter 1d465. Find f plus g. Letter 1d453 minus letter 1d454. Letter 1d453, letter 1d454. And letter 1d453, letter 1d454. 8. Given letter 1d453, letter 1d465 equals 1 letter 1d465 minus 4 and letter 1d454. Letter 1d465 equals 16 minus letter 1d465. Find f plus g. Letter 1d453 minus letter 1d454. Letter 1d453, letter 1d454. And letter 1d453, letter 1d454. 9. Given letter 1d453, letter 1d465 equals 3 letter 1d465 2 and letter 1d454. Letter 1d465 equals letter 1d465 minus 5 square. Find f plus g. Letter 1d453 minus letter 1d454. Letter 1d453, letter 1d454. And letter 1d453, letter 1d454. 10. Given and letter 1d454. Letter 1d465 equals letter 1d465 minus 3. Find letter 1d454, letter 1d453. 11. For the following exercise, find the indicated function given letter 1d453, letter 1d465, equals 2 letter 1d465 2 plus 1 and letter 1d454, letter 1d465, equals 3 letter 1d465 minus 5. A. Letter 1d453, letter 1d4542. B. Letter 1d453, letter 1d454, letter 1d465. C. Letter 1d454, letter 1d453, letter 1d465. D. Letter 1d454, letter 1d454, letter 1d465. E. Letter 1d453, letter 1d453. Minus 2 for the following exercises. Use each pair of functions to find letter 1d453, letter 1d454, letter 1d465, and letter 1d454, letter 1d453, letter 1d465. Simplify your answers. 12. Letter 1d453, letter 1d465 equals letter 1d465 2 plus 1, letter 1d454, letter 1d465 equals letter 1d465 plus 2 square 13. Letter 1d453, letter 1d465 equals letter 1d465 square plus 2, letter 1d454. Letter 1d465 equals letter 1d465 2 plus 314. Letter 1d453, letter 1d465 equals letter 1d465. Letter 1d454, letter 1d465 equals 5 letter 1d465 plus 115. Letter 1d453, letter 1d465 equals letter 1d465 square 3, letter 1d454. Letter 1d465 equals letter 1d465 plus 1 letter 1d465 316. Letter 1d453, letter 1d465 equals 1 letter 1d465 minus 6, letter 1d454. Letter 1d465 equals 7 letter 1d465 plus 617. Letter 1d453, letter 1d465 equals 1 letter 1d465 minus 4, letter 1d454. Letter 1d465 equals 2 letter 1d465 plus 4 for the following exercises. Use each set of functions to find letter 1d453, letter 1d454, letter 210e, letter 1d465. Simplify your answers. 18. Letter 1d453, letter 1d465 equals letter 1d465 4 plus 6, letter 1d454. Letter 1d465 equals letter 1d465 minus 6, and letter 210e, letter 1d465 equals letter 1d465 square 19. Letter 1d453, letter 1d465 equals letter 1d465 2 plus 1, and letter 210e. Letter 1d465 equals letter 1d465 plus 320. Given letter 1d453, letter 1d465 equals 1 letter 1d465 and letter 1d454. Letter 1d465 equals letter 1d465 minus 3, find the following. A. Letter 1d453, letter 1d454, letter 1d465. B. The domain of letter 1d453, letter 1d454, letter 1d465. In interval notation C, letter 1d454, letter 1d453, letter 1d465. D. The domain of letter 1d454, letter 1d453, letter 1d465. E. Letter 1d453, letter 1d454, letter 1d465, 21. Given letter 1d453, letter 1d465 equals 2 minus 4 letter 1d465 square and letter 1d454, letter 1d465 equals minus 3 letter 1d465, find the following. A. Letter 1d454, letter 1d453, letter 1d465. B. The domain of letter 1d454, letter 1d453, letter 1d465, in interval notation 22. Given the functions letter 1d453, letter 1d465, equals 1 minus letter 1d465, letter 1d465, at nd letter 1d454. Letter 1d465 equals 11 plus letter 1d465 2, find the following. A. Letter 1d454, letter 1d453, letter 1d465. B. Letter 1d454, letter 1d453. 2, 23. Given functions letter 1 d45d. Letter 1 d465 equals 1 letter 1 d465 square root and letter 1 d45a. Letter 1 d465 equals letter 1 d465 2 minus 4. State the domain of each of the following functions using interval notation. A. Letter 1 d45d, letter 1 d465, letter 1 d45a, letter 1 d465. B. Letter 1 d45d, letter 1 d45a, letter 1 d465. C. Letter 1 d45a, letter 1 d45d, letter 1 d465. 24. Given functions letter 1 d45e. Letter 1 d465 equals 1 letter 1 d465 square root and letter 210e. Letter 1 d465 equals letter 1 d465 2 minus 9. State the domain of each of the following functions using interval notation. A. Letter 1 d45e, letter 1 d465, letter 210e, letter 1 d465. B. Letter 1 d45e, letter 210e, letter 1 d465. C. Letter 210e, letter 1 d45e, letter 1 d465. 25. For letter 1 d453, letter 1 d465 equals 1 letter 1 d465 and letter 1 d454. Letter 1 d465 equals letter 1 d465 minus 1 square. Write the domain of letter 1 d453, letter 1 d454. Letter 1 d465 in interval notation. For the following exercises, find functions letter 1 d453, letter 1 d465, and letter 1 d454. Letter 1 d465. So the given function can be expressed as letter 210e, letter 1 d465 equals letter 1 d453, letter 1 d454, letter 1 d465. 26. Letter 210e, letter 1 d465 equals letter 1 d465 plus 227. Letter 210e, letter 1 d465 equals letter 1 d465 minus 5, 328. Letter 210e, letter 1 d465 equals 3 letter 1 d465 minus 529. Letter 210e, letter 1 d465 equals 4 letter 1 d465 plus 230. Letter 210e, letter 1 d465 equals 4 plus letter 1 d465 square 331. Letter 210e, letter 1 d465 equals 12 letter 1 d465 minus 3 square 332. Letter 210e, letter 1 d465 equals 1, 3 letter 1 d465 2 minus 4 minus 333. Letter 210e, letter 1 d465 equals 3 letter 1 d465 minus 2 letter 1 d465 plus 5 square 434. Letter 210e, letter 1 d465 equals 8 plus letter 1 d465 38 minus letter 1 d465 3, 435. Letter 210e, letter 1 d465 equals 2 letter 1 d465 plus 6 square 36. Letter 210e, letter 1 d465 equals 5 letter 1 d465 minus 1, 337. Letter 210e, letter 1 d465 equals letter 1 d465 minus 1 square 338. Letter 210e, letter 1 d465 equals letter 1 d465 2 plus 739. Letter 210e, letter 1 d465 equals 1, letter 1 d465 minus 2, 340. Letter 210e, letter 1 d465 equals 12 letter 1 d465 minus 3, 241. Letter 210e, letter 1 d465 equals 2 letter 1 d465 minus 13 letter 1 d465 plus 4 square graphical for the following exercises. Use the graphs of f, shown in Figure 4, and g, shown in Figure 5, to evaluate the expressions. Graph of a function. Figure 4 graph of a function. Figure 5 42. Letter 1 d453, letter 1 d4543, 43. Letter 1 d453, letter 1 d454, 1, 44. Letter 1 d454, letter 1 d453, 1, 45. Letter 1 d454, letter 1 d453, 0, 46. Letter 1 d453, letter 1 d453, 5, 47. Letter 1 d453, letter 1 d453, 4, 48. Letter 1 d454, letter 1 d454, 2, 49. Letter 1 d454, letter 1 d454, 0. For the following exercises, use graphs of letter 1D453, letter 1D465. Shown in Figure 6, letter 1D454, letter 1D465. Shown in Figure 7 and letter 210E, letter 1D465. Shown in Figure 8 to evaluate the expressions. Figure 6 graph of a parabola. Figure 7 graph of a square root function. Figure 850. Letter 1D454, letter 1D453, 151. Letter 1D454, letter 1D4532, 52. Letter 1D453, letter 1D454, 4, 53. Letter 1D453, letter 1D454, 1, 54. Letter 1D453, letter 210E2, 55. Letter 210E, letter 1D453, 2, 56. Letter 1D453, letter 1D454, letter 210E4, 57. Letter 1D453, letter 1D454, letter 1D453, -2. Numeric for the following exercises, use the function values for fan g shown in Table 3 to evaluate each expression. X letter 1D453, letter 1D465, letter 1D454, letter 1D465, 07916525638241508627713894930 Table 358. Letter 1D453, letter 1D4548, 59. Letter 1D453, letter 1D454, 5, 60. Letter 1D454, letter 1D4535, 61. Letter 1D454, letter 1D4533, 62. Letter 1D453, letter 1D453, 4, 63. Letter 1D453, letter 1D453, 1, 64. Letter 1D454, letter 1D454, 2, 65. Letter 1D454, letter 1D454, 6. For the following exercises, use the function values for fan g shown in Table 4 to evaluate the expressions. X letter 1D453, letter 1D465, letter 1D454, letter 1D465, -311 -8 -29 -3 -1700 5 1130 2 1 -33 -1 -8 Table 466. Letter 1D453, letter 1D454, 1, 67. Letter 1D453, letter 1D454, 2, 68. Letter 1D454, letter 1D453, 2, 69. Letter 1D454, letter 1D453, 3, 70. Letter 1D454, letter 1D454, 1, 71. Letter 1D453, letter 1D453, 3. For the following exercises, use each pair of functions to find letter 1D453, letter 1D454, 0, and letter 1D454, letter 1D453, 0. 72. Letter 1D453, letter 1D465, equals 4 letter 1D465 plus 8, letter 1D454. Letter 1D465 equals 7 minus letter 1D465, 273. Letter 1D453, letter 1D465 equals 5 letter 1D465 plus 7, letter 1D454. Letter 1D465 equals 4 minus 2 letter 1D465, 274. Letter 1D453, letter 1D465 equals letter 1D465 plus 4 square, letter 1D454. Letter 1D465 equals 12 minus letter 1D465, 375. Letter 1D453, letter 1D465 equals 1 letter 1D465 plus 2. Letter 1D454, letter 1D465 equals 4 letter 1D465 plus 3 for the following exercises. Use the functions letter 1D453, letter 1D465 equals 2 letter 1D465 2 plus 1, and letter 1D454. Letter 1D465 equals 3 letter 1D465 plus 5 to evaluate or find the composite function as indicated. 76. Letter 1D453, letter 1D454, 2, 77. Letter 1D453, letter 1D454, letter 1D465. 78. Letter 1D454, letter 1D453, -3, 79. Letter 1D454, letter 1D454. Letter 1D465. Extensions for the following exercises. Use letter 1D453. Letter 1D465 equals letter 1D465 3 plus 1, and letter 1D454 letter 1D465 equals letter 1D465 minus 1 square 3. 80. Find letter 1D453 letter 1D454, letter 1D465, and letter 1D454 letter 1D453, letter 1D465. Compare the two answers. 81. Find letter 1D453 letter 1D454, 2, and letter 1D454 letter 1D453, 2. 82. What is the domain of letter 1D454 letter 1D453, letter 1D465? 83. What is the domain of letter 1D453 letter 1D454, letter 1D465? 84. Let letter 1D453, letter 1D465 equals 1 letter 1D465. A. Find letter 1D453 letter 1D453, letter 1D465. B. Eyes letter 1D453 letter 1D453, letter 1D465, for any function f the same result as the answer to part A for any function. Explain. For the following exercises, let letter 1D439, letter 1D465 equals letter 1D465 plus 1 5, letter 1D453, letter 1D465 equals letter 1D465 5, and letter 1D454, letter 1D465 equals letter 1D465 plus 1. 85. True or false? Letter 1D454 letter 1D453, letter 1D465 equals letter 1D439, letter 1D465. 86. True or false? Letter 1D453, letter 1D454, letter 1D465 equals letter 1D439, letter 1D465. For the following exercises, find the composition when letter 1D453, letter 1D465, equals letter 1D465 2 plus 2 for all letter 1D465 greater or equal to 0 and letter 1D454. Letter 1D465 equals letter 1D465 minus 2 square. 87. Letter 1D453 letter 1D454 6. Letter 1D454 letter 1D453 6. 88. Letter 1D454 letter 1D453 letter 1D440. Letter 1D453 letter 1D454 letter 1D440 89. Letter 1D453 letter 1D454 11. Letter 1D454 letter 1D453 11. Real-world applications 90. The function letter 1D437, letter 1D45D, gives the number of items that will be demanded when the price is P. The production cost letter 1D436, letter 1D465, is the cost of producing X items. To determine the cost of production when the price is $6, you would do which of the following? A. Evaluate letter 1D437, letter 1D436, 6. B. Evaluate letter 1D436, letter 1D437, 6. C. Solve letter 1D437, letter 1D436, letter 1D465, equals 6. D. Solve letter 1D436, letter 1D437, letter 1D45D, equals 6. 91. The function gives the pain level on a scale of 0 to 10 experienced by a patient with D milligrams of a pain-reducing drug in her system. The milligrams of the drug in the patient's system after T minutes is modeled by letter 1D45A, letter 1D461. Which of the following would you do in order to determine when the patient will be at a pain level of 4? A. Evaluate letter 1D434, letter 1D45A 4. B. Evaluate letter 1D45A, letter 1D434, 4. C. Solve letter 1D434, letter 1D45A, letter 1D461, equals 4. D. Solve letter 1D45A, letter 1D434, letter 1D451, equals 4. 92. A store offers customers a 30% discount on the price X of selected items. Then, the store takes off an additional 15% at the cash register. Write a price function letter 1D443, letter 1D465, that computes the final price of the item in terms of the original price X. Hint: use function composition to find your answer. 93. A raindrop hitting a lake makes a circular ripple. If the radius, in inches, grows as a function of time in minutes according to letter 1d45f, letter 1d461, equals 25 letter 1d461 plus 2 square, find the area of the ripple as a function of time. Find the area of the ripple at letter 1d461 equals 2, 94. A forest fire leaves behind an area of grass burned in an expanding circular pattern. If the radius of the circle of burning grass is increasing with time according to the formula letter 1d45f, letter 1d461 equals 2 letter 1d461 plus 1, express the area burned as a function of time, t minutes. 95. Use the function you found in the previous exercise to find the total area burned after 5 minutes. 96. The radius r, in inches, of a spherical balloon is related to the volume, v, by letter 1d45f, letter 1d449, equals 3 letter 1d449 4 letter 1d70b square 3. Air is pumped into the balloon, so the volume after t seconds is given by letter 1d449, letter 1d461, equals 10 plus 20 letter 1d461. A. Find the composite function letter 1d45f, letter 1d449, letter 1d461. B. Find the exact time when the radius reaches 10 inches. 97. The number of bacteria in a refrigerated food product is given by letter 1d441. Letter 1d447 equals 23 letter 1d447, 2 minus 56, letter 1d447 plus 1. 3 letter 1d447 33, where T is the temperature of the food. When the food is removed from the refrigerator, the temperature is given by letter 1d447, letter 1d461, equals 5 letter 1d461 plus 1. 5, where T is the time in hours. A. Find the composite function letter 1d441, letter 1d447, letter 1d461. B. Find the time, round to 2 decimal places, when the bacteria count reaches 6752. Learning objectives in this section, you will graph functions using vertical and horizontal shifts. Graph functions using reflections about the x-axis and the y-axis. Determine whether a function is even, odd, or neither from its graph. Graph functions using compressions and stretches. Combine transformations. A photograph of 2 children staring at themselves in a distorting mirror. Figure 1, credit. Misco/flicker. We all know that a flat mirror enables us to see an accurate image of ourselves and whatever is behind us. When we tilt the mirror, the images we see may shift horizontally or vertically. But what happens when we bend a flexible mirror? Like a carnival funhouse mirror, it presents us with a distorted image of ourselves, stretched or compressed horizontally or vertically. In a similar way, we can distort or transform mathematical functions to better adapt them to describing objects or processes in the real world. In this section, we will take a look at several kinds of transformations. Graphing functions using vertical and horizontal shifts, often when given a problem. We try to model the scenario using mathematics in the form of words, tables, graphs, and equations. One method we can employ is to adapt the basic graphs of the toolkit functions to build new models for a given scenario. There are systematic ways to alter functions to construct appropriate models for the problems we are trying to solve. Identifying vertical shifts, one simple kind of transformation, involves shifting the entire graph of a function up, down, right, or left. The simplest shift is a vertical shift, moving the graph up or down, because this transformation involves adding a positive or negative constant to the function. In other words, we add the same constant to the output value of the function regardless of the input. For a function letter 1d454, letter 1d465 equals letter 1d453, letter 1d465, plus letter 1d458, the function letter 1d453, letter 1d465, is shifted vertically k units. See Figure 2 for an example. Graphing is shown on a set of x and y axes. The scale is -3 to +3 for both x and y2 graphs are shown. A blue curve for the cube root of x and an orange curve for the cube root of x plus 1. The blue curve goes from the third quadrant through the origin into the first quadrant. The orange curve is shifted 1 unit up. Figure 2 vertical shift by letter 1d458 equals 1 of the cube root function, letter 1d453, letter 1d465, equals letter 1d465 square 3. To help you visualize the concept of a vertical shift, consider that letter 1d466 equals letter 1d453, letter 1d465. Therefore, letter 1d453, letter 1d465, plus letter 1d458 is equivalent to y plus k. Every unit of y is replaced by y plus k, so the y value increases or decreases depending on the value of k. The result is a shift upward or downward. Vertical shift given a function letter 1d453, letter 1d465. A new function letter 1d454. Letter 1d465 equals letter 1d453, letter 1d465 plus letter 1d458, where k is a constant, is a vertical shift of the function letter 1d453, letter 1d465. All the output values change by k units. If k is positive, the graph will shift up. If k is negative, the graph will shift down. Example 1, adding a constant to a function to regulate temperature in a green building. Airflow vents near the roof open and close throughout the day. Figure 3 shows the area of open vents V, in square feet, throughout the day and hours after midnight, T. During the summer, the facility's manager decides to try to better regulate temperature by increasing the amount of open vents by 20 square feet throughout the day and night. Sketch a graph of this new function. A blue graph is shown on a set of T and V axes. The scale is -4 to +24 for T and -4 to 300 for V. The graph lies along the T-axis from the origin to 8, then rises as a straight line to 10, 220. Then it is a horizontal straight line to 17, 220. It then is a straight line to the T-axis at 19. It is then a straight line along the T-axis until T equals 24. Figure 3 solution, we can sketch a graph of this new function by adding 20 to each of the output values of the original function. This will have the effect of shifting the graph vertically up, as shown in Figure 4. A blue graph is shown on a set of T and V axes. The scale is -4 to +24 for T and -4 to 300 for V. The graph lies along the T-axis from the origin to 8, then rises as a straight line to 10, 220. Then it is a horizontal straight line to 17, 220. It then is a straight line to the T-axis at 19. It is then a straight line along the T-axis until T equals 24. There is also an orange graph identical to the blue graph, but shifted up by 20 units. Figure 4, notice that in Figure 4, for each input value, the output value has increased by 20, so if we call the new function letter 1d446, letter 1d461, we could write letter 1d446, letter 1d461 equals letter 1d449, letter 1d461, plus 20. This notation tells us that, for any value of t, letter 1d446, letter 1d461, can be found by evaluating the function v at the same input and then adding 20 to the result. This defines S as a transformation of the function v, in this case a vertical shift up 20 units. Notice that, with a vertical shift, the input values stay the same and only the output values change. See Table 1. T 0, 8, 10, 17, 19, 24, letter 1d449, letter 1d461. 0, 0, 220, 220, 0, 0, letter 1d446, letter 1d461. 2020, 240, 240, 2020 Table 1. How to give a tabular function. Create a new row to represent a vertical shift. Identify the output row or column. Determine the magnitude of the shift. Add the shift to the value in each output cell. Add a positive value for up or a negative value for down. Example 2, shifting a tabular function, vertically a function letter 1d453, letter 1d465, is given in Table 2. Create a table for the function letter 1d454, letter 1d465 equals letter 1d453, letter 1d465, minus 3. x2, 4, 6, 8, letter 1d453, letter 1d465. 1, 3, 7, 11 Table 2, solution, the formula letter 1d454, letter 1d465, equals letter 1d453, letter 1d465. Minus 3 tells us that we can find the output values of G by subtracting 3 from the output values of F. For example, letter 1 D453, 2 letter 1 D454, letter 1 D465, letter 1 D454, 2 = 1 letter 1 D453, letter 1 D465, minus 3 letter 1 D453, 2 minus 30, 1 minus 3 minus 2, given transformations subtracting 3 from each letter 1 D453, letter 1 D465, value. We can complete a table of values for letter 1 D454, letter 1 D465, as shown in Table 3. X2468 letter 1 D453, letter 1 D465, 13711 letter 1 D454, letter 1 D465, minus 2048 Table 3 analysis, as with the earlier vertical shift. Notice the input values stay the same and only the output values change. Try at 1 the function letter 210e, letter 1 D461 equals minus 4. 9t2 plus 30t gives the height h of a ball in meters, thrown upward from the ground after t seconds. Suppose the ball was instead thrown from the top of a 10m building. Relate this new height function letter 1 D44f, letter 1 D461, to letter 210e, letter 1 D461, and then find a formula for letter 1 D44f, letter 1 D461. Identifying horizontal shifts, we just saw that the vertical shift is a change to the output or outside of the function. We will now look at how changes to input on the inside of the function change its graph and meaning. A shift to the input results in a movement of the graph of the function left or right in what is known as a horizontal shift, shown in Figure 5. A graph is shown on a set of x and y axes. The scale is -3 to +3 for both x and y2 graphs are shown. A blue curve for the cube root of x and an orange curve for the cube root of x plus 1. The blue curve goes from the third quadrant through the origin into the first quadrant. The orange curve is shifted 1 unit to the left. Figure 5 horizontal shift of the function letter 1 D453, letter 1 D465 equals letter 1 D465 square 3. Note that x plus 1 means letter 210e equals 1, which shifts the graph to the left, that is, towards negative values of x. For example, if letter 1 D453, letter 1 D465 equals letter 1 D465 2, then letter 1 D454, letter 1 D465 equals letter 1 D465 minus 2 is a new function. Each input is reduced by 2 prior to squaring the function. The result is that the graph is shifted 2 units to the right, because we would need to increase the prior input by 2 units to yield the same output value as given in f. Horizontal shift given a function f, a new function letter 1 D454, letter 1 D465, equals letter 1 D453, letter 1 D465 minus letter 210e, where h is a constant, is a horizontal shift of the function f. If h is positive, the graph will shift right. If h is negative, the graph will shift left. Example 3, adding a constant to an input returning to our building airflow example from Figure 3, suppose that in autumn the facilities manager decides that the original venting plan starts too late and wants to begin the entire venting program 2 hours earlier. Sketch a graph of the new function. Solution we can set to be the original program and letter 1 D439, letter 1 D461 to be the revised program, letter 1 D449, letter 1 D461, letter 1 D439, letter 1 D461 equals the original venting plan starting 2 HRS sooner in the new graph. At each time, the airflow is the same as the original function v was 2 hours later. For example, in the original function v, the airflow starts to change at 8 a.m., whereas for the function f, the airflow starts to change at 6 a.m. The comparable function values are letter 1 D449, 8 equals letter 1 D439, 6. See Figure 6. Notice also that the vents first opened to 220 ft2 at 10 a.m. under the original plan, while under the new plan the vents reached 220 ft2 at 8 a.m. So letter 1 D449, 10 equals letter 1 D439, 8. In both cases, we see that because letter 1 D439, letter 1 D461 starts 2 hours sooner, letter 210e equals -2. That means that the same output values are reached when letter 1D439, letter 1D461 equals letter 1D449, letter 1D461 minus 2 equals letter 1D449, letter 1D461 plus 2. A blue graph is shown on a set of t and v axes. The scale is -4 to +24 for t and -4 to 300 for v. The graph lies along the t-axis from the origin to 8, then rises as a straight line to 10, 220. Then it is a horizontal straight line to 17, 220. It then is a straight line to the t-axis at 19. It is then a straight line along the t-axis until t equals 24. There is also an orange graph identical to the blue graph, but shifted left by 2 units. Figure 6 analysis note that letter 1D449, letter 1D461 plus 2 has the effect of shifting the graph to the left. Horizontal changes, or inside changes, affect the domain of a function, the input, instead of the range, and often seem counterintuitive. The new function letter 1D439, letter 1D461, uses the same outputs as letter 1D449, letter 1D461, but matches those outputs to inputs 2 hours earlier than those of letter 1D449, letter 1D461. Said another way, we must add 2 hours to the input of V to find the corresponding output for F. Letter 1D439, letter 1D461, equals letter 1D449, letter 1D461 plus 2. How to, given a tabular function, create a new row to represent a horizontal shift. Identify the input row or column. Determine the magnitude of the shift. Add the shift to the value in each input cell. Example 4. Shifting a tabular function horizontally, a function letter 1D453, letter 1D465, is given in Table 4. Create a table for the function letter 1D454, letter 1D465 equals letter 1D453, letter 1D465 minus 3. x2468 letter 1D453, letter 1D465. 13711 Table 4 solution, the formula letter 1D454, letter 1D465, equals letter 1D453, letter 1D465 minus 3, tells us that the output values of G are the same as the output value of F when the input value is 3 less than the original value. For example, we know that letter 1D453, 2 equals 1. To get the same output from the function G, we will need an input value that is 3 larger. We input a value that is 3 larger for letter 1D454, letter 1D465, because the function takes 3 away before evaluating the function f. Letter 1D454, 5, equals letter 1D453, 5 minus 3 letter 1D453, 2, 1. We continue with the other values to create Table 5. x57911 letter 1D465 minus 32468 letter 1D453, letter 1D465 3, 13711 letter 1D454, letter 1D465, 13711 Table 5. The result is that the function letter 1D454, letter 1D465, has been shifted to the right by 3. Notice the output values for letter 1D454, letter 1D465, remain the same as the output values for letter 1D453, letter 1D465. But the corresponding input values, x, have shifted to the right by 3. Specifically, 2 shifted to 5, 4 shifted to 7, 6 shifted to 9, and 8 shifted to 11. Analysis Figure 7 represents both of the functions. We can see the horizontal shift in each point. Graph of the points from the previous table for f, x, and g, x equals f, x3. Figure 7 Example 5, identifying a horizontal shift of a toolkit function. Figure 8 represents a transformation of the toolkit function letter 1D453, letter 1D465 equals letter 1D465 2. Relate this new function letter 1D454, letter 1D465 to letter 1D453, letter 1D465, and then find a formula for letter 1D454, letter 1D465. Graph of a parabola. Figure 8 solution. Notice that the graph is identical in shape to the letter 1D453, letter 1D465 equals letter 1D465 2 function, but the x values are shifted to the right 2 units. The vertex used to be at 0, but now the vertex is at 20. The graph is the basic quadratic function shifted 2 units to the right. So letter 1d454, letter 1d465, equals letter 1d453. Letter 1d465 minus 2, notice how we must input the value letter 1d465 equals 2 to get the output value letter 1d466 equals 0. The x values must be 2 units larger because of the shift to the right by 2 units. We can then use the definition of the letter 1d453, letter 1d465, function to write a formula for letter 1d454, letter 1d465, by evaluating letter 1d453, letter 1d465 minus 2, letter 1d453, letter 1d465, letter 1d454, letter 1d465, letter 1d454, letter 1d465 equals, letter 1d465 to letter 1d453, letter 1d465 minus 2 letter 1d453, letter 1d465 minus 2 equals, letter 1d465 minus 2 analysis to determine whether the shift is plus 2 or minus 2. Consider a single reference point on the graph. For a quadratic, looking at the vertex point is convenient. In the original function, letter 1d453, 0 equals 0. In our shifted function, letter 1d454, 2 equals 0. To obtain the output value of 0 from the function f, we need to decide whether a plus or a minus sign will work to satisfy letter 1d454. 2 equals letter 1d453. Letter 1d465 minus 2 equals letter 1d453. 0 equals 0. For this to work, we will need to subtract 2 units from our input values. Example 6, interpreting horizontal versus vertical shifts, the function letter 1d43a, letter 1d45a, gives the number of gallons of gas required to drive m miles. Interpret letter 1d43a, letter 1d45a, plus 10 and letter 1d43a, letter 1d45a plus 10. Solution letter 1d43a, letter 1d45a, plus 10 can be interpreted as adding 10 to the output, gallons. This is the gas required to drive m miles, plus another 10 gallons of gas. The graph would indicate a vertical shift. Letter 1d43a, letter 1d45a plus 10 can be interpreted as adding 10 to the input miles. So this is the number of gallons of gas required to drive 10 miles more than m miles. The graph would indicate a horizontal shift. Try it too given the function. Graph the original function letter 1d453, letter 1d465, and the transformation letter 1d454. Letter 1d465 equals letter 1d453, letter 1d465 plus 2 on the same axes. Is this a horizontal or a vertical shift? Which way is the graph shifted and by how many units? Combining vertical and horizontal shifts, now that we have 2 transformations, we can combine them. Vertical shifts are outside changes that affect the output, y values, and shift the function up or down. Horizontal shifts are inside changes that affect the input x, values, and shift the function left or right. Combining the 2 types of shifts will cause the graph of a function to shift up or down and left or right. How to give a function and both a vertical and a horizontal shift? Sketch the graph. Identify the vertical and horizontal shifts from the formula. The vertical shift results from a constant added to the output. Move the graph up for a positive constant and down for a negative constant. The horizontal shift results from a constant added to the input. Move the graph left for a positive constant and right for a negative constant. Apply the shifts to the graph in either order. Example 7, graphing combined vertical and horizontal shifts given letter 1d453, letter 1d465, equals letter 1d465. Sketch a graph of letter 210e. Letter 1d465 equals letter 1d453, letter 1d465 plus 1 minus 3. Solution: the function f is our toolkit absolute value function. We know that this graph has a V shape with the point at the origin. The graph of h has transformed f in 2 ways. Letter 1d453, letter 1d465 plus 1 is a change on the inside of the function, giving a horizontal shift left by 1 and the subtraction by 3 in letter 1d453. Letter 1d465 plus 1 minus 3 is a change to the outside of the function, giving a vertical shift down by 3. The transformation of the graph is illustrated in Figure 9. Let us follow one point of the graph of letter 1 D453, letter 1 D465, equals letter 1 D465. The point 0 is transformed first by shifting left 1 unit. 0, 0, right arrow -1, 0. The point -1, 0 is transformed next by shifting down 3 units. -1, 0, right arrow, -1, -3 graph of an absolute function, y equals x, and how it was transformed to y equals x plus 1, 3. Figure 9, Figure 10 shows the graph of h. The final function y equals x plus 1, 3. Figure 10 try it 3 given letter 1 D453, letter 1 D465 equals letter 1 D465. Sketch a graph of letter 210e. Letter 1 D465 equals letter 1 D453, letter 1 D465 minus 2 plus 4. Example 8, identifying combined vertical and horizontal shifts. Write a formula for the graph shown in Figure 11, which is a transformation of the toolkit square root function. Graph of a square root function, transposed right 1 unit and up 2. Figure 11 solution, the graph of the toolkit function starts at the origin, so this graph has been shifted 1 to the right and up 2. In function notation, we could write that as letter 210e. Letter 1 D465 equals letter 1 D453, letter 1 D465 minus 1 plus 2 using the formula for the square root function. We can write letter 210e. Letter 1 D465 equals letter 1 D465 minus 1 square plus 2. Analysis note that this transformation has changed the domain and range of the function. This new graph has domain 1, infinity, and range 2, infinity. Try it 4. Write a formula for a transformation of the toolkit reciprocal function letter 1 D453. Letter 1 D465 equals 1 letter 1 D465 that shifts the function's graph 1 unit to the right and 1 unit up. Graphing functions using reflections about the axes. Another transformation that can be applied to a function is a reflection over the x or y-axis. A vertical reflection reflects a graph vertically across the x-axis, while a horizontal reflection reflects a graph horizontally across the y-axis. The reflections are shown in Figure 12. Graph of the vertical and horizontal reflection of a function. Figure 12, vertical and horizontal reflections of a function. Notice that the vertical reflection produces a new graph that is a mirror image of the base or original graph about the x-axis. The horizontal reflection produces a new graph that is a mirror image of the base or original graph about the y-axis. Reflections given a function letter 1 D453, letter 1 D465, a new function letter 1 D454, letter 1 D465, equals minus letter 1 D453, letter 1 D465, is a vertical reflection of the function letter 1 D453, letter 1 D465, sometimes called a reflection about, or over, or through the x-axis. Given a function letter 1 D453, letter 1 D465, a new function letter 1 D454, letter 1 D465 equals letter 1 D453, minus letter 1 D465, is a horizontal reflection of the function letter 1 D453, letter 1 D465, sometimes called a reflection about the y-axis. How to, given a function, reflect the graph both vertically and horizontally. Multiply all outputs by 1 for a vertical reflection. The new graph is a reflection of the original graph about the x-axis. Multiply all inputs by 1 for a horizontal reflection. The new graph is a reflection of the original graph about the y-axis. Example 9, reflecting a graph horizontally and vertically. Reflect the graph of letter 1 D460, letter 1 D461, equals letter 1 D461 square root, a vertically and b horizontally. Solution, reflecting the graph vertically means that each output value will be reflected over the horizontal t-axis as shown in Figure 13. Graph of the vertical reflection of the square root function. Figure 13, vertical reflection of the square root function, because each output value is the opposite of the original output value. We can write letter 1 D449, letter 1 D461, equals minus letter 1 D460, letter 1 D461, or letter 1 D449, letter 1 D461, equals minus letter 1d461 square root. Notice that this is an outside change, or vertical shift, that affects the output letter 1d460, letter 1d461 values, so the negative sign belongs outside of the function. B reflecting horizontally means that each input value will be reflected over the vertical axis, as shown in Figure 14. Graph of the horizontal reflection of the square root function. Figure 14 horizontal reflection of the square root function. Because each input value is the opposite of the original input value, we can write letter 1d43b, letter 1d461 equals letter 1d460, minus letter 1d461, or letter 1d43b, letter 1d461, equals minus letter 1d461 square. Notice that this is an inside change or horizontal change that affects the input values, so the negative sign is on the inside of the function. Note that these transformations can affect the domain and range of the functions, while the original square root function has domain 0 infinity and range 0 infinity. The vertical reflection gives the letter 1d449, letter 1d461, function the range minus infinity 0, and the horizontal reflection gives the letter 1d43b, letter 1d461, function the domain minus infinity 0. Try it 5. Reflect the graph of letter 1d453, letter 1d465, equals letter 1d465 minus 1. A vertically and B horizontally. Example 10. Reflecting a tabular function horizontally and vertically. A function letter 1d453, letter 1d465, is given as table 6. Create a table for the functions below. A letter 1d454, letter 1d465, equals minus letter 1d453, letter 1d465. B letter 210e, letter 1d465 equals letter 1d453 minus letter 1d465. X 2468, letter 1d453, letter 1d465. 13711. Table 6. Solution. For letter 1d454, letter 1d465, the negative sign outside the function indicates a vertical reflection, so the x values stay the same and each output value will be the opposite of the original output value. See Table 7. X 2468, letter 1d454, letter 1d465. 13711. Table 7. B. For letter 210e, letter 1d465, the negative sign inside the function indicates a horizontal reflection, so each input value will be the opposite of the original input value, and the letter 210e, letter 1d465, values stay the same as the letter 1d453, letter 1d465. Values. See Table 8, x, minus 2 minus 4 minus 6 minus 8, letter 210e, letter 1d465. 13711. Table 8. Try it 6. A function letter 1d453, letter 1d465, is given as Table 9. Create a table for the functions below. A letter 1d454, letter 1d465, equals minus letter 1d453, letter 1d465. B letter 210e, letter 1d465 equals letter 1d453 minus letter 1d465. X minus 2024, letter 1d453, letter 1d465. 5, 10, 15, 20. Table 9. Example 11. Applying a learning model equation. A common model for learning has an equation similar to letter 1d458. Letter 1d461 equals minus 2 minus letter 1d461 plus 1, where letter 1d458 is the percentage of mastery that can be achieved after letter 1d461. Practice sessions. This is a transformation of the function letter 1d453, letter 1d461 equals 2 letter 1d461, shown in Figure 15. Sketch a graph of letter 1d458, letter 1d461. Graph of KT. Figure 15. Solution. This equation combines three transformations into one equation. A horizontal reflection, letter 1d453 minus letter 1d461 equals 2 minus letter 1d461. A vertical reflection, minus letter 1d453 minus letter 1d461 equals minus 2 minus letter 1d461. A vertical shift, minus letter 1d453 minus letter 1 d461 plus 1 equals minus 2 minus letter 1 d461 plus 1. We can sketch a graph by applying these transformations one at a time to the original function. Let us follow 2 points through each of the 3 transformations. We will choose the points 0, 1, and 1, 2. First, we apply a horizontal reflection, 0, 1, 1, 2. Then, we apply a vertical reflection, 0, minus 1, minus 1, 2. Finally, we apply a vertical shift, 0, 0, minus 1, minus 1. This means that the original points 1 and 12 become 0 and minus 1, 1 after we apply the transformations. In Figure 16, the first graph results from a horizontal reflection. The second results from a vertical reflection. The third results from a vertical shift up 1 unit. Graphs of all the transformations. Figure 16. Analysis. As a model for learning, this function would be limited to a domain of letter 1 d461 greater or equal to 0, with corresponding range 0, 1. Try it 7. Given the toolkit function letter 1 d453, letter 1 d465 equals letter 1 d465 2. Graph letter 1 d454, letter 1 d465 equals minus letter 1 d453 letter 1 d465, and letter 210e. Letter 1 d465 equals letter 1 d453 minus letter 1 d465. Take note of any surprising behavior for these functions. Determining even and odd functions. Some functions exhibit symmetry, so that reflections result in the original graph. For example, horizontally reflecting the toolkit functions letter 1 d453, letter 1 d465 equals letter 1 d465 2, or letter 1 d453, letter 1 d465 equals letter 1 d465, will result in the original graph. We say that these types of graphs are symmetric about the y-axis. A function whose graph is symmetric about the y-axis is called an even function. If the graphs of letter 1 d453, letter 1 d465 equals letter 1 d465 3, or letter 1 d453, letter 1 d465 equals 1 letter 1 d465, were reflected over both axes, the result would be the original graph, as shown in Figure 17. Graph of x3 and its reflections. Figure 17, A, the cubic toolkit function, B, horizontal reflection of the cubic toolkit function, C, horizontal and vertical reflections reproduce the original cubic function. We say that these graphs are symmetric about the origin. A function with a graph that is symmetric about the origin is called an odd function. Note, a function can be neither even nor odd if it does not exhibit either symmetry. For example, letter 1 d453, letter 1 d465 equals 2 letter 1 d465, is neither even nor odd. Also, the only function that is both even and odd is the constant function letter 1 d453, letter 1 d465 equals 0. Even and odd functions. A function is called an even function if, for every input letter 1 d465, letter 1 d453, letter 1 d465 equals letter 1 d453 minus letter 1 d465. The graph of an even function is symmetric about the letter 1 d466. Axis. A function is called an odd function if for every input letter 1 d465, letter 1 d453, letter 1 d465 equals minus letter 1 d453 minus letter 1 d465. The graph of an odd function is symmetric about the origin. How to? Given the formula for a function, determine if the function is even, odd, or neither. Determine whether the function satisfies letter 1 d453, letter 1 d465 equals letter 1 d453 minus letter 1 d465. If it does, it is even. Determine whether the function satisfies letter 1 d453, letter 1 d465 equals minus letter 1 d453 minus letter 1 d465. If it does, it is odd. If the function does not satisfy either rule, it is neither even nor odd. Example 12. Determining whether a function is even, odd, or neither. Is the function letter 1 d453, letter 1 d465 equals letter 1 d465 3 plus 2 letter 1 d465, even, odd, or neither? Solution. Without looking at a graph, we can determine whether the function is even or odd by finding formulas for the reflections and determining if they return us to the original function. Let's begin with the rule for even functions. letter 1d453 minus letter 1d465 equals minus letter 1d465 3 plus 2 minus letter 1d465 equals minus letter 1d465 3 minus 2 letter 1d465. This does not return us to the original function, so this function is not even. We can now test the rule for odd functions. Minus letter 1d453 minus letter 1d465 equals minus letter 1d465 3 minus 2 letter 1d465 equals letter 1d465 3 plus 2 letter 1d465. Because minus letter 1d453 minus letter 1d465 equals letter 1d453 letter 1d465. This is an odd function. Analysis. Consider the graph of letter 1d453. In figure 18, notice that the graph is symmetric about the origin for every point xy. On the graph, the corresponding point, minus letter 1d465, minus letter 1d466, is also on the graph. For example, 1, 3 is on the graph of letter 1d453, and the corresponding point, minus 1, minus 3, is also on the graph. Graph of fx with labeled points at 1, 3, and minus 1. Figure 18. Try at 8. Is the function letter 1d453. Letter 1d460 equals letter 1d460, 4 plus 3 letter 1d460, 2 plus 7. Even, odd, or neither. Graphing functions using stretches and compressions. Adding a constant to the inputs or outputs of a function changed the position of a graph with respect to the axes, but it did not affect the shape of a graph. We now explore the effects of multiplying the inputs or outputs by some quantity. We can transform the inside, input values, of a function, or we can transform the outside, output values, of a function. Each change has a specific effect that can be seen graphically. Vertical stretches and compressions. When we multiply a function by a positive constant, we get a function whose graph is stretched or compressed vertically in relation to the graph of the original function. If the constant is greater than 1, we get a vertical stretch. If the constant is between 0 and 1, we get a vertical compression. Figure 19 shows a function multiplied by constant factors 2 and 0, 5, and the resulting vertical stretch and compression. Graph of a function that shows vertical stretching and compression. Figure 19 vertical stretch and compression. Vertical stretches and compressions. Given a function letter 1d453, letter 1d465, a new function letter 1d454. Letter 1d465 equals letter 1d44 letter 1d453, letter 1d465, where letter 1d44 is a constant, is a vertical stretch or vertical compression of the function letter 1d453, letter 1d465. If letter 1d44 then the graph will be stretched. If 0 letter 1d44 then the graph will be compressed. If letter 1d44 then there will be combination of a vertical stretch or compression with a vertical reflection. How to, given a function, graph its vertical stretch. Identify the value of multiply all range values by, if letter 1d441, the graph is stretched by a factor of letter 1d440. If 0 letter 1d441, the graph is compressed by a factor of, if letter 1d440, the graph is either stretched or compressed and also reflected about the x-axis. Example 13. Graphing a vertical stretch. A function letter 1d443, letter 1d461, models the population of fruit flies. The graph is shown in figure 20. Graph to represent the growth of the population of fruit flies. Figure 20. A scientist is comparing this population to another population, letter 1d444, whose growth follows the same pattern but is twice as large. Sketch a graph of this population. Solution. Because the population is always twice as large, the new population's output values are always twice the original function's output values. Graphically, this is shown in figure 21. If we choose 4 reference points, 0, 1, 3, 3, 6, 2, and 7, 0, we will multiply all of the outputs by 2. The following shows where the new points for the new graph will be located. 0, 1, right arrow 0, 2, 3, 3, right arrow 3, 6, 6, 2, right arrow 6, 4, 7, 0, right arrow 7, 0. Graph of the population function doubled. Figure 21. Symbolically, the relationship is written as letter 1d444, letter 1d461 equals 2 letter 1d443, letter 1d461. This means that, for any input letter 1d461, the value of the function letter 1d444 is twice the value of the function letter 1d443. Notice that the effect on the graph is a vertical stretching of the graph, where every point doubles its distance from the horizontal axis. The input values, letter 1d461, stay the same while the output values are twice as large as before. How to? Given a tabular function and assuming that the transformation is a vertical stretch or compression, create a table for a vertical compression. Determine the value of letter 1d44e. Multiply all of the output values by example 14, finding a vertical compression of a tabular function. A function, letter 1d453, is given as table 10. Create a table for the function letter 1d454. Letter 1d465 equals 12 letter 1d453, letter 1d465. X, 2468. Letter 1d453, letter 1d465. 13711. Table 10. Solution. The formula letter 1d454, letter 1d465 equals 12 letter 1d453, letter 1d465, tells us that the output values of letter 1d454 are half of the output values of letter 1d453 with the same inputs. For example, we know that letter 1d453, 4 equals 3. Then, letter 1d454, 4 equals 12 letter 1d453, 4 equals 12, 3 equals 32. We do the same for the other values to produce table 11. X, 2, 4, 6, 8, letter 1d454, letter 1d465, 12, 32, 72, 112. Table 11. Analysis. The result is that the function letter 1d454, letter 1d465, has been compressed vertically by 12. Each output value is divided in half, so the graph is half the original height. Try it 9. A function, letter 1d453, is given as table 12. Create a table for the function letter 1d454, letter 1d465 equals 34 letter 1d453, letter 1d465. X, 2468. Letter 1d453, letter 1d465, 12, 16, 20, 0. Table 12. Example 15. Recognizing a vertical stretch. The graph in figure 22 is a transformation of the toolkit function letter 1d453, letter 1d465 equals letter 1d4653. Relate this new function letter 1d454, letter 1d465 to letter 1d453, letter 1d465, and then find a formula for letter 1d454, letter 1d465. Graph of a transformation of f x equals x3, figure 22. Solution. When trying to determine a vertical stretch or shift, it is helpful to look for a point on the graph that is relatively clear. In this graph, it appears that letter 1d454, 2 equals 2. With the basic cubic function at the same input, letter 1d4532 equals 23 equals 8. Based on that, it appears that the outputs of letter 1d454 are 14. The outputs of the function letter 1d453. Because letter 1d454, 2 equals 14 letter 1d453, 2. From this, we can fairly safely conclude that letter 1d454, letter 1d465 equals 14 letter 1d453, letter 1d465. We can write a formula for letter 1d454 by using the definition of the function letter 1d453. Letter 1d454, letter 1d465 equals 14 letter 1d453, letter 1d465 equals 14 letter 1d4653. Try it 10. Write the formula for the function that we get when we stretch the identity toolkit function by a factor of 3, and then shift it down by 2 units. Horizontal stretches and compressions. Now we consider changes to the inside of a function. When we multiply a function's input by a positive constant, we get a function whose graph is stretched or compressed horizontally in relation to the graph of the original function. If the constant is between 0 and 1, we get a horizontal stretch. If the constant is greater than 1, we get a horizontal compression of the function. Graph of the vertical stretch and compression of x2. Figure 23, given a function letter 1d466 equals letter 1d453, letter 1d465. The form letter 1d466 equals letter 1d453, letter 1d44f letter 1d465 results in a horizontal stretch or compression. Consider the function letter 1d466 equals letter 1d4652. Observe figure 23. The graph of letter 1d466 equals 0. 5 letter 1d465, 2, is a horizontal stretch of the graph of the function letter 1d466 equals letter 1d4652 by a factor of 2. The graph of letter 1d466 equals 2 letter 1d465, 2 is a horizontal compression of the graph of the function letter 1d466 equals letter 1d4652 by a factor of 12. Horizontal stretches and compressions given a function letter 1d453, letter 1d465, a new function letter 1d454, letter 1d465 equals letter 1d453, letter 1d44f letter 1d465, where b is a constant, is a horizontal stretch or horizontal compression of the function letter 1d453, letter 1d465. If letter 1d44f1, then the graph will be compressed by b. If 0 letter 1d44f1, then the graph will be stretched by 1b. If letter 1d44f0, then there will be combination of a horizontal stretch or compression with a horizontal reflection. How to give in a description of a function, sketch a horizontal compression or stretch. Write a formula to represent the function. Set letter 1d454, letter 1d465 equals letter 1d453, letter 1d44f letter 1d465, where letter 1d44f 1 for a compression or 0 letter 1d44f 1 for a stretch. Example 16, graphing a horizontal compression. Suppose a scientist is comparing a population of fruit flies to a population that progresses through its lifespan twice as fast as the original population. In other words, this new population, R, will progress in 1 hour the same amount as the original population does in 2 hours, and in 2 hours, it will progress as much as the original population does in 4 hours. Sketch a graph of this population. Solution symbolically, we could write letter 1d445, 1 letter 1d445, 2, letter 1d445, letter 1d461 equals letter 1d4432, letter 1d4434, and in general, letter 1d443, 2 letter 1d461. See figure 24 for a graphical comparison of the original population and the compressed population. 2 side-by-side graphs. The first graph has function for original population whose domain is 0, 7, and range is 0, 3. The maximum value occurs at 33. The second graph has the same shape as the first except it is half as wide. It is a graph of transformed population with a domain of 0, 3, 5, and a range of 0, 3. The maximum occurs at 1, 5, 3. Figure 24, A. Original population graph. B. Compressed population graph analysis. Note that the effect on the graph is a horizontal compression, where all input values are half of their original distance from the vertical axis. Example 17, finding a horizontal stretch for a tabular function, a function letter 1d453, letter 1d465, is given as table 13. Create a table for the function letter 1d454, letter 1d465 equals letter 1d453, 12 letter 1d465, x2468 letter 1d453, letter 1d465. 13711 table 13 solution, the formula letter 1d454, letter 1d465, equals letter 1d453, 12 letter 1d465, tells us that the output values for g are the same as the output values for the function f at an input half the size. Notice that we do not have enough information to determine letter 1d454, 2, because letter 1d454, 2 equals letter 1d453, 12, 2 equals letter 1d453, 1, and we do not have a value for letter 1d453, 1, in our table. Our input values to g will need to be twice as large to get inputs for f that we can evaluate. For example, we can determine letter 1d454, 4. Letter 1d454, 4, equals letter 1d453, 12.4 equals letter 1d453, 2 equals 1. We do the same for the other values to produce table 14. X 4, 8, 12, 16, letter 1d454, letter 1d465, 1, 3, 7, 11. Table 14 figure 25 shows the graphs of both of these sets of points. Graph of the previous table. Figure 25 analysis. Because each input value has been doubled, the result is that the function letter 1d454, letter 1d465 has been stretched horizontally by a factor of 2. Example 18, recognizing a horizontal compression on a graph, relate the function letter 1d454, letter 1d465, to letter 1d453, letter 1d465, in figure 26. Graph of f, x being vertically compressed to g, x. Figure 26 solution. The graph of letter 1d454, letter 1d465, looks like the graph of letter 1d453, letter 1d465, horizontally compressed. Because letter 1d453, letter 1d465, ends at 64 and letter 1d454, letter 1d465, ends at 24, we can see that the x values have been compressed by 13 because 6, 13 equals 2. We might also notice that letter 1d454, 2 equals letter 1d453, 6, and letter 1d454, 1 equals letter 1d453, 3. Either way, we can describe this relationship as letter 1d454, letter 1d465 equals letter 1d453, 3 letter 1d465. This is a horizontal compression by 13. Analysis. Notice that the coefficient needed for a horizontal stretch or compression is the reciprocal of the stretch or compression. So to stretch the graph horizontally by a scale factor of 4, we need a coefficient of 14 in our function. Letter 1d453, 14 letter 1d465. This means that the input values must be 4 times larger to produce the same result, requiring the input to be larger, causing the horizontal stretching. Try it 11. Write a formula for the toolkit square root function horizontally stretched by a factor of 3. Performing a sequence of transformations. When combining transformations, it is very important to consider the order of the transformations. For example, vertically shifting by 3 and then vertically stretching by 2 does not create the same graph as vertically stretching by 2 and then vertically shifting by 3. Because when we shift first, both the original function and the shift get stretched, while only the original function gets stretched when we stretch first. When we see an expression such as 2 letter 1d453, letter 1d465, plus 3, which transformation should we start with? The answer here follows nicely from the order of operations. Given the output value of letter 1d453, letter 1d465, we first multiply by 2, causing the vertical stretch, and then add 3, causing the vertical shift. In other words, multiplication before addition. Horizontal transformations are a little trickier to think about. When we write letter 1d454, letter 1d465 equals letter 1d453, 2 letter 1d465 plus 3. For example, we have to think about how the inputs to the function g relate to the inputs to the function f. Suppose we know letter 1d453, 7 equals 12. What input to g would produce that output? In other words, what value of x will allow letter 1d454, letter 1d465 equals letter 1d453, 2 letter 1d465 plus 3 equals 12. We would need 2 letter 1d465 plus 3 equals 7. To solve for x, we would first subtract 3, resulting in a horizontal shift, and then divide by 2, causing a horizontal compression. This format ends up being very difficult to work with, because it is usually much easier to horizontally stretch a graph before shifting. We can work around this by factoring inside the function. Letter 1d453, letter 1d44f, letter 1d465, plus letter 1d45d equals letter 1d453, letter 1d44f, letter 1d465, plus letter 1d45d, letter 1d44f. Let's work through an example. Letter 1d453, letter 1d465 equals 2 letter 1d465 plus 4, 2. We can factor out a 2. Letter 1d453, letter 1d465 equals 2 letter 1d465 plus 2. 2 now we can more clearly observe a horizontal shift to the left 2 units and a horizontal compression. Factoring in this way allows us to horizontally stretch first and then shift horizontally. Combining transformations when combining vertical transformations written in the form letter 1d44 letter 1d453, letter 1d465, plus letter 1d458, first vertically stretch by A and then vertically shift by K. When combining horizontal transformations written in the form letter 1d453, letter 1d44f letter 1d465 minus letter 210e. First horizontally shift by H and then horizontally stretch by 1b. When combining horizontal transformations written in the form letter 1d453, letter 1d44f, letter 1d465 minus letter 210e. First horizontally stretch by 1b and then horizontally shift by H. Horizontal and vertical transformations are independent. It does not matter whether horizontal or vertical transformations are performed first. Example 19, finding a triple transformation of a tabular function given table 15 for the function letter 1d453, letter 1d465. Create a table of values for the function letter 1d454 letter 1d465 equals 2 letter 1d453, 3 letter 1d465, plus 1. x6 12 18 24 letter 1d453, letter 1d465, 10 14 15 17 table 15 solution. There are 3 steps to this transformation, and we will work from the inside out. Starting with the horizontal transformations, letter 1d453, 3 letter 1d465 is a horizontal compression by 13, which means we multiply each x value by 13. See table 16. x2 4 6 8 letter 1d453, 3 letter 1d465, 10 14 15 17 table 16. Looking now to the vertical transformations, we start with the vertical stretch, which will multiply the output values by 2. We apply this to the previous transformation. See table 17. x2 4 6 8 2 letter 1d453, 3 letter 1d465, 20 28 30 34 table 17. Finally, we can apply the vertical shift, which will add 1 to all the output values. See table 18. x2 4 6 8 letter 1d454, letter 1d465, equals 2 letter 1d453, 3 letter 1d465, plus 121 29 30 135 table 18. Example 20, finding a triple transformation of a graph. Use the graph of letter 1d453, letter 1d465, in figure 27 to sketch a graph of letter 1d458, letter 1d465 equals letter 1d453, 12 letter 1d465 plus 1 minus 3. Graph of a half circle. Figure 27 solution. To simplify, let's start by factoring out the inside of the function. Letter 1d453, 12 letter 1d465 plus 1 minus 3 equals letter 1d453, 12 letter 1d465 plus 2, minus 3. By factoring the inside, we can first horizontally stretch by 2, as indicated by the 12 on the inside of the function. Remember that twice the size of 0 is still 0, so the point 2 remains at 2, while the point 20 will stretch to 40. See figure 28. Graph of a vertically stretched half circle. Figure 28. Next, we horizontally shift left by 2 units, as indicated by x plus 2. See figure 29. Graph of a vertically stretched and translated half circle. Figure 29. Last, we vertically shift down by 3 to complete our sketch, as indicated by the minus 3 on the outside of the function. See figure 30. Graph of a vertically stretched and translated half circle. Figure 30. Media. Access this online resource for additional instruction and practice with transformation of functions. Function transformations 3-5 section, exercises verbal 1. When examining the formula of a function that is the result of multiple transformations, how can you tell a horizontal shift from a vertical shift? 2. When examining the formula of a function that is the result of multiple transformations, how can you tell a horizontal stretch from a vertical stretch? 3. When examining the formula of a function that is the result of multiple transformations, how can you tell a horizontal compression from a vertical compression? 4. When examining the formula of a function that is the result of multiple transformations, How can you tell a reflection with respect to the x-axis from a reflection with respect to the y-axis? 5. How can you determine whether a function is odd or even from the formula of the function? Algebraic for the following exercises, write a formula for the function obtained when the graph is shifted as described. 6. Is shifted up 1 unit and to the left 2 units. 7. Letter 1 D453, letter 1 D465, equals letter 1 D465 is shifted down 3 units and to the right 1 unit. 8. Letter 1 D453, letter 1 D465, equals 1 letter 1 D465 is shifted down 4 units and to the right 3 units. 9. Letter 1 D453, letter 1 D465, equals 1 letter 1 D4652 is shifted up 2 units and to the left 4 units. For the following exercises, describe how the graph of the function is a transformation of the graph of the original function, f. 10. Letter 1 D466 equals letter 1 D453, letter 1 D465 minus 49, 11. Letter 1 D466 equals letter 1 D453, letter 1 D465 plus 43, 12. Letter 1 D466 equals letter 1 D453, letter 1 D465 plus 3, 13. Letter 1 D466 equals letter 1 D453, letter 1 D465 minus 4, 14. Letter 1 D466 equals letter 1 D453, letter 1 D465, plus 5, 15. Letter 1 D466 equals letter 1 D453, letter 1 D465, plus 8, 16. Letter 1 D466 equals letter 1 D453, letter 1 D465, minus 2, 17. Letter 1 D466 equals letter 1 D453, letter 1 D465 minus 7, 18. Letter 1 D466 equals letter 1 D453, letter 1 D465 minus 2 plus 3, 19. For the following exercises, determine the interval, s, on which the function is increasing and decreasing. 20. Letter 1 D453, letter 1 D465, equals 4 letter 1 D465 plus 1 2 minus 521. Letter 1 D454, letter 1 D465 equals 5, letter 1 D465 plus 3 2 minus 222. Letter 1 D440, letter 1 D465, equals minus letter 1 D465 plus 4 square 23. Letter 1 D458, letter 1 D465, equals minus 3 letter 1 D465 square minus 1 graphical for the following exercises. Use the graph of letter 1 D453, letter 1 D465, equals 2 letter 1 D465 shown in figure 31 to sketch a graph of each transformation of letter 1 D453, letter 1 D465. Graph of f, x. Figure 3124. Letter 1 D454, letter 1 D465, equals 2 letter 1 D465 plus 125. Letter 210e, letter 1 D465, equals 2 letter 1 D465 minus 326. Letter 1 D464, letter 1 D465, equals 2 letter 1 D465 minus 1 for the following exercises. Sketch a graph of the function as a transformation of the graph of one of the toolkit functions. 27. Letter 1 D453, letter 1 D461 equals letter 1 D461 plus 1 2 minus 328. Letter 210e, letter 1 D465 equals letter 1 D465 minus 1 plus 429. Letter 1 D458, letter 1 D465 equals letter 1 D465 minus 2, 3 minus 130. Numeric 31. Tabular representations for the functions fg and h are given below. Write letter 1 D454, letter 1 D465, and letter 210e, letter 1 D465, as transformations of letter 1 D453, letter 1 D465. X minus 2 minus 1012, letter 1 D453, letter 1 D465, minus 2 minus 1 minus 312x minus 10123, letter 1 D454, letter 1 D465, minus 2 minus 1 minus 312x minus 2 minus 1012, letter 210e, letter 1 D465, minus 10 minus 22332. Tabular representations for the functions fg and h are given below. Write letter 1 D454, letter 1 D465, and letter 210e, letter 1 D465, as transformations of letter 1d453 letter 1d465. X minus 2 minus 1 0 1 2 letter 1d453. Letter 1d465. Minus 1 minus 3 4 2 1 x minus 3 minus 2 minus 1 0 1 letter 1d454. Letter 1d465. Minus 1 minus 3 4 2 1 x minus 2 minus 1 0 1 2 letter 210 e. Letter 1d465. Minus 2 minus 4 3 1 0 for the following exercises. Write an equation for each graphed function by using transformations of the graphs of one of the toolkit functions. 33. Graph of an absolute function. 34. Graph of a parabola. 35. Graph of a square root function. 36. Graph of an absolute function. 37. Graph of a parabola. 38. Graph of a square root function. 39. Graph of an absolute function. 40. Graph of a square root function. For the following exercises, use the graphs of transformations of the square root function to find a formula for each of the functions. 41. Graph of a square root function. 42. Graph of a square root function. For the following exercises, use the graphs of the transformed toolkit functions to write a formula for each of the resulting functions. 43. Graph of a parabola. 44. Graph of a cubic function. 45. Graph of a square root function. 46. Graph of an absolute function. For the following exercises, determine whether the function is odd, even, or neither. 47. Letter 1d453, letter 1d465 equals 3 letter 1d465 448. Letter 1d454, letter 1d465 equals letter 1d465 square 49. Letter 210e. Letter 1d465 equals 1 letter 1d465 plus 3 letter 1d465 50. Letter 1d453, letter 1d465 equals letter 1d465 minus 2 251. Letter 1d454, letter 1d465 equals 2 letter 1d465 452. Letter 210e, letter 1d465 equals 2 letter 1d465 minus letter 1d465 3 for the following exercises. Describe how the graph of each function is a transformation of the graph of the original function f. 53. Letter 1d454, letter 1d465 equals minus letter 1d453, letter 1d465. 54. Letter 1d454, letter 1d465 equals letter 1d453 minus letter 1d465, 55. Letter 1d454, letter 1d465 equals 4 letter 1d453, letter 1d465, 56. Letter 1d454, letter 1d465 equals 6 letter 1d453, letter 1d465, 57. Letter 1d454, letter 1d465 equals letter 1d453, 5 letter 1d465, 58. Letter 1d454, letter 1d465 equals letter 1d453, 2 letter 1d465, 59. Letter 1d454, letter 1d465 equals letter 1d453, 13 letter 1d465, 60. Letter 1d454, letter 1d465 equals letter 1d453, 15 letter 1d465, 61. Letter 1d454, letter 1d465 equals 3 letter 1d453 minus letter 1d465, 62. Letter 1d454, letter 1d465 equals minus letter 1d453, 3 letter 1d465. For the following exercises, write a formula for the function g that results when the graph of a given toolkit function is transformed as described. 63. The graph of letter 1d453, letter 1d465 equals letter 1d465 is reflected over the y-axis and horizontally compressed by a factor of 14. 64. The graph of letter 1d453, letter 1d465 equals letter 1d465 square is reflected over the x-axis and horizontally stretched by a factor of 2. 65. The graph of letter 1d453, letter 1d465 equals 1 letter 1d465 2 is vertically compressed by a factor of 13, then shifted to the left 2 units and down 3 units. 66. The graph of letter 1d453, letter 1d465 equals 1 letter 1d465 is vertically stretched by a factor of 8, then shifted to the right 4 units and up 2 units. 67. The graph of letter 1d453, letter 1d465, equals letter 1d4652 is vertically compressed by a factor of 12, then shifted to the right 5 units and up 1 unit. 68. The graph of letter 1d453, letter 1d465, equals letter 1d4652 is horizontally stretched by a factor of 3, then shifted to the left 4 units and down 3 units. For the following exercises, describe how the formula is a transformation of a toolkit function. Then sketch a graph of the transformation. 69. Letter 1d454, letter 1d465 equals 4 letter 1d465 plus 1 2 minus 570. Letter 1d454, letter 1d465 equals 5, letter 1d465 plus 3 2 minus 271. Letter 210e, letter 1d465 equals minus 2 letter 1d465 minus 4 plus 372. Letter 1d458, letter 1d465 equals minus 3 letter 1d465 square minus 173. Letter 1d45a, letter 1d465 equals 12 letter 1d465 374. Letter 1d45b, letter 1d465 equals 13 letter 1d465 minus 275. Letter 1d45d, letter 1d465 equals 13 letter 1d465 3 minus 376. Letter 1d45e, letter 1d465 equals 14 letter 1d465 3 plus 177. Letter 1d44e, letter 1d465 equals minus letter 1d465 plus 4 square. For the following exercises, use the graph in figure 32 to sketch the given transformations. Graph of a polynomial. Figure 3278. Letter 1d454, letter 1d465 equals letter 1d453, letter 1d465, minus 279. Letter 1d454, letter 1d465 equals minus letter 1d453, letter 1d465, 80. Letter 1d454, letter 1d465 equals letter 1d453, letter 1d465 plus 1, 81. Letter 1d454, letter 1d465 equals letter 1d453, letter 1d465 minus 2. Learning objectives. In this section, you will graph an absolute value function, solve an absolute value equation, the Milky Way. Figure 1 distances in deep space can be measured in all directions. As such, it is useful to consider distance in terms of absolute values. Credit S58Y/Flickr. Until the 1920s, the so-called spiral nebulae were believed to be clouds of dust and gas in our own galaxy, some tens of thousands of light-years away. Then, astronomer Edwin Hubble proved that these objects are galaxies in their own right, at distances of millions of light-years. Today, astronomers can detect galaxies that are billions of light-years away. Distances in the universe can be measured in all directions. As such, it is useful to consider distance as an absolute value function. In this section, we will continue our investigation of absolute value functions, understanding absolute value. Recall that in its basic form, letter 1d453, letter 1d465 equals letter 1d465. The absolute value function is one of our toolkit functions. The absolute value function is commonly thought of as providing the distance the number is from 0 on a number line. Algebraically, for whatever the input value is, the output is the value without regard to sign. Knowing this, we can use absolute value functions to solve some kinds of real-world problems. Absolute value function. The absolute value function can be defined as a piecewise function. Letter 1d453, letter 1d465 equals letter 1d465 equals letter 1d465 minus letter 1d465, if, letter 1d465 greater or equal to 0, letter 1d465 0. Example 1. Using absolute value to determine resistance. Electrical parts, such as resistors and capacitors, come with specified values of their operating parameters. Resistance, capacitance, etc. However, due to imprecision in manufacturing, the actual values of these parameters vary somewhat from piece to piece, even when they are supposed to be the same. The best that manufacturers can do is to try to guarantee that the variations will stay within a specified range, often plus or minus 1%, plus or minus 5%, or plus or minus 10%. Suppose we have a resistor rated at 680 ohms, plus or minus 5%. Use the absolute value function to express the range of possible values of the actual resistance. Solution: we can find that 5% of 680 ohms is 34 ohms. The absolute value of the difference between the actual and nominal resistance should not exceed the stated variability. So, with the resistance R. In ohms, letter 1 D445 minus 680 less 34. Try it 1. Students who score within 20 points of 80 will pass a test. Write this as a distance from 80 using absolute value notation. Graphing an absolute value function. The most significant feature of the absolute value graph is the corner point at which the graph changes direction. This point is shown at the origin in Figure 2, graph of an absolute function. Figure 2. Figure 3 shows the graph of letter 1D466 equals 2 letter 1D465 3 plus 4. The graph of letter 1D466 equals letter 1D465 has been shifted right 3 units, vertically stretched by a factor of 2, and shifted up 4 units. This means that the corner point is located at 34. For this transformed function, graph of the different types of transformations for an absolute function. Figure 3. Example 2. Writing an equation for an absolute value function given a graph. Write an equation for the function graphed in Figure 4. Graph of an absolute function. Figure 4. Solution: the basic absolute value function changes direction at the origin. So this graph has been shifted to the right 3 units and down 2 units from the basic toolkit function. See Figure 5. Graph of 2 transformations for an absolute function at 3 minus 2. Figure 5. We also notice that the graph appears vertically stretched, because the width of the final graph on a horizontal line is not equal to 2 times the vertical distance from the corner to this line, as it would be for an unstretched absolute value function. Instead, the width is equal to 1 times the vertical distance, as shown in Figure 6. Graph of 2 transformations for an absolute function at 3 minus 2 and describes the ratios between the 2 different transformations. Figure 6. From this information, we can write the equation. Letter 1D453, letter 1D465, letter 1D453, letter 1D465 equals 2 letter 1D465 minus 3 minus 2. 2 letter 1D465 minus 3 minus 2, treating the stretch as letter 1D44 vertical stretch, or treating the stretch as letter 1D44 horizontal compression. Analysis. Note that these equations are algebraically equivalent. The stretch for an absolute value function can be written interchangeably as a vertical or horizontal stretch or compression. Note also that if the vertical stretch factor is negative, there is also a reflection about the x-axis, Q and A. If we couldn't observe the stretch of the function from the graphs, could we algebraically determine it? Yes. If we are unable to determine the stretch based on the width of the graph, we can solve for the stretch factor by putting in a known pair of values for x, and letter 1D453, letter 1D465, letter 1D453, letter 1D465 equals letter 1D44, letter 1D465 minus 3 minus 2. Now substituting in the point 1, 2, 24 letter 1D44 equals letter 1D44, 1 minus 3 minus 22 letter 1D442. Try it 2. Write the equation for the absolute value function that is horizontally shifted left 2 units, is vertically reflected, and vertically shifted up 3 units. Q and A. Do the graphs of absolute value functions always intersect the vertical axis, the horizontal axis? Yes, they always intersect the vertical axis. The graph of an absolute value function will intersect the vertical axis when the input is 0. No, they do not always intersect the horizontal axis. The graph may or may not intersect the horizontal axis, depending on how the graph has been shifted and reflected. It is possible for the absolute value function to intersect the horizontal axis at 0, 1, or 2 points. See Figure 7. Graph of the different types of transformations for an absolute function. Figure 7a the absolute value function does not intersect the horizontal axis. B. The absolute value function intersects the horizontal axis at one point. C. The absolute value function intersects the horizontal axis at 2 points. Solving an absolute value equation. In other type of equations, we touched on the concepts of absolute value equations. Now that we understand a little more about their graphs, we can take another look at these types of equations. Now that we can graph an absolute value function, we will learn how to solve an absolute value equation. To solve an equation such as 8 equals 2 letter 1d465 minus 6, we notice that the absolute value will be equal to 8 if the quantity inside the absolute value is 8 or minus 8. This leads to two different equations we can solve independently. 2 letter 1d465 minus 62 letter 1d465 letter 1d465 equals 8,147, or to letter 1d465 minus 62 letter 1d465 letter 1d465 equals minus 8 minus 2 minus 1. Knowing how to solve problems involving absolute value functions is useful. For example, we may need to identify numbers or points on a line that are at a specified distance from a given reference point. An absolute value equation is an equation in which the unknown variable appears in absolute value bars. For example, letter 1d465 equals 4, 2 letter 1d465 minus 1 equals 3, or 5 letter 1d465 plus 2 minus 4 equals 9. Solutions to absolute value equations. For real numbers a and b, an equation of the form letter 1d434 equals letter 1d435, with letter 1d435 greater or equal to 0. We'll have solutions when letter 1d434 equals letter 1d435, or letter 1d434 equals minus letter 1d435. If letter 1d435 0, the equation has no solution. How to? Given the formula for an absolute value function, find the horizontal intercepts of its graph. Isolate the absolute value term. Use letter 1d434 equals letter 1d435 to write letter 1d434 equals letter 1d435, or minus a equals letter 1d435, assuming letter 1d435 0. Solve for x example 3, finding the zeros of an absolute value function. For the function letter 1d453, letter 1d465 equals 4 letter 1d465 plus 1 minus 7. Find the values of x, such that letter 1d453, letter 1d465 equals 0. Solution: 0776 letter 1d465 equals 4 letter 1d465 plus 1 minus 7 4 letter 1d465 plus 1 4 letter 1d465 plus 14 letter 1d465 64 equals 1. 5 or minus 7 minus 8 letter 1d465 equals 4 letter 1d465 plus 14 letter 1d465 minus 80. 4 equals minus 2. Substitute 0 for letter 1d453. Letter 1d465. Isolate the absolute value on one side of the equation. Break into two separate equations and solve. The function outputs 0 when letter 1d465 equals 32, or letter 1d465 equals minus 2. See Figure 8. Graph an absolute function with x-intercepts at minus 2 and 1, 5. Figure 8. Try at 3. For the function letter 1d453, letter 1d465 equals 2 letter 1d465 minus 1 minus 3. Find the values of x, such that letter 1d453, letter 1d465 equals 0. Q&A. Should we always expect two answers when solving letter 1d434 equals letter 1d435? No. We may find 1, 2, or even no answers. For example, there is no solution to 2 plus 3 letter 1d465 minus 5 equals 1. Media. Access these online resources for additional instruction and practice with absolute value. Graphing absolute value functions. Graphing absolute value functions 2. 3-6 section exercises. Verbal. 1. How do you solve an absolute value equation? 2. How can you tell whether an absolute value function has two x-intercepts without graphing the function? 3. When solving an absolute value function, the isolated absolute value term is equal to a negative number. What does that tell you about the graph of the absolute value function? 4. How can you use the graph of an absolute value function to determine the x values for which the function values are negative? Algebraic. 5. Describe all numbers x that are at a distance of 4 from the number 8. Express this set of numbers using absolute value notation. 6. Describe all numbers x that are at a distance of 12 from the number -4. Express this set of numbers using absolute value notation. 7. Describe the situation in which the distance that point x is from 10 is at least 15 units. Express this set of numbers using absolute value notation. 8. Find all function values letter 1d453, letter 1d465, such that the distance from letter 1d453, letter 1d465, to the value 8 is less than 0, 3 units. Express this set of numbers using absolute value notation. For the following exercises, find the x and y intercepts of the graphs of each function. 9. Letter 1d453, letter 1d465 equals 4 letter 1d465 minus 3 plus 4. 10. Letter 1d453, letter 1d465 equals minus 3 letter 1d465 minus 2 minus 1. 11. Letter 1d453, letter 1d465 equals minus 2 letter 1d465 plus 1 plus 6. 12. Letter 1d453, letter 1d465 equals minus 5 letter 1d465 plus 2 plus 15. 13. Letter 1d453, letter 1d465 equals 2 letter 1d465 minus 1 minus 6. 14. Letter 1d453, letter 1d465 equals minus 2 letter 1d465 plus 1 minus 13. 15. Letter 1d453, letter 1d465 equals minus letter 1d465 minus 9 plus 16. Graphic. For the following exercises, graph the absolute value function. Plot at least 5 points by hand for each graph. 16. Letter 1d466 equals letter 1d465 minus 1. 17. Letter 1d466 equals letter 1d465 plus 1. 18. Letter 1d466 equals letter 1d465 plus 1. For the following exercises, graph the given functions by hand. 19. Letter 1d466 equals letter 1d465 minus 2. 20. Letter 1d466 equals minus letter 1d465. 21. Letter 1d466 equals minus letter 1d465 minus 2. 22. Letter 1d466 equals minus letter 1d465 minus 3 minus 2. 23. Letter 1d453, letter 1d465 equals minus letter 1d465 minus 1 minus 2. 24. Letter 1d453, letter 1d465 equals minus letter 1d465 plus 3 plus 4. 25. Letter 1d453, letter 1d465 equals 2 letter 1d465 plus 3 plus 1. 26. Letter 1d453, letter 1d465 equals 3 letter 1d465 minus 2 plus 3. 27. Letter 1d453, letter 1d465 equals 2 letter 1d465 minus 4 minus 3. 28. Letter 1d453, letter 1d465 equals 3 letter 1d465 plus 9 plus 2. 29. Letter 1d453, letter 1d465 equals minus letter 1d465 minus 1 minus 3. 30. Letter 1d453, letter 1d465 equals minus letter 1d465 plus 4 minus 3. 31. Letter 1d453, letter 1d465 equals 12 letter 1d465 plus 4 minus 3. Technology. 32. Use a graphing utility to graph letter 1d453, letter 1d465 equals 10 letter 1d465 minus 2. On the viewing window 04, identify the corresponding range, show the graph. 33. Use a graphing utility to graph letter 1d453, letter 1d465 equals minus 100 letter 1d465 plus 100. On the viewing window -5, identify the corresponding range, show the graph. For the following exercises, graph each function using a graphing utility. Specify the viewing window. 34. Letter 1d453, letter 1d465 equals minus 0, 1 0, 1 0, 2 minus letter 1d465 plus 0, 3. 35. Letter 1D453, letter 1D465, equals 4 times 109 letter 1D465 minus 5 times 109 plus 2 times 109. Extensions. For the following exercises, solve the inequality. 36. If possible, find all values of a, such that there are no x-intercepts for letter 1D453. Letter 1D465 equals 2 letter 1D465 plus 1 plus letter 1D440. 37. If possible, find all values of a, such that there are no y-intercepts for letter 1D453. Letter 1D465 equals 2 letter 1D465 plus 1 plus letter 1D440. Real-world applications. 38. Cities A and B are on the same east-west line. Assume that city A is located at the origin. If the distance from city A to city B is at least 100 miles and x represents the distance from city B to city A, express this using absolute value notation. 39. The true proportion P of people who give a favorable rating to Congress is 8% with a margin of error of 15%. Describe this statement using an absolute value equation. 40. Students who score within 18 points of the number 82 will pass a particular test. Write this statement using absolute value notation and use the variable x. For the score, 41. A machinist must produce a bearing that is within 0.1 inches of the correct diameter of 50 inches. Using x as the diameter of the bearing, write this statement using absolute value notation. 42. The tolerance for a ball bearing is 0.1. If the true diameter of the bearing is to be 20 inches and the measured value of the diameter is x inches, express the tolerance using absolute value notation. Learning objectives in this section, you will verify inverse functions. Determine the domain and range of an inverse function and restrict the domain of a function to make it one-to-one. Find or evaluate the inverse of a function. Use the graph of a one-to-one function to graph its inverse function on the same axes. A reversible heat pump is a climate control system that is an air conditioner and a heater in a single device. Operated in one direction, it pumps heat out of a house to provide cooling. Operating in reverse, it pumps heat into the building from the outside, even in cool weather, to provide heating. As a heater, a heat pump is several times more efficient than conventional electrical resistance heating. If some physical machines can run in two directions, we might ask whether some of the function machines we have been studying can also run backwards. Figure 1 provides a visual representation of this question. In this section, we will consider the reverse nature of functions. Diagram of a function and would be its inverse. Figure 1, can a function machine operate in reverse? Verifying that two functions are inverse functions, Betty is traveling to Milan for a fashion show and wants to know what the temperature will be. She is not familiar with the Celsius scale. To get an idea of how temperature measurements are related, Betty wants to convert 75 degrees Fahrenheit to degrees Celsius using the formula letter 1D436 equals 59, letter 1D439 minus 32, and substitute 75 for F to calculate 59. 75 minus 30 to approximately 24 degrees C, knowing that a comfortable 75 degrees Fahrenheit is about 24 degrees Celsius. Betty gets the week's weather forecast from Figure 2 for Milan and wants to convert all of the temperatures to degrees Fahrenheit, a forecast of Mondays through Thursdays weather. Figure 2, at first, Betty considers using the formula she has already found to complete the conversions. After all, she knows her algebra and can easily solve the equation for F after substituting a value for C. For example, to convert 26 degrees Celsius, she could write 2,626.95, letter 1D439 equals 59. Letter 1D439 minus 32, letter 1D439 minus 3,226.95, plus 32, approximately 79, after considering this option for a moment. However, she realizes that solving the equation for each of the temperatures will be awfully tedious. She realizes that since evaluation is easier than solving, it would be much more convenient to have a different formula, one that takes the Celsius temperature and outputs the Fahrenheit temperature. The formula for which Betty is searching corresponds to the idea of an inverse function. which is a function for which the input of the original function becomes the output of the inverse function, and the output of the original function becomes the input of the inverse function. Given a function letter 1d453, letter 1d465, we represent its inverse as letter 1d453 minus 1, letter 1d465, read as f inverse of x. The raised minus 1 is part of the notation. It is not an exponent. It does not imply a power of minus 1. In other words, letter 1d453 minus 1, letter 1d465 does not mean one letter 1d453, letter 1d465, because one letter 1d453, letter 1d465 is the reciprocal of f and not the inverse. The exponent-like notation comes from an analogy between function composition and multiplication. Just as letter 1d44e minus 1 letter 1d44e equals 1, 1 is the identity element for multiplication for any non-zero number a. So letter 1d453 minus 1 letter 1d453 equals the identity function. That is, letter 1d453 minus 1 letter 1d453. Letter 1d465 equals letter 1d453 minus 1, letter 1d453, letter 1d465. Equals letter 1d453 minus 1, letter 1d466 equals letter 1d465. This holds for all x in the domain of f. Informally, this means that inverse functions undo each other. However, just as 0 does not have a reciprocal, some functions do not have inverses. Given a function letter 1d453, letter 1d465, we can verify whether some other function letter 1d454, letter 1d465, is the inverse of letter 1d453, letter 1d465, by checking if both and are true. For example, letter 1d466 equals 4 letter 1d465, and letter 1d466 equals 14 letter 1d465 are inverse functions. Letter 1d453 minus 1 letter 1d453. Letter 1d465 equals letter 1d453 minus 1, 4 letter 1d465 equals 14, 4 letter 1d465 equals letter 1d465, and letter 1d453 letter 1d453 minus 1. Letter 1d465 equals letter 1d453. 14 letter 1d465 equals 4. 14 letter 1d465 equals letter 1d465 a few. Coordinate pairs from the graph of the function letter 1d466 equals 4 letter 1d465 are minus 2, minus 8, 0, 0, and 2, 8. A few coordinate pairs from the graph of the function letter 1d466 equals 14 letter 1d465 are minus 8, minus 2, 0, 0, and 8, 2. If we interchange the input and output of each coordinate pair of a function, the interchanged coordinate pairs would appear on the graph of the inverse function. Inverse function for any one-to-one function letter 1d453, letter 1d465 equals letter 1d466. A function letter 1d453 minus 1, letter 1d465 is an inverse function of f if. This can also be written as letter 1d453 minus 1, letter 1d453, letter 1d465 equals letter 1d465 for all x in the domain of f. It also follows that letter 1d453, letter 1d453 minus 1, letter 1d465 equals letter 1d465 for all x in the domain of letter 1d453 minus 1 if letter 1d453 minus 1 is the inverse of f. The notation letter 1d453 minus 1 is read f inverse. Like any other function, we can use any variable name as the input for letter 1d453 minus 1, so we will often write letter 1d453 minus 1, letter 1d465, which we read as f inverse of x. Keep in mind that letter 1d453 minus 1, letter 1d465, not equal to 1 letter 1d453, letter 1d465, and not all functions have inverses. Example 1, identifying an inverse function for a given input-output pair if, for a particular one-to-one function letter 1d453. 2 equals 4 and letter 1d453. 5 equals 12. What are the corresponding input and output values for the inverse function? Solution: the inverse function reverses the input and output quantities. So if letter 1d453, 2 letter 1d453, 5 equals 4, then letter 1 d453 minus 1, 4 equals 2. 12 then f minus 1, 12 equals 5. Alternatively, if we want to name the inverse function g, then letter 1 d454, 4 equals 2 and letter 1 d454, 12 equals 5. Analysis: notice that if we show the coordinate pairs in a table form, the input and output are clearly reversed. See Table 1. X, letter 1 d453, letter 1 d465. X, letter 1 d454, letter 1 d465. 2, 4, 4, 2, 5, 12, 12. 5. Table 1. Try it 1 given that letter 210 e minus 1. 6 equals 2. What are the corresponding input and output values of the original function h? How to given two functions letter 1 d453, letter 1 d465, and letter 1 d454, letter 1 d465. Test whether the functions are inverses of each other. Determine whether or letter 1 d454, letter 1 d453, letter 1 d465 equals letter 1 d465. If either statement is true, then both are true, and letter 1 d454 equals letter 1 d453 minus 1, and letter 1 d453 equals letter 1 d454 minus 1. If either statement is false, then both are false, and letter 1 d454 not equal to letter 1 d453 minus 1, and letter 1 d453 not equal to letter 1 d454 minus 1. Example 2. Testing inverse relationships algebraically if letter 1 d453, letter 1 d465 equals 1 letter 1 d465 plus 2 and letter 1 d454. Letter 1 d465 equals 1 letter 1 d465 minus 2 is letter 1 d454 equals letter 1 d453 minus 1. Solution: letter 1 d454, letter 1 d453, letter 1 d465 equals 1, 1 letter 1 d465 plus 2 minus 2 letter 1 d465 plus 2 minus 2 letter 1 d465. We must also verify the other formula. Letter 1 d453, letter 1 d454, letter 1 d465 equals 11 letter 1 d465 minus 2 plus 211 letter 1 d465 letter 1 d465. So letter 1 d454 equals letter 1 d453 minus 1, and letter 1 d453 equals letter 1 d454 minus 1. Analysis: notice the inverse operations are in reverse order of the operations from the original function. Try it too if letter 1 d453, letter 1 d465 equals letter 1 d465 3 minus 4, and letter 1 d454, letter 1 d465 equals letter 1 d465 plus 4 square 3, is letter 1 d454 equals letter 1 d453 minus 1. Example 3. Determining inverse relationships for power functions if letter 1 d453, letter 1 d465 equals letter 1 d465 3, the cube function, and letter 1 d454, letter 1 d465 equals 13, letter 1 d465 is letter 1 d454 equals letter 1 d453 minus 1. Solution: letter 1 d453, letter 1 d454, letter 1 d465 equals letter 1 d465 327, not equal to letter 1 d465. No, the functions are not inverses. Analysis: the correct inverse to the cube is, of course, the cube root letter 1 d465 square 3 equals letter 1 d465 13. That is, the 1/3 is an exponent, not a multiplier. Try it 3 if letter 1 d453, letter 1 d465 equals letter 1 d465 minus 1, 3 a n d letter 1 d454, letter 1 d465 equals letter 1 d465 square 3 plus 1 is letter 1 d454 equals letter 1 d453 minus 1. Finding domain and range of inverse functions, the outputs of the function f are the inputs to letter 1 d453 minus 1. So the range of f is also the domain of letter 1 d453 minus 1. Likewise, because the inputs to f are the outputs of letter 1 d453 minus 1, the domain of f is the range of letter 1 d453 minus 1. We can visualize the situation as in Figure 3. Domain and range of a function and its inverse. Figure 3. Domain and range of a function and its inverse when a function has no inverse function it is possible to create a new function where that new function on a limited domain does have an inverse function. For example, the inverse of letter 1d453, letter 1d465, equals letter 1d465 square is letter 1d453 minus 1, letter 1d465, equals letter 1d465 2, because a square undoes a square root. But the square is only the inverse of the square root on the domain 0, infinity. Since that is the range of letter 1d453, letter 1d465 equals letter 1d465 square. We can look at this problem from the other side, starting with the square, toolkit quadratic, function letter 1d453, letter 1d465 equals letter 1d465 2. If we want to construct an inverse to this function, we run into a problem, because for every given output of the quadratic function, there are two corresponding inputs, except when the input is 0. For example, the output 9 from the quadratic function corresponds to the inputs 3 and 3. But an output from a function is an input to its inverse. If this inverse input corresponds to more than one inverse output, input of the original function, then the inverse is not a function at all. To put it differently, the quadratic function is not a one-to-one function. It fails the horizontal line test, so it does not have an inverse function. In order for a function to have an inverse, it must be a one-to-one function. In many cases, if a function is not one-to-one, we can still restrict the function to a part of its domain on which it is one-to-one. For example, we can make a restricted version of the square function letter 1d453, letter 1d465, equals letter 1d465 2 with its domain limited to 0, infinity, which is a one-to-one function. It passes the horizontal line test, and which has an inverse, the square root function. If letter 1d453, letter 1d465 equals letter 1d465 minus 1 2 on 1 infinity, then the inverse function is letter 1d453 minus 1, letter 1d465 equals letter 1d465 square plus 1. The domain of f equals range of letter 1d453 minus 1 equals 1, infinity. The domain of letter 1d453 minus 1 equals range of f equals 0, infinity. Q and A, is it possible for a function to have more than one inverse? No. If two supposedly different functions, say g and h, both meet the definition of being inverses of another function f, then you can prove that letter 1d454 equals letter 210e. We have just seen that some functions only have inverses if we restrict the domain of the original function. In these cases, there may be more than one way to restrict the domain, leading to different inverses. However, on any one domain, the original function still has only one unique inverse. Domain and range of inverse functions the range of a function letter 1d453, letter 1d465, is the domain of the inverse function letter 1d453 minus 1, letter 1d465. The domain of letter 1d453, letter 1d465, is the range of letter 1d453 minus 1, letter 1d465. How to given a function, find the domain and range of its inverse. If the function is one-to-one, write the range of the original function as the domain of the inverse, and write the domain of the original function as the range of the inverse. If the domain of the original function needs to be restricted to make it one-to-one, then this restricted domain becomes the range of the inverse function. Example 4, finding the inverses of toolkit functions. Identify which of the toolkit functions besides the quadratic function are not one-to-one, and find a restricted domain on which each function is one-to-one, if any. The toolkit functions are reviewed in Table 2. We restrict the domain in such a fashion that the function assumes all y values exactly once. Constant identity, quadratic, cubic, reciprocal, letter 1d453. Letter 1d465 equals letter 1d450, letter 1d453. Letter 1d465 equals letter 1d465, letter 1d453. Letter 1d465 equals letter 1d465, 2 letter 1d453. Letter 1d465 equals letter 1d465, 3 letter 1d453. Letter 1d465 equals 1 letter 1d465. Reciprocal squared cube root square, root absolute value letter 1d453. Letter 1d465 equals 1 letter 1d465, 2 letter 1d453. letter 1d465 equals letter 1d465 square 3 letter 1d453. Letter 1d465 equals letter 1d465 square letter 1d453. Letter 1d465 equals letter 1d465 table 2. Solution: the constant function is not one-to-one. And there is no domain, except a single point, on which it could be one-to-one, so the constant function has no inverse. The absolute value function can be restricted to the domain 0, infinity, where it is equal to the identity function. The reciprocal squared function can be restricted to the domain 0, infinity. Analysis: we can see that these functions, if unrestricted, are not one-to-one by looking at their graphs, shown in Figure 4. They both would fail the horizontal line test. However, if a function is restricted to a certain domain so that it passes the horizontal line test, then in that restricted domain, it can have an inverse. Graph of an absolute function. Figure 4, A, absolute value. B, reciprocal square. Try it for the domain of function f is 1, infinity, and the range of function f is minus infinity, minus 2. Find the domain and range of the inverse function. Finding and evaluating inverse functions. Once we have a one-to-one function, we can evaluate its inverse at specific inverse function inputs, or construct a complete representation of the inverse function in many cases. Inverting tabular functions. Suppose we want to find the inverse of a function represented in table form. Remember that the domain of a function is the range of the inverse, and the range of the function is the domain of the inverse. So we need to interchange the domain and range. Each row or column of inputs becomes the row or column of outputs for the inverse function. Similarly, each row or column of outputs becomes the row or column of inputs for the inverse function. Example 5, interpreting the inverse of a tabular function, a function letter 1d453, letter 1d461, is given in Table 3, showing distance in miles that a car has traveled in t minutes. Find and interpret letter 1d453 minus 170. Letter 1d461, minutes, 30, 50, 70, 90, letter 1d453, letter 1d461. Miles, 20, 40, 60, 70. Table 3 solution: the inverse function takes an output of f and returns an input for f. So in the expression letter 1d453 minus 1, 70, 70 is an output value of the original function, representing 70 miles. The inverse will return the corresponding input of the original function, f, 90 minutes, so letter 1d453 minus 1, 70, equals 90. The interpretation of this is that, to drive 70 miles, it took 90 minutes. Alternatively, recall that the definition of the inverse was that if letter 1d453, letter 1d44e equals letter 1d44f, then letter 1d453 minus 1, letter 1d44f equals letter 1d44e. By this definition, if we are given letter 1d453 minus 1, 70 equals letter 1d44e, then we are looking for a value a so that letter 1d453, letter 1d44e equals 70. In this case, we are looking for a t so that letter 1d453, letter 1d461 equals 70, which is when letter 1d461 equals 90. Try it 5 using Table 4, find and interpret a letter 1d453, 60, and b letter 1d453 minus 1, 60. Letter 1d461, minutes, 30, 50, 60, 70, 90, letter 1d453, letter 1d461. Miles, 20, 40, 50, 60, 70. Table 4, evaluating the inverse of a function. Given a graph of the original function, we saw in functions and function notation that the domain of a function can be read by observing the horizontal extent of its graph. We find the domain of the inverse function by observing the vertical extent of the graph of the original function, because this corresponds to the horizontal extent of the inverse function. Similarly, we find the range of the inverse function by observing the horizontal extent of the graph of the original function, as this is the vertical extent of the inverse function. If we want to evaluate an inverse function, we find its input within its domain, which is all or part of the vertical axis of the original function's graph. How to, given the graph of a function, evaluate its inverse at specific points. Find the desired input on the y-axis of the given graph. Read the inverse function's output from the x-axis of the given graph. Example 6. Evaluating a function and its inverse from a graph at specific points, a function letter 1d454, letter 1d465, is given in Figure 5. Find letter 1d454, 3, and letter 1d454 minus 1, 3. Graph of g, x. Figure 5 solution to evaluate letter 1d454, 3. We find 3 on the x-axis and find the corresponding output value on the y-axis. The point 31 tells us that letter 1d454, 3 equals 1. To evaluate letter 1d454 minus 1, 3, recall that by definition letter 1d454 minus 1, 3 means the value of x for which letter 1d454, letter 1d465, equals 3. By looking for the output value 3 on the vertical axis, we find the point 53 on the graph, which means letter 1d454, 5, equals 3, so by definition, letter 1d454 minus 1, 3 equals 5. See Figure 6. Graph of g, x. Figure 6. Try it 6 using the graph in Figure 5. A. Find letter 1d454 minus 1, 1, and B. Estimate letter 1d454 minus 1, 4. Finding inverses of functions represented by formulas. Sometimes we will need to know an inverse function for all elements of its domain, not just a few. If the original function is given as a formula, for example, y as a function of x, we can often find the inverse function by solving to obtain x as a function of y. How to given a function represented by a formula, find the inverse. Make sure f is a one-to-one function. Solve for x. Interchange x and y, replace y with letter 1d453 minus 1, letter 1d465. Variables may be different in different cases, but the principle is the same. Example 7. Inverting the Fahrenheit to Celsius function, find a formula for the inverse function that gives Fahrenheit temperature as a function of Celsius temperature. Letter 1d436 equals 59, letter 1d439 minus 32. Solution: letter 1d436, letter 1d436, 95, letter 1d439 equals 59. Letter 1d439 minus 32. Letter 1d439 minus 3,295, letter 1d436, plus 32 by solving in general. We have uncovered the inverse function. If letter 1d436 equals letter 210e, letter 1d439 equals 59, letter 1d439 minus 32. Then letter 1d439 equals letter 210e minus 1. Letter 1d436 equals 95, letter 1d436 plus 32 in this case. We introduced a function h to represent the conversion because the input and output variables are descriptive, and writing letter 1d436 minus 1 could get confusing. Try it 7. Solve for x in terms of y given letter 1d466 equals 13, letter 1d465 minus 5. Example 8. Solving to find an inverse function, find the inverse of the function letter 1d453, letter 1d465, equals 2, letter 1d465 minus 3 plus 4. Solution: letter 1d466, letter 1d466 minus 4, letter 1d465 minus 3, letter 1d465 equals 2, letter 1d465 minus 3, plus 42, letter 1d465, minus 32, letter 1d466 minus 42, letter 1d466 minus 4 plus 3. Set up an equation. Subtract 4 from both sides. Multiply both sides by letter 1d465 minus 3 and divide by letter 1d466 minus 4. Add 3 to both sides. So letter 1d453 minus 1. Letter 1d466 equals 2, letter 1d466 minus 4 plus 3, or letter 1d453 minus 1. Letter 1d465 equals 2, letter 1d465 minus 4 plus 3. Analysis: the domain and range of f exclude the values 3 and 4, respectively. F and letter 1d453 minus 1 are equal at 2 points, but are not the same function, as we can see by creating Table 5. x125, letter 1d453 minus 1, letter 1d466, letter 1d453, letter 1d465. 325y, Table 5, Example 9, solving to find an inverse with radicals, find the inverse of the function letter 1d453, letter 1d465, equals 2 plus letter 1d465 minus 4 square. Solution letter 1d466. Letter 1d466 minus 2, 2, letter 1d465 equals 2 plus letter 1d465 minus 4 square letter 1d465 minus 4 letter 1d466 minus 2, 2 plus 4 so letter 1d453 minus 1 letter 1d465 equals letter 1d465 minus 2, 2 plus 4. The domain of f is 4 infinity. Notice that the range of f is 2 infinity. So this means that the domain of the inverse function letter 1d453 minus 1 is also 2, infinity. Analysis the formula we found for letter 1d453 minus 1, letter 1d465. Looks like it would be valid for all real x. However, letter 1d453 minus 1 itself must have an inverse, namely f, so we have to restrict the domain of letter 1d453 minus 1 to 2 infinity, in order to make letter 1d453 minus 1 a one-to-one function. This domain of letter 1d453 minus 1 is exactly the range of f. Try at 8. What is the inverse of the function letter 1d453? Letter 1d465 equals 2 minus letter 1d465 square. State the domains of both the function and the inverse function. Finding inverse functions and their graphs. Now that we can find the inverse of a function, we will explore the graphs of functions and their inverses. Let us return to the quadratic function letter 1d453. Letter 1d465 equals letter 1d465 2 restricted to the domain 0, infinity, on which this function is one-to-one, and graph it as in Figure 7. Graph of f, x. Figure 7 quadratic function with domain restricted to 0, infinity. Restricting the domain to 0, infinity makes the function one-to-one. It will obviously pass the horizontal line test, so it has an inverse on this restricted domain. We already know that the inverse of the toolkit quadratic function is the square root function. That is, letter 1d453 minus 1, letter 1d465, equals letter 1d465 square. What happens if we graph both f and letter 1d453 minus 1 on the same set of axes, using the x-axis for the input to both fand letter 1d453 minus 1? We notice a distinct relationship. The graph of letter 1d453 minus 1, letter 1d465, is the graph of letter 1d453, letter 1d465, reflected about the diagonal line letter 1d466 equals letter 1d465, which we will call the identity line, shown in Figure 8. Graph of f, x, and f minus 1, x. Figure 8 square and square root functions on the non-negative domain. This relationship will be observed for all one-to-one functions because it is a result of the function and its inverse swapping inputs and outputs. This is equivalent to interchanging the roles of the vertical and horizontal axes. Example 10, finding the inverse of a function using reflection about the identity line, given the graph of letter 1d453, letter 1d465. In Figure 9, sketch a graph of letter 1d453 minus 1, letter 1d465. Graph of f minus 1, x. Figure 9 solution. This is a one-to-one function, so we will be able to sketch an inverse. Note that the graph shown has an apparent domain of 0, infinity, and range of minus infinity, infinity, so the inverse will have a domain of minus infinity, infinity, and range of 0, infinity. If we reflect this graph over the line letter 1d466 equals letter 1d465, the point 10 reflects to 1, and the point 42 reflects to 24. Sketching the inverse on the same axes as the original graph gives Figure 10. Graph of f, x, and f minus 1, x. Figure 10, the function and its inverse, showing reflection about the identity line. Try at 9. Draw graphs of the functions f and letter 1d453 minus 1 from example 8. Q and A. Is there any function that is equal to its own inverse? Yes. If letter 1d453 equals letter 1d453 minus 1, then, and we can think of several functions that have this property. The identity function does, and so does the reciprocal function, because 11 letter 1d465 equals letter 1d465 any function letter 1d453. Letter 1d465 equals letter 1d450 minus letter 1d465, where c is a constant, is also equal to its own inverse. Media access, these online resources for additional instruction and practice with inverse functions. Inverse functions, 101 functions, inverse function, values using graph restricting the domain, and finding the inverse 3. 7 section, exercises verbal 1. Describe why the horizontal line test is an effective way to determine whether a function is 101. 2. Why do we restrict the domain of the function letter 1d453, letter 1d465 equals letter 1d4652 to find the function's inverse? 3. Can a function be its own inverse? Explain. 4. Are one-to-one functions either always increasing or always decreasing? Why or why not? 5. How do you find the inverse of a function algebraically? Algebraic 6. Show that the function letter 1d453, letter 1d465, equals letter 1d44e minus letter 1d465 is its own inverse for all real numbers. For the following exercises, find letter 1d453 minus 1, letter 1d465 for each function. 7. Letter 1d453, letter 1d465 equals letter 1d465 plus 3 8. Letter 1d453, letter 1d465 equals letter 1d465 plus 5 9. Letter 1d453, letter 1d465 equals 2 minus letter 1d465 10. Letter 1d453, letter 1d465 equals 3 minus letter 1d465 11. Letter 1d453, letter 1d465 equals letter 1d465 letter 1d465 plus 2 12. Letter 1d453, letter 1d465 equals 2 letter 1d465 plus 35 letter 1d465 plus 4 for the following exercises. Find a domain on which each function f is 1-to-1 and non-decreasing. Write the domain in interval notation. Then find the inverse of f restricted to that domain. 13. Letter 1d453, letter 1d465 equals letter 1d465 plus 7 2 14. Letter 1d453, letter 1d465 equals letter 1d465 minus 6 2 15. Letter 1d453, letter 1d465 equals letter 1d465 2 minus 5 16. Given letter 1d453, letter 1d465 equals letter 1d465 2 plus letter 1d465 and letter 1d454. Letter 1d465 equals 2 letter 1d465 1 minus letter 1d465. A. Find letter 1d453, letter 1d454, letter 1d465, and letter 1d454, letter 1d453, letter 1d465. B. What does the answer tell us about the relationship between letter 1d453, letter 1d465, and letter 1d454, letter 1d465? For the following exercises, use function composition to verify that letter 1d453, letter 1d465, and letter 1d454, letter 1d465 are inverse functions. 17. Letter 1d453, letter 1d465 equals letter 1d465 minus 1 square 3 and letter 1d454. Letter 1d465 equals letter 1d465 3 plus 1 18. Letter 1d453, letter 1d465 equals minus 3 letter 1d465 plus 5 and letter 1d454. Letter 1d465 equals letter 1d465 minus 5 minus 3. Graphical for the following exercises. Use a graphing utility to determine whether each function is 1-to-1. 19. 20. Letter 1d453, letter 1d465 equals 3 letter 1d465 plus 1 square 321. Letter 1d453, letter 1d465 equals minus 5 letter 1d465 plus 122. Letter 1d453, letter 1d465 equals letter 1d465 3 minus 27 for the following exercises. Determine whether the graph represents a 1-to-1 function. 23. Graph of a parabola. 24. Graph of a step function. For the following exercises, use the graph of f shown in Figure 11. Graph of a line, Figure 1125. Find letter 1d453, 0. 26. Solve letter 1d453, letter 1d465 equals 0. 27. Find letter 1d453 minus 1, 0. 28. Solve letter 1d453 minus 1, letter 1d465 equals 0. For the following exercises, use the graph of the one-to-one function shown in Figure 12. Graph of a square root function. Figure 12:29. Sketch the graph of letter 1d453 minus 1. 30. Find letter 1d453, 6, and letter 1d453 minus 1, 2. 31. If the complete graph of f is shown, find the domain of f. 32. If the complete graph of f is shown, find the range of f numeric for the following exercises, evaluate or solve, assuming that the function f is one-to-one. 33. If letter 1d453, 6 equals 7, find letter 1d453 minus 1, 7. 34. If letter 1d453, 3 equals 2, find letter 1d453 minus 1, 2. 35. If letter 1d453 minus 1, minus 4 equals minus 8, find letter 1d453 minus 8. 36. If letter 1d453 minus 1, minus 2 equals minus 1, find letter 1d453 minus 1. For the following exercises, use the values listed in Table 6 to evaluate or solve. X0 1 2 3 4 5 6 7 8 9, letter 1d453, letter 1d465, 807426539 Table 637. Find letter 1d453 1, 38. Solve letter 1d453, letter 1d465 equals 3, 39. Find letter 1d453 minus 1, 0, 40. Solve letter 1d453 minus 1, letter 1d465 equals 7, 41. Use the tabular representation of f in Table 7 to create a table for letter 1d453 minus 1, letter 1d465. X3 6 9 13 14 letter 1d453, letter 1d465, 1 4 7 12 16 Table 7 technology. For the following exercises, find the inverse function. Then graph the function and its inverse. 42. Letter 1d453, letter 1d465 equals 3 letter 1d465 minus 243. Letter 1d453, letter 1d465 equals letter 1d465 3 minus 144. Find the inverse function of letter 1d453. Letter 1d465 equals 1 letter 1d465 minus 1. Use a graphing utility to find its domain and range. Write the domain and range in interval notation. Real-world applications 45. To convert from x degrees Celsius to y degrees Fahrenheit, we use the formula letter 1d453, letter 1d465, equals 95 letter 1d465 plus 32. Find the inverse function, if it exists, and explain its meaning. 46. The circumference c of a circle is a function of its radius given by letter 1d436, letter 1d45f, equals 2 letter 1d70b letter 1d45f. Express the radius of a circle as a function of its circumference. Call this function letter 1d45f, letter 1d436. Find letter 1d45f, 36 letter 1d70b, and interpret its meaning. 47. A car travels at a constant speed of 50 miles per hour. The distance the car travels in miles is a function of time, t, in hours given by letter 1d451, letter 1d461, equals 50 letter 1d461. Find the inverse function by expressing the time of travel in terms of the distance traveled. Call this function letter 1d461, letter 1d451. Find letter 1d461, 180, and interpret its meaning.